screen on this. This is really bad. That's not me. Okay, we come to the 28th annual CESM Workshop. We are really thrilled to see this many people in person. It has been 4 years since we did it last time, and we have about 250 registered in person and another 250 or more online. So for those online people, if you encounter any technical issues, please bear with us. And this is a large meeting in this hybrid format. And if you encounter any issues, please let us know, and we'll try to address them as soon as possible. So without further delay, I'll invite Everett Joseph. He is the NCAR director, to welcome everybody. Thank you, Everett. I won't.
There's a little trick here that very few of us know about. That's right. At NCAR, we have all the technology we need. Let me get my notes here so I don't ramble on and stay within the time limit that I'm allotted. So thanks, Gokhan. It's really my pleasure to welcome all of you this year to this CSM workshop. And it's really, as Gokhan said, it's really wonderful to see so many people here in person. Really looking forward to all the networking that's going to happen. And of course, the strong participation that we have online. And your participation, both here in person and online, is really a reflection of your investment, the investment of this community in CSM, which is really important to NCAR, of course, and incredibly important to the community. And I really don't need to tell this group what a profoundly important tool CESM is for the Earth System science community, and how much it's really been a benefit already to society. I think the fact that there are about on the order of, 500 people that are registered for this workshop really speaks for itself. But it's really important for me to underscore that. As it is every year, the utility of this really world-class model were really on display in the formal presentation, all the side conversation, all the networking, all the planning that happens here. And this year, of course, is no exception to that. The talks, they highlight the amazing work in the development and the application of CESM across all parts of the Earth system, and that's really remarkable. I also don't need to remind this group, but again, I will. Just the power of CESM really lies in the community. CESM is truly an exemplar of community development and community governance that really sets the bar for community modeling efforts everywhere. In fact, I would say that it's this model that this community has developed over the many and many years is trailblazing. It's unprecedented. And I want to reassure you that of NCAR's continued commitment to strong community governance. It's really part of our DNA here. I want to thank you all for being really a part of that community, continuing that spirit of community governance, community development, continuing to make the community thrive, and really for sharing your expertise as part of that, right? Especially at this these workshops, at this workshop, really to continue to ensure the continued success of CESM. I am really excited to see all the things that are happening, but I'm particularly excited to see the emerging community interest in seamless Earth system predictability across timescales. This is an opportunity for CESM to advance new scientific boundaries and broaden the communities that are really scientifically empowered by CESM. It's really NCAR's mission. It's our bread and butter. It's really the core of our mission to make science widely accessible across the university community. NCAR is really here to enable the university community. And this is also aligned with our scientific mission. It's also aligned with our actionable science theme and our strategic plan. And responding to society as we have and as we continue to do is really important for us and an important part of our mission. And today there's really great demand in our community to provide, as we all here know, again, I'm speaking to the people who already know this, but there's great demand in our community to provide detailed information about how global phenomena, including climate change, will impact communities on a local scale, right? They want to understand, for example, how will they be impacted by changing intensity and changing frequency of extreme events associated with climate change. They want to understand how the communities adapt and become resilient to this change that's taking place. And the research community, us, the science community, really have a role to play and they really have responsibility in that regard. But it not only requires basic and applied research that we know how to do really well in Earth system predictability, it really also requires how we work together. It requires collaboration across multiple communities, new types of collaborations that we're not accustomed to, across weather and climate, across air quality, across, even here at NCAR, across geospace communities, hydrology, certainly social science. There's been a lot of dialogue about how we collaborate and work better with the social sciences, and we're doing it. And it's about breaking down barriers, traditional barriers that have existed, to make these it's not just collaborating, but it's how do you break down barriers and set up new ways of working together that make these collaborations thrive and make them effective. And I'm really encouraged to see the CESM community, this community, continue to look for ways to expand CESM science scope and how do you facilitate this, this new way of doing work and this new research. I want to take a moment to embarrass a few people, starting with John Patch. John, where are you? Please stand up, wave, you're right in the front. John is the, I'm not going to invite you up to stage. John is the incoming director of CGD, beginning September 5th. And John's come stand car from the UK Met office where he serves, he's still working for UK Met as an associate director. John is a former CGD postdoc in the 1990s, so some of you may remember John, who've been here that long. And he's worked on the development of climate and weather models for more than 25 years. He earned his PhD in atmospheric sciences from the University of Reading. And I'm confident that John is really going to be a champion for CGD and for CESM, and that his experience, his leadership experience, all the skills that he's gained over the last 25 plus years really will build on, right? It will build on CGD, the successes of CGD, of CESM already, and continue the scientific excellence that we've come accustomed to here in the best interest of the community. So I'm really confident that John's gonna do that. Although he doesn't start his position until till September, John really wanted to be here at this workshop to meet and hear from you, to listen to your concerns, to hear about opportunities. He also wanted to take a deep dive into the science that'll happen here this week. So, so please take him up on that opportunity. John will be here attending the workshop for the next few days. And I really encourage you to, during the break, say hi and introduce yourself to him. We all are hugely indebted to Dave Lawrence and Yaga Richter, who served as interim directors over the last 6 months or so since JF left CGD. And I want to say that, and you know, we all say that, right? But I want to say that they weren't just caretakers, and I think the staff know this. They really took on some tough problems and made progress on those problems. And so I think we all owe them a huge debt of gratitude. In fact, I'd like to. Okay, the other person to embarrass publicly is our fearless leader, Gokhan, who's been chief scientist. He's been our leader for what, 5.5 years? 5.5 years. There's a lot that I can embarrass you with here, but Gokhan again has been our fearless leader and has really led, trailblazed, if you will, the development of CESM over the last 5.5 years. Really held his community together and just really continued that tradition of excellence. And what I will say is also done some really transformational work. And we're, again, hugely indebted to Gokhan for his expertise, his contribution, and you know his sacrifice, frankly, to do the work that he's been successful in doing. So Gokhan, we're going to embarrass you with a certificate. Yaga, please come, please join me. And this is a certificate of recognition. Yaga, do you want to add anything to it?
Sure. So the only thing I'll add, apparently, when Gokhan took on the position, he got a hamster wheel. That's part of the CSM transition, and I can vouch that he's been on that hamster wheel for over 5.5 years. He starts his day between 6 and 7, because that's usually when I get the messages from him, and they don't end till 7 p.m. at night. So please really give him a big round of applause. It's been a huge job, and we really appreciate it.
Thank you so much for that well-deserved recognition. Gokhan, don't go too you I'm done. You only gave me 10 minutes. So thanks again for your attention, and just really wishing you, again, lovely to see so many people here, and I'm just wishing you a really productive meeting here for this week, as I know you'll have. Thanks.
Thank you very much. Okay, now I need to know the secret here to reduce. It's working. I forgot to mention one thing. Since this is a hybrid event, if you have any questions, please use the microphones. There are 3 of them, I believe, so that everybody can hear you. And I just wanted to also remind everybody our code of conduct. Please adhere to this code of conduct and treat each other respectfully as you would like to be treated yourself. Thank you. So with that, I'll start. Again, welcome. I already welcome you. This is my second welcome. And what I'll try to do here is I'll try to /introduction to the CSM science and /introduction to the CSM science and strategic plan. Then I'll talk about some of our high and ultra high resolution efforts that have been going on and planned activities. I would like to show some highlights afterwards and then provide a short summary of where we are going towards our next model version, that'll be CESM version 3. However, before going further, I just wanted to remind everybody what we mean by community. You'll hear it in my presentation. CSM is the Community Earth System model, and you'll also hear it throughout this workshop. So I put this definition, at least this is my definition, vetted by SSC and other members, of what we mean by community in this respect. So in our case, community refers to all entities whose members are engaged in research and or education in Earth system sciences. So it's a rather broad definition. You guys, the community, form the collaborative foundations of CESM, and all of these entities include universities, laboratories, national laboratories, private sector, and other organizations, both nationally and internationally. So you guys are all members of this community, and it's a rather broad definition. So that's what I just wanted to clarify up front. So with that, this is the cover page for the, I can see it. This is really fancy. You can point it to the screen and it shows up there. So this is the CSM strategic plan. It was released in March 2023. It's available at the website, oops, not that one, listed down here, if I can show it, okay. And I think this is the last one was written by Peter Gent and the company back in 2008, 2009. So it has been almost 15 years to come up with a new strategic plan and science plan. It provides scientific and modeling priorities and guidelines for the CSM project over the next 5 years. It is based on extensive input, really, we received from you guys, from the community, starting back in 2019 in the annual CSM workshop. It is also consistent with the vision of the NCAR strategic plan. You can find many elements essentially consistent with the NCAR strategic plan. I should also mention that it is consistent with many elements of several national plans that came out since 2020, including the one that came out from the National Academy of Sciences, providing a roadmap for NSF Earth system modeling. The strategic priorities are determined by the Earth system modeling community's present and anticipated and emerging scientific needs. Guiding principles include advancing science and understanding of the Earth system and providing information, actionable information for societal use at relevant temporal and spatial scales in strong collaboration with the community. It has been a tough act. It is actually representing a balance between curiosity-driven, use-inspired research and related technical developments. And I use this balance here. And if people are interested in buying it, it's used in pharmaceutical industry. It's available, I think, on eBay for 45,000 euros or something like that. So the unique aspect and strength of the CSM project are its community-driven research and developments. And the plan advances coupled Earth system science and applications through CESM's unique capabilities. The goal is to bridge weather, climate, chemistry, and geoscience applications and communities. At the same time, it aspires to develop additional capabilities to address emerging science questions including those associated with ultra-high or high resolution, I'll talk about it quite a bit, both globally and regionally, while recognizing related challenges and offering pathways as to how we wish to address these challenges. And if you are interested in all the science drivers and goals are articulated within each priority area within the strategic plan. So one of the main parts of the strategic plan is actionable science and climate justice, as Everett also alluded to. These are two related and fundamental objectives for the CESM project. To chart an organized path forward on these two topics, we had, in strong collaboration with the community, we had two cross-working group sessions at last year's workshop. They were on justice and climate change and actionable science and CESM. And several really good recommendations came out of those cross-working group sessions that are also included in the strategic plan. And SSC formed a task team. It has been initiated. It's led by Monica Morrison, somewhere in the audience. And there will be a related cross-working session, I believe, this afternoon. A challenge for our project is, especially internally here, is that CSM does not have a critical mass of internal expertise to lead and enhance its societally relevant science and climate justice efforts. So we'll be heavily relying on external community. So this is going to be an important aspect. And as a first step, we will organize a workshop, and that workshop either it's going to happen in the fall or early spring next year, so please stay tuned for that effort. So I wanted to spend a few minutes on our ongoing high and ultra-high resolution efforts, and just for clarifying what I mean by high and ultra-high, I actually included the resolution definitions in my view down there. High is quarter-degree atmosphere coupled to 10th of a degree ocean, and ultra-high is less than or finer than 5-kilometer resolution. As many of you know, we have quite a bit of, and it's an ongoing effort on CSM high-resolution simulations using an older version of the model 1.3. This effort started with the IHASP, that's the International Laboratory for High-Resolution Earth System Prediction. It was in collaboration between TAMU, Qingdao, and us. It got terminated, but we produced quite an impressive set of high-resolution simulations that are listed here. And I wanted to particularly highlight decadal prediction simulations at this resolution. Steve Yeager here is playing a major role in that effort. All of these data sets are available to the community. Needless to say, there are so many science and societal applications of these simulations, and this configuration is being used also for new simulations, such as the advanced, advanced scientific and discovery effort that's going to be running on the new machined retro. Our Paleoclimate working group will be using this configuration to study various past climate events that are included here. I'm also happy to report that we had a successful proposal funded by NSF. We will be expanding these data sets further. We will be performing additional prediction simulations. We'll be performing additional RCP scenario simulations with this configuration. We'll be increasing the ensemble size for the historical and transient period from 3 to 10 members. This is used also, regional downscaling is also an important part. It is being used already, the data sets, for regional downscaling purposes, for example, Gulf of Mexico, and there are numerous societal applications, sea level rise studies. It's being used for fisheries applications, and lately, most recently, is used for sea turtle habitat studies in Gulf of Mexico, for example. Another high resolution, it's getting into the ultra high resolution realm actually, is we have just submitted a proposal to NSF to enable cloud permitting coupled climate modeling. And this is led by University of Michigan and Texas A&M University. The goal here is to incorporate Department of Energy, E3SM's non-hydrostatic version of the spectral element atmospheric dynamical core into CAM via SEMA. And for those of you who are not familiar with SEMA, it stands for System for Integrated Modeling of the Atmosphere. There are quite a few science applications to this effort. It brings both Fortran and C++ versions so that we can use the GPU side of the new machined retro. Initial science applications would include mesoscale convective systems over the continental United States and air-sea interactions associated with tropical cyclones. This is a rather strategic partnership with the university community, with Department of Energy, Earthworks project that's based in CSU, and 3 NCAR labs, MCube, CISL, and CGD. My own personal thinking in these ultra-high or high-resolution efforts is that I think community is recognizing that ultra-high-resolution simulations cannot be run too long for climate applications, but there is enormous scientific value if we use these simulations in concert, in harmony, that's what I would like to use, in harmony or seamlessly with low, high, and ultra-high resolution versions, because all those simulations can learn from each other for parameterization, development, or including missing physics. An immediate application area, for example, this effort is our already existing spectral element variable resolution grids in the atmosphere. I've used several examples of this variable resolution spectral element up here, and this is already being used extensively by the university community. The science areas, I just included a few examples here, include the North Atlantic configuration to address deficiencies in jet stream variability, for example, in relation to North Atlantic SSD variability. It includes, for example, the South Asian configuration is being used to study air quality over India and in that Asian subcontinent. And I'll show the example of the last one here. The Arctic configuration is used to study surface mass balance with the glacials with increasing CO2, for example. As these configurations, the examples here are using 1/8 or so resolution, but as we go to higher and higher resolution with this variable resolution configuration, we're essentially pushing the boundaries of the non-hydrostatic hydrostatic split. So this would be an important application area for the spectral element non-hydrostatic work. And of course, there are so many science questions, including how to use scale selective parameterizations when you switch from non-hydrostatic to hydrostatic regimes. Okay, I said I'll show you an example. I think this is a very nice example of variable resolution Arctic grid use. This is a fully coupled CESM 2.2 simulation in which the community ice sheet model, two-way interacting, is used in this application. What they have done, they've run first a 180-year pre-industrial control simulation. Then they increased this is the CO2 forcing, they increased the CO2 concentration at 1% per year level up to quadrupling. And then they kept it constant for another 140 years to see what's going on. And the plots on the right side here show the albedo, surface mass balance, thickness, and velocity, ice velocity distributions, land ice velocity distributions over Greenland. The left side is the PI control. These are the actual values, the fields. The middle and the right panels show differences from the PI control at quadrupling time and also at the end of the integration. Without going too much into detail, you can see that there are significant albedo changes. They are decreasing, actually, particularly around the Greenland coastal areas. And in turn, essentially, you see reduction in the surface mass balance, along with thickness reductions in the periphery of Greenland. But there's also an increase in the surface mass balance and ice thickness within the island, interior of the island. Another application area of the community ice sheet model is it's used in mountain glacier simulations. This is for specific glaciers in the Alps, and it is the first third-order ice sheet model used to simulate such mountain glaciers at resolutions of 200 meters or even finer. And there are good agreements between the observational distributions. In the ongoing work, our Climate Working Group will be submitting this thing to Glacier MIP3 project, and it will be also used for high mountain Asia simulations that's underway. For the future, it's going to be expanded to other glacials, and it will be used in studies of freshwater availability and security at decadal time scale, so that's an important societal application, and it will be used in coupled land model simulations as well. In the last part of the talk, when I talk about towards CESM3, I just wanted to make sure that you understand that all of these new features will be incorporated into the future versions of CESM. So another, application area highlight is another study. They've looked at using CESM impacts of freshwater input in the North Atlantic during the last deglaciation in western United States. In this particular example, it is looking into, for example, comparisons with proxy records. Proxy records are suggesting that there were weather conditions in the western United States associated with the Heinrich events. And those events, for those of you who are not familiar, they're essentially associated with glacial-related freshwater discharge in the North Atlantic, and they result in reduced AMOC strength. That's the Atlantic Meridional Overturning Circulation. That's the most important thing in the world, if you are me, right? That's so in these simulations, on the right, this panel, it's the control, 16,000 years ago. And this freshwater perturbation experiment is essentially putting freshwater perturbations in the North Atlantic to mimic that. And then you can see that it's showing the atmospheric river-related precipitation. So there's clearly an increase in the atmospheric river-related precipitation associated with weakening in the North Atlantic. So this is actually rather good that CSM is able to capture this observed or proxy record. And similar teleconnections may influence future precipitation in western United States under potential AMOC weakening in the future. Another highlight that I wanted to include here is showing the impacts of volcanic eruptions on multi-year to decadal prediction skill. This effort was led by an ASP postdoc who is now at GFTL. What is shown here on the left side is anomaly correlation coefficients for annual mean surface air temperature, or SST, for 1 to 5 year, 6 to 10 year, and the decadal lead times. The top is for decadal prediction large ensemble. The middle panel is essentially using decadal prediction ensembles in which the volcanic forcing is not used from roughly mid-1950s all the way to 2015. And the bottom shows their difference. So you can clearly see that there's actually degradation of skill, prediction skill in the eastern and central tropical Pacific. And if you look at the surface temperature skill comparison at time series format for different lead years, you don't have to worry about it. The only thing that I wanted to highlight here is that blue is the full decadal prediction large ensemble with all the forcings, and the orange is the withholding the volcanic eruption information. You can see that if we withhold information for volcanic forcing, we actually see an increase in skill, which should not technically happen. So this is essentially indicating that there is an incorrect response to volcanic forcing in CESM, at least in CESM1. So we need to take a look at what's going on, essentially, interactions of the volcanoes. I think this is really important stuff that we need to pay attention to. And final thing that I wanted to show related to highlights is Wacom Group, and with chemistry, they incorporated a new sectional aerosol model called CARMA. It stands for Community Aerosol and Radiation Model for Atmospheres. In this example, they are comparing it against an existing model, MAM4, and for the Pinatubo eruption period, which is shown here, time here, and then this is showing the stratospheric aerosol optical depth. In this sort of integrated measure, blue is CARMA, pink is MAM4, and some observational distributions are given here. There's not much of a difference. However, if you look at actual particle volume size distributions that are shown on the left panels in two different events or cases, and the observations are balloon observations in the top with dots and aircraft observations with the black line here, you can clearly see that in this metric, Karma is actually doing a lot better in terms of capturing the particle distribution of aerosols. And this can have important impacts for geoengineering simulations. So with that, I would like to now switch to our efforts towards CSM3. Again, I wanted to make sure that we are not just targeting our, what I call, workhorse configuration. There are so many other efforts going towards CSM3. So I'll start with simpler models. Just to give you 2 examples, there's quite a bit of demand from our user community for simpler versions of CESM. So in this regard, SLIM, that's the Simple Land Interface model, has been implemented in CESM as its own component, and it'll be released soon. Gray Radiation Aquaplanet, simple model version, is almost ready to be released. Another effort that we have is graphical user interface and tools to support CESM, what we are calling as specialized and flexible model configurations. So this interface is intended to guide users through the process of creating CESM cases. An example is shown here, essentially with this interface. You click on these things and it checks for consistency and all that stuff. New metadata and logic module to check compatibility of the comp sets. That's all available. It's almost not quite released yet. It can create custom MOM6, that's the new ocean model, modular ocean model version 6 from GFDL. It can create custom grids and bathymetry. And it can also generate land model tools to facilitate creating, well, it has, or I should say, incorporates land model tools to facilitate creating surface data sets for custom grids and configurations for the land model. And we are aware of course, this is part of the strategic plan also, we are pursuing new technologies for CSM3 and future versions to advance science. And one application area, or one area is, of course, machine learning. And we intend to use and explore machine learning methods primarily for process understanding, parameterization development, parameter estimation, and improving prediction skills studies in strong collaboration with the community, universities and industrial-led projects. And the examples of these projects are listed here, down here: LEAP, M2 Lines, NVIDIA, as well as HPE SmartSim machine learning approaches. And there will be, you'll see examples of these things throughout the workshop as well. And one more thing that I wanted to add, as I said, MOM6 is our new ocean model. And we have actually, this thing should be running here. Okay, there's a simulation at quarter-degree resolution up there for sea surface speed. Just to give you an example that we have a hierarchy of grids available for MOM6. Our workhorse is 2/3 of a degree. Then we have quarter-degree, 1/12 of a degree, and 1/36 of a degree sort of resolution. The last two are especially the last one at this point, it's sort of created, but we haven't used it, if I'm not mistaken. And the idea here is to, with these hierarchy of grids, will allow us easy implementation of regional and out-of-the-box configurations of MOM6. Okay, so now the last part, I just wanted to touch base on where we are in terms of our workhorse configuration with CSM3. So back in December of 2021, there was an SSC decision, and the idea was to have an initial goal to perform preliminary evaluations of the coupled simulations with a new CESM configuration that uses our targeted component models, MOM6, CI6, and CAP6, and with the spectral element and 58 level version. Actually, we are targeting 93 level version, but this was sort of a cheaper version. They incorporate numerous new developments and features in each component. And to date, we have performed more than 50 decadal, multi-decadal scale, and centennial scale simulations. And these runs have been extremely helpful for us to identify and resolve various scientific and technical issues, such as enthalpy non-conservation, because we have a now mass-conserving model rather than volume-conserving, salt non-conservation issues, and a bunch of other errors that were identified and fixed. And this has been sort of our development timeline. Unfortunately, that green color is not coming out well. The timeline is shown in the bottom. It's not to scale. We had sort of initially individual component models doing their own thing, incorporating developments in standalone or fully coupled configurations. Then we brought everything together back in about a year ago. We performed a bunch of, as I said, coupled evaluation and development studies, tuning, bug fixes. We took a break in fall 2022, and then each component model went back to their drawing table, added more features, and tried to address some of the challenges that we encountered. And we are right now here bringing all the developments together again. And our target is sort of fall of 2024 to create a workhorse version of CESM3. It is not the final version. There will be additional developments going in, but it is a starting point that we can use for several purposes. And this is just our internal sort of table of experiments and how long they have run. Unfortunately, our old nemesis is back. In other words, this is showing as a function of integration time, the Labrador Sea ice annual sea ice area. You can see that we are back to Labrador Sea freeze. And this comes together with weakening of AMOC. And you can see that AMOC is going down. And this is also associated with pretty much no deep water formation happening in the North Atlantic. So that was the situation back in the fall of 2022. We took a break, as I said. We incorporated a bunch of other changes, and we are in the process of redoing these. Okay, some of you may ask, well, how is it this timeline is consistent, or does it jive with CMIP timeline? This is a draft CMIP 7 timeline. This may not necessarily be the latest version from the CMIP office, but it's close. So this is their estimate of what they think the timeline is going to be based on, again, a guesstimate of IPCC working group timeline. And these boxes actually are intended to indicate the fuzziness of the timelines. So if you go back and look at the timelines, essentially go backwards in terms of creation of forcing, if you want to essentially provide these experiments in time for IPCC report, thinking that it will take about 1 to 2 years to do these experiments, the simulations need to start pretty much summer, fall of next year. So CSM timeline is consistent with that. Okay, and finally, I wanted to advertise 2 sessions here in my final 2 slides. We are going to have 2 sort of newer sessions tomorrow afternoon, starting at 5:30. One is a celebration of partnership. This is assessing responses and impacts of solar climate intervention on the Earth system. I wanted to also close the loop when I said define the community up front. So this is a great example of essentially what we really mean by community. You can see that it involves so many, Silver Lining NGO, NCAR folks are not actually included in this case, but this is one of the efforts that Yaga has been sort of leading at NCAR, AWS, and university community, including Colorado State. Jim is here. So this is a great example of what we say, what we do when we say we collaborate with community. So there's going to be a reception starting at 6:30, and everybody is invited for our second reception of the workshop. And then in parallel with that, we'll have another special session, the use of CESM in climate services and climate technology. And these are the 4 speakers from Jupiter, Earthshot, McKinsey & Company, and NVIDIA. And I don't put names, and you may recognize some of the faces in that. So please join us again tomorrow afternoon at 5:30. We'll hear 4 perspectives of how the need for information on climate risk and climate solutions is driving a new user-based or user-inspired problems for CESM model and its data sets. And with that, I'll take questions. Thank you again for your time. Okay. we are slightly behind time, so we can proceed then. Okay, so now it's this is the great, no, go back to the presentation, please. So this is the great part of this job, and I'll be doing it for the last time. And I would like to now announce the recipients of the CESM 2023 CESM Distinguished Achievement Award recipients. And they are Julio Bachmeister and Peter Lauritsen from ENCA. So you guys can come over here. You should have noticed because Julio is dressed up. You don't see Julio in that way. So they were nominated jointly for their exceptional contributions to the understanding of dynamical processes in CSM atmosphere models. And together, Peter and Julio have delivered a streamlined and scale-consistent orography generation software, generalizable to multiple dynamical cores and horizontal resolutions. In addition to managing these important model development efforts, they have each generously offered their time to mentor and advise students, visitors, and postdocs, as well as other members of the research community. In summary, their individual and joint contributions have elevated the rigor of the representation of dynamical processes in CAM, and in doing so, delivered atmospheric models that have greater credibility in applications used across the CSM community. The actual nomination is like almost 2 pages. I'm just reading you a few sentences here. So thank you again. And I have these for you guys. These are really heavy. So I don't know how to do this, but you should go take a picture. Yeah, that's right. Okay. So you guys can hold it like that. So as you all know, as a punishment now, they have to give a talk, and we'll hear their presentation here. These are you can put these later, empty boxes. Pizza boxes, yes. This. So now we can switch to the other presentation. I don't know who's going first.
I'm going first here. All righty, well, thank you. So Julio and I are atmospheric model developers, and the first thing we said to each other when GoCon scheduled a meeting to tell us that we won this award was this award should really go to all of the CAM development community, which is a huge community of very talented and energetic software engineers, and scientists that work very close together to develop the model CAM. Also, model development is expensive. We believe it's very important that we have solid base funding to develop a model, but we also got a ton of extra money from NSF to really push things forward, as well as from the director's office at ENCA. Here's a CAM7, Simpler Models funding, CPTs, CEMA funding, and the PBL reinvestment funding. So our title of our talk is a little provocative. It is lower or resolution climate modeling dead? Why are we asking that question? Well, for quite a while, I would say decades, there has been the idea floated around that we should stop just incrementally increase the complexity of our model, increase the resolution very slowly in the case of CAM. We should just leapfrog to 3 kilometers to convection permitting scales. That would be, the way to make really rapid progress of reducing our biases in terms of climate projections. So that leads to the question, should we just get rid of our 100-kilometer model? So as a model developer, I dip my toes in different communities. And I often walk away with this mental image here. So I walk away with the image of a cat, which you see on the right-hand side there, which is the 3-kilometer global model cat. And then on the left-hand side here, you have the 100-kilometer scale climate model dog. And the cat points its finger at the dog and says, your model can't simulate a squall line or the details of a hurricane, so it is useless to me. The climate model dog then points the finger at the cat and says, well, your model can only be run for a couple of days, so it's completely useless to me. I can hear the suspension in the room here. My gosh. Okay. It's never a good idea to point fingers if you want to have a conversation. So let's mentally have these paws, not fingers, paws, come down. And let's let the climate model dog talk, which is in the form of Julio. There we go.
Well, I won't bark. But I also don't know how to run this presentation. So. This? Okay. Can I go back or just, all right, great. Good. So I have opposable thumbs. So, as the climate model dog, I think we decided that there are maybe two missions, broadly speaking, that CESM serves. I'm going to focus on the second. How is this? Oh, there we go. I'm going to focus on the second, providing state-of-the-art climate information to stakeholders. And we're going to argue that even for this purpose, you really do need a lower resolution model, as we've been talking about before. So what do we need to provide projections of climate change to stakeholders? We need, a well-tuned climate model with an accurate representation of the mean climate state. You can't really make very sensible statements about extremes unless you get the means first. As Gökhan already alluded to in his talk, the process of tuning can be very costly. So I'm just going to leave that with that statement here, but you can easily imagine from what Gökhan said that the number of years required to tune a climate model can run into the multiple thousands of simulation years. What I am going to focus on for the rest of this climate dog talk, until I hand it back off to Peter, are these the second and third points. I really want to take a few minutes to talk about how we can use lower resolution models in combination with higher resolution models to start to identify the impact of uncertainties in climate projection that arise from the simple fact that there's variability in the coupled system. Here are estimates of how many years of simulation we might need to characterize this variability. This is derived, basing this on large ensembles. Really great idea. I think a great contribution to the community, spearheaded by Jen Kay, Clara, Isla, Gökhan, and others. So from these large ensembles, I think we can say that we're going to need well over 10,000 years of simulation to really characterize variability. So I'm going to show one sample problem. This isn't necessarily, it's certainly not the only example of how projections will depend on variability. It's only one that I'm familiar with. I'm going to discuss, show an example of TC projections for the end of the 21st century, using lens to try to bracket some of the uncertainties. For more background, you can look at this older paper, and I want to thank, I want to really call out Nan Rosenblum and Susan Bates for doing the initial runs for these simulations, and also making sure that these results are still available and usable by the community, including me. So Gökhan sort of set the stage already for the quarter-degree simulations. This is a version of the model, CSM1. It's closely related to the IHESP model version that Gokhan talked about. But I'm sure all the results that I'll discuss on this slide are results derived from forced SST. So we don't do fully coupled simulations to make these simulations. To begin with, this is the workflow that I want to illustrate here. This shows quarter degree simulations sort of summarized by the accumulated cyclone energy. This is a measure of the kinetic energy density, so to speak, associated with tropical cyclones. It sort of encapsulates both frequency and intensity, so it's a nice sort of simple measure to kind of quantify tropical cyclones. It's normally calculated per basin, and we see, this plot, this bar graph shows ACE, accumulated cyclone energy, in the North Atlantic, Northwest Pacific, et cetera, different basins. And what you see here is, that the model at quarter degree does a reasonable job, I'd say. It's not perfect by any means, but it does a reasonable job of capturing the rough climatology of tropical cyclones in the present day. So the next step is to go to the lens and pick some ensemble members to force the model in the future. And the ensemble members for this study were picked, I'd say, in a fairly arbitrary way. I think that's one thing that we might want to revisit at some point. We picked 5 ensemble members from the lens, and also the mean, and also picked a RCP 8.5 simulation from CMIP5 using CSM1. So we have 7 SSTs. We bias correct the SSTs and use those to force the model in sort of AMIP style in the future. So everything is based on RCP 8.5 forcings, but we have different SSTs under the model to try to see what impacts that has on our tropical cyclone projections. And this is the result. The bluish grayish bars are the present day simulations, and the orange scale is the bar charts for the 7 SSTs that we've picked from the lens in the 3 decades at the end of the 21st century. And what you see, I don't want to dwell too much on this, but the point here is that the spread in SST, the variability in SST has a big impact on what you project for different basins in the future. You can see there are some cases, for example, the Northwest Pacific here, where, depending on what SST you use, you project both an increase or a decrease in tropical cyclones. And just to, emphasize, these are 30-year means, so ENSO variability is probably not the cause of these differences. All right, then the next question is high resolution, and here I'm using Gokhan's definition of high resolution, 25 kilometers. Is the climate of these models better? So I'm going to show one example. This is 25 kilometer precipitation from CSM1 here at the top. Down here is the 1 degree simulation. Here are GPCP observational estimates of precipitation. So the point is that the ITCZ biases and doubling appear actually to intensify in this 25 kilometer configuration. Now, in interest of full disclosure, this intensification in CSM is tunable. If we increase the activity of the convection scheme, this precipitation begins to look more like the precipitation in the 1-degree model. But what we've learned in CAM is that when we do this, that nearly, when we increase the activity of the Zhang-McFarland scheme in this configuration, it nearly eliminates tropical cyclone activity. So that's puts us in sort of a difficult position. We can get the interesting mesoscale stuff or the climatology right. But it doesn't look like we figured out how to do both at the same time yet. All right, so the question, Peter and I are asking, is 3 kilometers a breakthrough? And I'm going to say right now, we don't have, I think, enough information yet to say whether 3 kilometer is a breakthrough resolution. You might expect that, since you're not parameterizing convection anymore, you may not be parameterizing partial cloud cover. There's less, there are less places that you need to tune. So that could be, it could be significant. I don't think we have enough yet to tell us whether that's true. There will be a talk this afternoon on extended simulations using a 3 kilometer model. So that will be, it'll be interesting to hear what Lucas Harris has to say. But anyway, I'll just leave that at this for now. And then the next bullet that I want to talk about a little bit is, 1-degree model is not especially useful in many contexts for stakeholders. So how do we get from, the 1-degree results to higher resolution results? And the answer, it's nothing new. Downscaling. Downscaling really works. I'm going to show 2 examples and then hand it back to Peter. The first example is this nice video from Andreas Prine in M-Cubed. It's, these simulations were conducted as part of the South America Affinity Group, and WRF is here on the right. Well, I guess that's the right. And satellite observations of precip and cloudiness are on the left. This is a WRF 4-kilometer run, and the basic point here is that this model, which is being forced by ERA reanalysis around the edges, no nudging or anything inside, it's still doing a remarkable job if you look at the individual cloud features of capturing weather scale variability. So downscaling works if the boundary data is good. Adam will discuss this a little bit. This is it's an interesting view of the regionally refined grid over the Arctic. There's Greenland. And Adam has shown that when you refine, and I think Gökhan mentioned this too, when you refine over the ice sheet, you get a better simulation of hydrological processes that are important to the surface mass balance of the ice sheet. There's a video that I won't have time to show here, but maybe this presentation will be available and the video will be clickable from there. Okay, so I think that's it for me. I'll just stop my part here with these recommendations, and I was happy to see that recommendation 2 is apparently already sort of underway. That is, I think we need to begin to assess whether the variability we see in the coupled system is resolution dependent or not. So with that, I think I'll just close and let Peter take up the model dog.
Okay, so I hope Julio has convinced you that we shouldn't let the cat kill the dog quite yet. So we'd like to air some thoughts about where we think we should be going in the future from a model developer's perspective to meet the scientific goals. Before I do that, I would like to highlight a slide here. This was from a symposium at AMS last year on Earth prediction, innovation, and community modeling. where Peter Nealon from the weather company was present, and he was giving his advice on moving forward. And he said, can we avoid dynamical core component organized communities? And also, is a community supermodel with multiple dynamical cores possible? Unfortunately, nobody there mentioned that CSM has that capability. But he also mentioned, be really careful with narrow motives. Avoid this my model for my use motive. And I think CSM is in a good space there because we have this community governance. It's kind of the checks and balances to make sure we meet the science needs of the community. So what the model dog would like in the future is a very flexible modeling system where we can do global low and high resolution simulations all the way from hundreds of kilometers to the kilometer scale in the same system. And then easily configurable downscaling, let it be traditional nesting or mesh refinement. And then also LES capability where we regionally can run at very, very high resolution, in particular for parameterization development. All of this exists in its own community somewhere. But what I'm talking about here is actually being able to do this in one system. And then along with this comes all the workflows and diagnostics, which is a similar can of worms. This sounds really easy when I just say it like that, even banal. But anybody who has tried to set up a new resolution or trying to run a new model, doing something new in a modeling system would know what I'm talking about. Like first you need to define, say you want to run a new resolution in CSM, you need to define a new grid. If it's variable resolution, that's not straightforward, so you need some kind of community tool to do that, or help from inside. You need input data sets, you need topographies, you need to check out some software to do that, figuring out how it works, and get those files, and then you need to create initial conditions, and I think most systems do not have dynamical core agnostic methods for doing that, so everybody has their own little tailored procedure to do that. Then there's a question what physics you have to use. It depends on where your model top is, what resolution you're running, etc. And then we also know there's always known unknowns. There's always stuff pops up that we might have seen before that you have to deal with. And if you're really lucky, you'll get unknown unknowns of stuff out of the blue breaking when you're setting up this new run. And then once you finally get your model running, then you have diagnostics. Which I won't go into, but there's a lot to discuss with respect to that. So I would like to mention that CSM and also CIMA has stuff going on that's trying to address some of these issues, and we have addressed some of them already. But I'm talking about doing all of this stuff, across scales. It's a very, very ambitious target. Another thing the model dog would like to bring up is, let's not forget about first principle. Let's not forget about what we actually know about our systems from basic physics, because we are making quite a few assumptions in our global modeling system. So in particular in CSM, we're moving towards a true multi-phase component fluid formulation in the atmosphere. We're starting to look at thermodynamic and energetic consistency in physics packages. If you start to look at the different assumptions, there can easily be inconsistencies between parameterizations and between the parameterizations and the host model. And then we also know there's a bunch of missing processes, the stuff we do not have in the model that may or may not be important, but I think some of these will become pretty important at high resolution when we start to look at particular phenomena, such as do we include the heat content of rain and evaporation. I can refer to that as enthalpy flux, as frictional heating of falling precipitation. Could be a big term in the tropics, drag of falling precipitation, etc. So if you're interested in this, we have a very big paper here. Again, not just me, it's a huge group of international researchers that put together a paper from this first principle view of Earth system models. The other wish list that we have here is we would like to move away from column-based physics. Our parameterization currently only operates in the column. So you give it the state in the column, and it does its thing based on whatever assumptions are in the parameterizations, whatever we're trying to represent. But it can only do things up and down, not to the sides. But we think there's several things in our models that would need that. I'm just going to highlight one of them, which is gravity waves. So this shows temperature perturbations from observations on the left and from a 3-kilometer wharf simulations on your right here. And these are phenomena triggered by topography. But as you will notice here is that the effects of these span several grid cells. Even if you go to the 1 degree box, which is the yellow box there, you will see that these subgrid scale waves for the 100-kilometer box actually are felt far away from that box. So even at 1 degree, we argue that you should actually have communication between columns because the gravity waves propagate out in a cone, not in a vertical column. And you can make similar arguments for moving to 3D radiation, for example, or training your AI algorithms. You might need lateral communication for that as well. So to conclude, let's go back to the cat and the dog here. So what we're proposing is that we should clone these two. I think it would look something like this. So we should create a dog-cat because I think we have huge synergies that we can exploit if we work in a unified system, respect each other, communicate with each other, learn from each other, and move forward in that way. And I'll leave it up to you to think about what this thing should be called. We propose it could be called a DAT, or DOT, or whatever you think it should be called. Anyway, with that, we'll take questions.
Questions for Julio or Peter? Yes, Simon. There's a microphone right there in the...
I just want to make a comment that we have a cross-working group session this afternoon on ultra-high regional refined and area limited resolution. I just wanted to point people to that as well because we'll continue the discussion. Thanks so much for the talk.
Thank you. Thank you. Any other comments or questions? Okay, well, thank you guys and congratulations again. So you get the pizza too. Okay, could you put my presentation again? Okay, so, and this is another exciting part of the job. And our 2023 CESM Graduate Student Award or recipient goes to Claire Zarakas from University of Washington. Congratulations. So I just wanted to... Claire is a PhD student. She's expected to graduate in 2024 in atmospheric sciences at the University of Washington, working with Professor Abby Swan. Her body of work has made significant contributions to the CESM project throughout her dissertation. Specifically, 2 projects stand out for the depth of understanding and important model developments they afford the broader CESM community. These projects include her work on coupled land-atmosphere perturbed parameter ensemble, that's PPE, experiment, and the development efforts with the functional assembled terrestrial ecosystem simulator, that's FATES. Beyond these activities, Claire provides high engagement with activities in the land model working group. For example, she provides input, testing, and feedback on the collaboration between NCAR and the National Ecological Observatory Network, that's NEON. She continues to engage with the FATES development team and participates in ongoing PPE discussions and the application of these tools in CTSM and CESM. She is thoughtful, creative, innovative, diligent, and collaborative for the broader good. In short, Claire embodies all the attributes of excellent CESM contributors, and we look forward to her or your future contributions. So again, thank you and congratulations. So as I said, as a punishment, she's going to give a plenary talk. So, and I should actually present you with the award first. Oh, thank you. Yeah, I don't know what, yeah. You have the signed version. So I'll leave it here for you. So, okay. You can move to the other one. Thank you. That's good.
Well, I'll start by saying thank you very much for this recognition. And I also want to start by thanking the CLM and BGC working groups. This has been a really valuable community to be a part of in graduate school. So thank you very much for your support in all these projects. So today I'll be talking about how land parameter uncertainty impacts the mean climate state. And this project is motivated by the fact that modern land models are really complicated. So climate scientists have represented land in models for a really long time, even looking at early modeling papers like Manabe in 1969. That paper had land in it. It was just really simple land, so things like albedo were prescribed. And since then, we've added a lot more processes to our land models, so things like snow model resistance, improved complexity of hydrology, biogeochemical cycling. So this has been really valuable because these are all real processes, so by including them in models, we can better represent how the land works and how it responds to change. But the flip side of this improved process representation is that our models now have more and more equations and parameters for those equations. So this is showing the number of equations in the community land model going up to CLM 4.5. And in the current version, CLM 5, we have over 200 parameters, and many of them are poorly constrained by observations. So land parameter uncertainty is a really major driver of uncertainty in land fluxes. And now those land surface properties like albedo and evaporative resistance that were previously prescribed are now emergent properties that depend on all of these interacting processes and lots of poorly constrained parameters. So we know that land parameters are uncertain. We also know that changing land surface properties can generate really significant climate responses. Just as an example of this, this is showing temperature responses to changing the evaporative resistance of the land surface. So each of these statements in isolation are well supported by tons of research. They may seem pretty obvious. Land parameters are uncertain, and changing the land surface can influence climate. But there hasn't been much kind of dialogue between these two perspectives. So it's common to think about land parameter uncertainty from a land perspective. So thinking about how land uncertainty influences terrestrial processes. And I'm interested in looking at land parameter uncertainty in a coupled context, so thinking about how land processes can influence the atmosphere. So specifically, I'm going to talk through two research questions today. The first is, to what extent can land parameters influence climate? And I'm going to focus on the biophysical impacts of land rather than carbon cycle implications. And then secondly, how do atmospheric feedbacks modulate land parameters' impact on terrestrial processes? So starting with this first question, land parameters can really only impact the atmosphere by altering land to atmosphere fluxes of energy, water, and momentum. So for energy, land can directly influence outgoing shortwave and longwave energy and the partitioning between sensible and latent heat fluxes. So to quantify how land parameter uncertainty impacts climate, I ran a coupled parameter perturbation ensemble, or PPE, that leveraged output from a community project, the CLM5 PPE. So this was led by Daniel Kennedy, Katie Dagan, Dave Lawrence, Lydia Hawkins, many others, and they ran a land-only uncoupled ensemble of one-at-a-time simulations for all the parameters in CLM5. So it was a pretty massive effort, and because that data set existed, I used it to select 18 land parameters that generated the largest impact on these land-to-atmosphere fluxes of water, energy, and momentum. And I also tried to sample different functional areas of the model. I ran one-at-a-time simulations for these 18 land parameters where I perturbed each parameter to observationally informed minimum and maximum values. And so this kind of combines the effect of how uncertain a parameter is as well as how sensitive the model is to that parameter. And for each ensemble member, I ran coupled pre-industrial equilibrium simulations for 140 years in CESM2 using CAM6, CLM5, and a slab ocean. And we found that changing land parameters can really influence the mean climate state. So at some latitudes, the mean change in land temperature ranged by up to about 3 degrees. And averaged over all land globally, we had a 2.2 degree spread in global mean land temperature. If we include ocean in our average for the total global mean temperature, this is about a 1 degree spread in global mean temperature, which is over a third of the spread we see in CMIP5 and CMIP6 pre-industrial mean climate, but just by perturbing land parameters in CESM. Soil hydrology parameters drove the largest spread in land mean temperature and global mean temperature, followed by parameters related to stomatal conductance and plant water use. So if we look across this whole parameter space, soil hydrology and plant water use and stomatal conductance drove the largest changes. Other abiotic parameters related to snow and roughness or the boundary layer drove pretty small changes in global mean temperature, but there were quite a few plant-related parameters that all drove over a 0.5 degree temperature change in the land surface. So these are parameters related to photosynthesis, canopy evaporation, plant radiative properties, temperature acclimation, that one was kind of smaller, and biomass heat storage. And even though these parameters are all kind of touching really different processes in the model, we found that land parameter uncertainty drove a really consistent pattern of temperature change. So this is the leading EUF of mean temperature changes across our ensemble, and it explains almost 80% of the variance across our ensemble. So when I initially saw that high percentage of variance explained, I thought that maybe land temperature changes were just kicking off kind of classic radiative feedbacks, and that's why we see this consistent pattern. But if we compare the pattern of temperature variance across our ensemble to, say, the pattern of radiatively driven warming in the same model configuration, this is also scaled to 1 degree mean for comparison, we see that they're pretty different spatial patterns. So in particular, our pattern of change in our land PPE has this real hotspot of climate sensitivity to parameter choice in the North American Great Plains, and also in like Central Asia, Eastern Europe, and there's more of a hemispheric asymmetry in our spatial pattern as well. So land parameter uncertainty significantly influences the mean climate state, and we have to think about these land-driven temperature sensitivities as kind of activating different mechanisms than we think of as being important for radiatively driven climate changes. So this kind of begs the question of why do we see this high sensitivity of the mean climate state to land parameters? There are really just 3 kind of contenders for mechanisms. So parameters can influence temperature by altering evaporative resistance of the land surface, albedo, or aerodynamic resistance. And these are all emergent properties of the land model. So by having these 36 ensemble members, we're really creating 36 combinations of these 3 different properties. We've tried a bunch of different ways of disentangling these different properties, and they all kind of qualitatively give us the same answer, which is that evaporative resistance explains most of the spread in temperature across our ensemble, with albedo playing a secondary role, and at least when looking at global scale changes, aerodynamic resistance isn't as important for the parameters we selected. I wanted to briefly touch on precipitation as well, though I won't focus on it today, because we're finding that precipitation is also really sensitive to land parameters. And one of the neat things about our experimental design is that we ran our simulations for quite a long time, so we can get pretty good stats on how precipitation is influenced by land parameter choice. And we found that some of these kind of climatological hotspots of places where precipitation is really sensitive to land parameter choice. It aligns with these more traditional metrics of land-atmosphere coupling and hotspots that emerge from that kind of body of literature. In particular, the North American Great Plains, again, emerges as a consistent hotspot where land parameter choice really matters for your kind of precipitation climatology. And this is just showing the percent change in June, July, August precipitation across our ensemble. So land parameters' influence on evapotranspiration is a really important mechanism through which land parameters can influence the mean climate state. So I showed that land parameters can influence mean climate. We know that terrestrial processes relating to the water and carbon cycles are really sensitive to climate. That's why we study these things, for many of us anyway. So next I quantified how atmospheric feedbacks modulate land parameters' impact on terrestrial processes. And to do this, I ran a parallel offline PPE where I made the exact same parameter perturbations, but this time I held the atmospheric state fixed with the default configuration at 3-hour time frequency. So by comparing a coupled simulation with the corresponding offline simulation, I can isolate the impact of atmospheric feedbacks on the total response. And we found that for the water cycle, on global scales, atmospheric feedbacks generally dampen parameters' impact on hydrologic metrics. So here I'm showing runoff. The x-axis is the offline change in runoff, where each dot is a different ensemble member, and the y-axis is the coupled change. And so these points all deviate from this one-to-one line, which means that atmospheric feedbacks matter. They change the answer. And the fact that they deviate consistently so as to have a smaller change in runoff in the coupled case than in the offline case means that there's this kind of consistent dampening effect when we're aggregating up to the global scale. But this does vary spatially. So this is showing kind of grid cell by grid cell the extent to which atmospheric feedbacks dampen parameters' influence on evapotranspiration now in blue versus amplify it in red. And you can see there's kind of it varies based on your baseline moisture regime. So in wetter places, you have this kind of dampening pattern, while in more arid regions, atmospheric feedbacks have an amplifying effect. And we hypothesize that this is because kind of two different mechanisms are more important depending on whether your evapotranspiration is demand limited or supply limited. So in a wet regime, if you increase evapotranspiration, that cools and moistens the boundary layer, which lowers VPD, and so that'll dampen the initial evapotranspiration change. While if you're in a dry regime, if you're in a place with strong land-atmosphere coupling, an increase in evapotranspiration may increase precipitation, increasing soil moisture, and because you're supply limited, that could amplify your initial evapotranspiration change. So atmospheric feedbacks dampen water cycle responses globally because most evapotranspiration and runoff happens in places where it's wet, but regionally it depends on your mean climate state and your baseline moisture regime. The story is a little bit different for the carbon cycle. So here we found that atmospheric feedbacks aren't as important on the global scale. So I want to highlight that there's a really large spread in, this is showing gross primary productivity, or GPP, across our ensemble. So land parameter choice matters a huge amount for the carbon cycle. But if we're focusing on the relative contribution of atmospheric feedbacks, these points are pretty close to this one-to-one line. So while land parameter uncertainty matters a lot for the carbon cycle, atmospheric feedbacks don't change the answer quite as much. There are some regions where atmospheric feedbacks matter more for the carbon cycle though. So this is showing the leading EOF of differences in mean GPP between a coupled simulation and the corresponding offline simulation. So again, the North American Great Plains pop up as a hotspot where atmospheric feedbacks matter for the carbon cycle, but the Amazon also pops up as being pretty significant. So we have to think about atmospheric feedbacks when considering the carbon cycle in these two regions. So in summary, land parameter uncertainty significantly influences the mean climate state. Changes in evapotranspiration explain most of the spread in mean climate across our ensemble, and atmospheric feedbacks are globally important for water cycle metrics and regionally important for the carbon cycle. So there are a few implications for this. So first, I think it means we really need to account for land parameter contributions to uncertainty and biases in model representations of present-day climate. So I think this is pretty well established when you're thinking about kind of local scale to regional scale processes, but we're showing that land parameter uncertainty can really drive uncertainty and biases at a global scale for the mean climate state. I think this also has implications for land parameters which aren't stationary in time. So in particular, a lot of the plant parameters I showed could vary depending on climate. So if there are climate-driven shifts in plant traits, that could generate further climate feedbacks, and we kind of indicate what those atmospheric responses might look like. And then the second part of my talk, I think, emphasizes that we really need to be developing and evaluating and benchmarking our land models and components of CESM more broadly in this coupled context. I think it might not work to calibrate and validate our models in isolation, but then deploy them when they're all coupled to each other if that coupling might meaningfully change the answer. So before taking questions, I wanted to thank the CLM and BGC working groups again for their support throughout graduate school and for this award, and also acknowledge all my collaborators on this project and many other collaborators and supporters more broadly. So thanks very much.
Thank you very much. Any questions for Peter?
Model group make the final choices on the parameters to use in the model. Do they ask you, or does Dave Lawrence make some arbitrary decisions?
I mean, I'm not sure I'm the best person to speak to that, honestly, but I think that's something that's really progressing really rapidly. So this CLM PPE project that I mentioned, which has been like this massive undertaking by folks at NCAR, I think is really changing how parameter calibration happens, and I think will lead to like more systematic calibration efforts. And I think we're still kind of working on how we can combine that with the fact that we know that coupling to the atmosphere can change the answer to some extent. Like maybe we could have some kind of offset factors, and some of the relationships look kind of linear on the global scale. But yeah, still working on that. Thanks for the question.
Yes.
Curious if you've thought about why, if in certain regions the coupled model is affecting ET, why the ET is not affecting GPP in those regions.
Yeah, I have been thinking about that. It's something I'm still working on, but I think a lot of the ET changes are actually driven more by like non-plant processes. So like when I had that big offset, that was mostly driven by changes in soil evaporation or canopy evaporation rather than plant transpiration. I was still surprised to see that there wasn't more of an influence of atmospheric feedbacks on GPP, since plants care a lot about water, and changing the water cycle should influence how much water plants have available to them. But I guess there's just so much uncertainty in the land parameters for the carbon cycle that land parameter uncertainty just kind of outweighed the influence of the change in plant water status. But it's a great question. Thank you.
One more last question. Yeah, go ahead, Peter.
Thanks, Claire. Great talk. I'm wondering about, land use, land cover change, like impacts, and these large uncertainties in the parameters, what it means, because we use the models a lot to determine larger scale climate responses. Do you have any idea of like how that could guide our understanding of land use and land cover change in the larger climate system?
Yeah, I mean, I hypothesize, though my experimental design was unfortunately not super well suited to answer this question, but I think that land parameters could definitely influence the kind of temperature signal of land cover change and potentially even affect the sign. Like I know there's tons of variation across the CMIT models, and I hypothesize that we could mimic that spread just by changing land parameters within a single model. But I think it'd be really cool to do some more like transient historical simulations where we could look at a lot of different questions, and I think that would be better suited to looking at how land parameter uncertainty influences the like biophysical effects of land cover change. Yeah.
Thanks very much.
Well, thank you very much. Let's thank you one more time, and congratulations again. Congratulations. So we'll take a break till 10:30, if I'm not mistaken, and we'll come back with, we are trying a different format this year. It'll be a panel sort of plenary. And so 10:30, please.
Good morning, everyone. So we're going to do something that's a little bit different for a CESM workshop. So we're actually going to have a panel. There's going to be no slides. It's going to be more of a conversation. And so this is about the Rising Voices Changing Coast Hub. And I'm actually going to hand it over to Julie Maldonado, who's online, to introduce the panel and moderate. So Julie, take it away.
Thanks, Rika. Apologize for any hacking or anything on my end, trying to get healthy here for y'all. Thank you for also going out on a limb and going a little different style for us. I hope even in this hybrid space, we can engage together in a good way here. So just really grateful for everyone for the invitation here and excited to be joining for this session that's focused on the Rising Voices Changing Coasts National Indigenous and Earth Sciences Convergence Hub. So I'm Julie Maldonado. I serve as the Associate Director of the Livelihoods Knowledge Exchange Network, or LICAN, which is a nonprofit think tank for policy-relevant research toward post-carbon livelihoods and communities. And in this capacity, I also serve as the co-director of the Rising Voices Center for Indigenous Earth Sciences. I also serve as the co-director of the Rising Voices Center for Indigenous Earth Sciences, housed out of NCAR. And then specifically for the Rising Voices Changing Coast Hub project, which we might refer to as RVCC for short, I'm working on the project management and social science components. And so I'm going to provide just a real quick, brief 30,000 foot level background for the RVCC Hub project, and then give brief introductions to our amazing panelists here, and away we will go into our conversation. And so just so folks know are on the same page here is when we're talking about the Rising Voices Changing Coast Hub, this is a project led by the Haskell Foundation, which serves Haskell Indian Nation University out of Lawrence, Kansas. And this 5-year, $20 million grant from the National Science Foundation's Coastlines and People Hubs for Research and Broadening Participation, or as many of you might know it as the COPE program. This is the largest NSF-funded research award in tribal college and university history. The project focuses on coastal change occurring in Hawaii, in Puerto Rico, Louisiana, and Alaska, and as part of the project is using CESM along with other tools and approaches to address questions of changing coastal inundation, coastal storms, and marine ecosystems, among other topics. And so the goals of the hub are really fourfold. So we're working to develop a successful cross-cultural research framework that can be adapted by future research collaborations. We're working to improve Earth system modeling and prediction of coastal processes to provide highly usable and appropriate and culturally relevant information for communities. We're working to broaden participation and support leadership of Indigenous students and researchers in Earth system science. And fourth, we're working to strengthen infrastructure for future collaborations between academic institutions and Indigenous communities. And so the hub is founded on partnerships that have been built for well over a decade, most recently in the past decade through the Rising Voices Center for Indigenous Earth Sciences, through work of the Indigenous Peoples Climate Change Working Group, and through the decades prior to that and all those who came before to make these happenings possible today. And at the heart of these partnerships, we have really worked to build relationships of trust, of respect, of reciprocity among Indigenous knowledge holders, Indigenous science, other Earth system scientists at NCAR and well beyond the walls and boundaries of NCAR itself. And so this leads us really into today's session where we're focusing on the RVCC, the Rising Voices Changing Coast Hub project, and specifically talking here about co-creating knowledge through Indigenous and Earth Sciences collaboration. And so we'd like to share with you all, with the CESM community, really about how the project and its unique aspects of weaving together Indigenous knowledges and science, Western science, and communities' priorities and needs really to inform scientific efforts and to provide some information on how CESM is being used within the project and the context of our work. And so with us today, we have Dr. Daniel Wildcat, who is up on your screen. He is a professor at Haskell Indian Nations University in Lawrence, Kansas, and an accomplished scholar who writes on Indigenous knowledge, technology, environment, and education. A Yuki member of the Muskogee Nation of Oklahoma, Dr. Wildcat formed the Indigenous Peoples Climate Change Working Group, a tribal college center network of individuals and organizations working on climate change issues. And Dr. Wildcat serves as the principal investigator for the RVCC Hub project. And we have with us also on your screen, Suzanne Van Kooten, who is a citizen of the Chickasaw Nation. She is the National Weather Service leader of the Advancing Sustained Collaboration and Engagement with Native Tribes, otherwise lovely known as ASCENT program. Suzanne is a co-lead for the project's Storms and Weather Working Group and provides tremendous support for the Louisiana region and across the hub. Diamond Takira is also on your screen. Give a little hello. Is Native Hawaiian born and raised on Oahu. She's currently an NCAR ASP or Advanced Study Program postdoc, working with the Research Applications Laboratory and the M-Cube, the Mesoscale and Microscale Meteorology Laboratory. Diamond's also the co-director for the University of Hawaii at Manoa's Mentoring Bridge program. And so for the hub, she's currently co-leading the Ecosystems Working Group and part of the Hawaii regional team. We have with us now, turning to the room, so you can see up front here, we have Kristen Krumhart, who's a scientist in the oceanography section of the Climate and Global Dynamics Lab at NCAR. Kristen works on modeling biology in the ocean, specifically phytoplankton and zooplankton dynamics. I highly encourage, if you have not seen her amazing artwork of what she does, I hope Kristen will at some point in your time there share that with you. And Kristen contributes to development of the ocean ecosystem model in the CESM, the Community Earth System Model. And so for the Hub project, Kristen is the co-lead for the Observations and Modeling Working Group and part of the Ecosystems Working Group and supporting across the regions as well. And also next to Kristen in the room, we have Carlos Martinez, who is another ASP Advanced Study Program postdoc fellow in the Climate Analytics section in the CGD, or Climate and Global Dynamics Laboratory at NCAR. Carlos works on climate dynamics, variability, and change, specifically on the Caribbean and Central American hydroclimate, utilizing CESM and other CMIP6 models. He's working with, for the project, he's working specifically with the Puerto Rico and Louisiana regional teams on leveraging NCAR tools and resources to address coastal issues such as precipitation, flooding, tropical systems across the Caribbean and Gulf of Mexico regions. And so what we'd like to do for you, this is a little out of our ordinary because normally we would take a good most of this time for everyone on this panel to introduce themselves appropriately. We do understand we have 60 minutes for this. So we are rolling with this way, but I do encourage you to be following up with folks on here and learn a lot more about the amazing folks we have gathered today. And so what we're going to do, we're going to go through a round of questions here. I'm going to ask, one of the panelists to, take kind of a lead on and then see if anyone else would like to respond as well. And so this first question we have, I'd like to pose to you, Dr. Wildcat, of how do you respond to people who are using the CESM and other related tools to look at natural resources, or really our relatives, to look at development in places that you consider your homeland?
Well, first of all, thank you very much, Julie, and for taking on this this challenge of moderating this panel, and just so honored to be here at the CESM workshop. So it's a great question, and so my expectations and what I want people to understand is, first of all, I think when people talk to indigenous, tribal people about a homeland, they need to understand that what we are really talking about is community. And community as understood as a deep sense of community of people with a place, people who take their identity from that land, from the water, from the plants, the animals, the ecosystem, if you will, that environment that in our indigenous ways of thinking really give us our identity, shape us who we are as unique indigenous peoples. And I think that's why it's really, really important that people who are using this model engage people on the ground in those places where they are going to work so that they can really understand that we're not talking about land in any sense of real estate. We're not talking about land and plants and animals and what's under the ground. In a resource model, we're really talking about it in a deeply relational model, a way of thinking. And ultimately, as Julie pointed out, as she graciously put in the question, not so much as our relationship with resources, but our relationship with relatives. You probably noticed that my surname Wildcat is an embodiment, again, of that deep relationality, a Wildcat clan. I'm fortunate my name, my surname, my English surname that was given after the Trail of Tears to one of my ancestors was just basically a clan totem, Wildcat. Oh, that's Mr. Wildcat. So when you take your identity from plants, animals, the wind clan is a very powerful clan among many of the southeastern tribes. So we have a wind clan, but we have a deer clan, we have a turtle clan. It's almost as if when you start talking about our place and our community, you have to understand that you are stepping into a kind of an environment where people really take that relationality to a very different level, almost I like to call it a kinship level of understanding, you know. And I think that's really crucial for people who are using CSM to understand. So, you know, my main point is to engage with people, because particularly when people are using these models, you know, and you know, it's real easy to get so caught up in the technology, the art, the creativity, the intellect that you can employ, you know, in the use of this powerful tool, to forget the people on the ground, the people who are living in that place, which your models and how people think about that place play a tremendous role in informing that how they think about that. And I think that's really important to grasp. So, you know, my thoughts on this, what I want people when they reach out to tribal communities, indigenous communities, to try to understand how those places fit in a value system that might be somewhat different than the people who are looking at land, air, water, plants, animals as resources, and how that's gives a very different kind of viewpoint of a place compared to when you think of that place as full of relatives. And I think what's exciting about this, I think for people who are using CESM, you're using this model because it's really all about relationships. So I am really excited about the fact that I think people who are using CSM have a really incredible opportunity to draw on, to understand what people on the ground know in particular places that you are modeling, or that your model, you know, is projecting what it might look like, you know, over a period of time or in the future, what could happen. I think having those relationships with people there just gives you a whole nother level of insight into how you might interpret, how you might, you know, think about tweaking, you know, the model that you're using with some different elements, some different features that are going to be useful as we think about landscapes and seascapes that are going to be tremendously impacted by climate change. Your work is so critically important. It's not an either or. I don't want people to ever think it's an either or. You know, I talk a lot about Indigenous knowledge, and yeah, Indigenous knowledge sort of on the ground where you live, experiential knowledge. You know, I jokingly said that we're the local sensors. The people who are using the models, you're the remote sensors. We need to put both together. We'll have a much more accurate view of what's going on with this beautiful blue-green planet, and with particular places and particular peoples by doing that. So that would be my suggestion. When you reach out, bring your active listening skills, because I think if you're fortunate, you are going to learn something that will make you better modelers.
Thank you, Dr. Wildcat. And I think you can all see why this is he's one wildcat that is a expert herder for all of us cats here. So with tremendous appreciation for that and more. I think we'll go kind of looking, from, the CSM and, and modeling and climate science side of this. I'm curious, Kristen, I'd like to bring you in to, share some thoughts on how CSM can really be useful to communities that are experiencing the on-the-ground effects of climate change. As Dr. Wildcat was just talking to, right, really those local sensors, right, the people who are facing this every day, not as some existential crisis into the future, but it's their lived reality in the present. If you can speak to this.
Yeah, thanks, Julie.
Please turn on your mic.
I just think, is it on? Is it on? Yeah? Okay, there. Yeah, maybe I'll just hold it closer. So I think, the obvious answer is that climate affects everybody on this planet. I mean, whether you're an indigenous person or not, we're all interacting with the climate every day. And, but I think that it's important to point out that, for these indigenous communities, they're interacting with nature so intimately that, that they are experiencing climate change at a different level than a lot of us. And so having a model like CSM to be able to look at these changes and what we anticipate in the future is extremely important. And we know that everything is connected, and that's what CSM is all about. We have all these different parts of the Earth system interacting, and we really need all those parts to accurately, simulate what's going to happen in the future. And we also have the ability to use large ensembles, which are, they allow like the statistical analysis of the likelihood of extreme events, and we can really disentangle the effects of climate change from just natural variability, which I think would be useful in putting changes that indigenous communities have observed and will continue to observe into the proper context. Of course, there's, these are run at 1 degree resolution, and that is a challenge for this project because, all of our future simulations, or at least most of them, I think that you're looking at other ones that are higher resolution, but a lot of them are run at 1 degree resolution, which is hard to translate into on-the-ground effects for climate change. And so that's one of the major challenges with this work, and we do have members on our team that do simulate smaller scale processes like coastal modeling, hydrology, things like that. But also just like to bring up, like, you know, CSM has a lot of useful variables that are output from the model, and you know, we can gain a lot of information by analyzing these in the context of natural variability, something like how hot will the summers get, are storm intensity going to increase, what are the effects of ocean acidification on the region. I'm always thinking about marine ecosystems. But yeah, we can definitely capture some of the large scale effects, disentangle that from natural variability. There's also, you know, we don't simulate like a harmful algal bloom, which is one of the major effects or effects of climate change that's impacting one of the regional hubs, the Alaska hub. And but we can simulate conditions that might favor the development of harmful algal blooms. And so I think, yeah, there are obviously a lot of ways that CSM could be useful to the communities, but just like kind of flip the question around, you know, to how can the engaging Indigenous communities actually help, you know, CSM? And I think that's what Dr. Wildcat has been alluding to as well, is that, you know, by engaging with these Indigenous communities, we can tailor CSM, it's what we simulate and its output to be useful to these communities. And that's something that we just couldn't do without actually engaging with these people who are really experiencing climate change, and they're, you know, just interacting with nature in a way that I think, yeah, that most of us don't really do. So it is especially critical to engage these Indigenous communities and on the coastline, because they have all these different processes that are impacting them, and that's yeah, that's pretty intense. So yeah, I'll leave it there.
Thank you so much, Kristen. You know, and I think a lot of what you shared too is, you know, thinking about the flexibility and adaptability needed, right? That not you know, not any community is the same, right? The diversity of cultures, of knowledge systems, of when we're talking about, you know, Indigenous people, it's Indigenous peoples, that it's Indigenous knowledge systems, right? Indigenous knowledges, Indigenous sciences, right? That the multitude of working with. And so even doing this within one context, in one place, and one people, right? It's all going to look different. And, you know, there's things that we can learn and adapt to other places. But, you know, I think, you know, we're all always on that learning curve. So I hugely appreciate what you shared. I think we'll go over to Diamond and then Suzanne. Would like you both to respond to and thinking about, you know, how has working with Indigenous communities really affected the science you do, right? Affected the science that you do, how you do it, you know, thinking about what's been, you know, those challenges, and in a similar light, what have also been those biggest transformations. And so maybe if you can duke it out over Zoom, or Diamond, I'll call on you to kick us off.
Sure. Yeah, I guess for a little bit of context, for my dissertation, I did absolutely no modeling. Everything I did was collecting water samples and looking at the chemistry to better understand how the water in Hawaii moves through the water cycle. And what I was finding was that within 1 mile, waters can be very different. The source of water and how it flows underground, even the rainfall patterns are so unique. And if you've ever been to Hawaii, especially the big island of Hawaii, you will know this too, right? Like you can just drive 2 minutes down the road and it could be pouring rain, and then drive a little bit further and it's like you're in a desert, right? And so after I finished my dissertation and I was really looking for postdoc opportunities, I chose NCAR because I really wanted to be able to understand the modeling perspective in what I was observing in real life. And a lot of what my dissertation utilized was my ancestors' knowledge. So in Hawaii, we have what is called Nupepa on the Hawaii newspapers, and it goes back to the 1800s. And it's just this huge repository of information where people were documenting things like, you know, houses blowing over from strong winds, or streams overflowing because of large amounts of rain. And so how can we think outside the box, I guess, is what I'm pitching to everyone here is, there's so much more information that each Indigenous community has about their place because they're so reliant on it for their livelihoods. One of the elders that I worked with, oh my God, sorry, my cat, she's never done this before. So one of the elders that I worked with on the Big Island, he framed it to me in this way. He said, in this modern society, we think of things as a resource, but for our people, it was a source. And that's the difference, right? Resource talks more about how can you extract and utilize what's in the environment. But for Native peoples, we call it a source because we understand that it's not infinite. And so for me, having that kind of understanding of my own place, I think that's changed the way that I think about modeling. So how can we use a model like CESM to really change the scale and resolution at which we're doing our models? I don't know anything still about modeling, so I might be pitching to a crowd that's like in total shock. But I think that, from my experience, I guess I'll bring this back to what I said in the beginning. From my experience in Hawaii, especially, the climate change impacts that we're seeing, whether it be sea level rise, changing rainfall patterns, whatever, happen at a resolution that's so small compared to what is normally used. Hawaii is usually like 1 pixel, right? And that's the entire island chain. We're seeing things happening within 1 mile. There's variability. So I think, like the previous questions about boots on the ground, I'm always happy to take you around Hawaii and help to introduce you to communities here that I'm familiar with. But I think, actually being here, being in this place or being in a place that you're studying is really impactful for the way that you view modeling systems.
Definitely appreciate that, Diamond. And if it's okay, I'll take you up on that offer too.
Yeah. Oh gosh, I'm going to try to follow all of y'all. Amazing. I'm just sitting here. I was like, oh, I want to work with these people. And then I'm like, yay, I am. So from Indigenous community standpoint, so I'm an enrolled member of the Chickasaw tribe of Oklahoma. And so we've been relocated. Our traditional homelands are in the area where the Tennessee Valley Authority boundaries are now. And then we were relocated to Oklahoma. And what I find is stunning with that is if you go over to our homelands and then you go to South Central Oklahoma, where we have aquifers and limestone karst topography, even the plants and everything and the smells, they're the same. It's just stunning to me how resilient we were, that we were like, okay, they're moving us west, continuing to move us west, but wait a minute, we found this place that's our homeland. That's what we smell, that's how we are, that's what we do, and those are our seasons. And it's just stunning to me from a resiliency standpoint on that. And so with that, it goes to what Diamond was saying, is that we have tremendous knowledge of those systems, events, oral traditions, and everything that were in our traditional homelands. So you may think that we are in central Oklahoma, that it's like, okay, they moved here, and everything. And our history starts there. Our history doesn't start there. Our history starts way there, in a whole nother part, in a whole nother place, in a whole nother connectedness that we're looking at differently when we're trying to bring about our reanalysis. When we say we have a data set reanalysis and they're saying, oh, we've been able to do 80 years. It's like, really? Our reanalysis is all the way back. all of our oral traditions, all of everything that we have that's in our tribal repositories and everything. And we can help. But with that comes a trust. And so in my work now as a scientist and having worked in the realm of modeling and sea level and coastal ocean coupling with river models and everything, it's that connectedness that I'm like, okay, wait a minute. We were talking about something way back in oral tradition and with my tribe. And I'm like, let's go back and let's see. If we can't run this and we can't do this and it doesn't capture that one, we're on a tail end of a curve here and we're extrapolating into nowhere. So let's go. So that connectedness, not only from our home place, but our experiences is so vitally important, I feel, in our modeling discussions to know, okay, wait a minute, we're trying to calibrate, for example, high flows. Our high flow, well, I'm sorry, we had the entire Mississippi River Valley that was underwater according to what our oral traditions were. So what does that event look like when we're looking at climate change? So I bring it to that point that how has that affected me and what I do and what I'm working with now with the tribes in Louisiana, some of whom are not federally recognized. If you have ever just experienced heartbreak, is to understand the hoops that you have to jump through to be recognized by the United States, to be an indigenous tribe where you've always lived. And so with those tribes, that sense of place that Diamond was going to, what they know, what they've experienced, how they are living in it, the seasons are changing, and how we can, with co-production, but also from a long history of trusted relationship, help them, but they're actually helping us. And so that's what I've really learned a lot with that experience in both the Indigenous community and also in the modeling community. So.
Thank you both. And, I think what Suzanne was articulating there too is, sorry, I'll call you out for a moment, but a great example of, we often talk about as, kind of two-eyed seeing, and what you bring into that space. And I think, as to what Kristen was speaking to earlier and, Dr. Wildcat's call for, active listening, of how you've really taken the approach to just sit there and listen for many hours on end to communities in meeting space, in conversations with leaders, seeing it from more that bird's eye view above of what's going on across the landscape, and then bringing both, that two-eyed way of seeing into the perspective in supporting and working together and coming into the collaboration, recognizing the difference between, support and help, and centering communities' priorities. So thank you for sharing in those remarks. I think we'll go over another question I'd like to pose to Carlos. We're going to come back into the room here. Is, Carlos, from your perspective and the work that you've been doing, what do you see that makes the Rising Voices Changing Coasts work and project unique, particularly considering with the usage of CESM?
Great question. Thank you, Julie, and thank you for inviting me here as a panelist for this incredible session with all of you. So there are a couple of things with themes that was expressed today. I think this project in particular has a foundation on intentionality and relationships, which is really unique and key in the development of this project. One example is, the proposal for this grant that was brought before NSF was not just done in a matter of 5 months. This was over a span of at least 10 years through the Rising Voices community and the relationships that have been built over the past 10 years and the connections that have been done to bring us to this point. And that just speaks volumes to how intentional this RVCC project is. It's very human relationship oriented and community centric with the community leads that we have across the 4 regions for this project. Another unique aspect is on the discussion of open science, which has been a huge topic within NCAR and within the geosciences, within this particular project on the sovereignty of data, on protecting sacred knowledge when information like CESM or other products that are being used to leverage and provide insights for communities. How are we ensuring that there is community input from local knowledge holders? And that also ties in with language. So what does open science mean for communities versus, Western trained scientists and professionals? And we see this too in other sectors, in the private sector and government, et cetera. That's a really important aspect of this project, and there have been numerous conversations, including professional trainings from the ODEI here at NCAR on IRBs, on data sovereignty. It's a wonderful experiential training opportunity from student engagement, to have the opportunity for Indigenous students, for example, to come here and get to experience the tools and resources that they could leverage and tie in with their local communities. But also for myself, as I, for example, am working in the Puerto Rican and Louisiana working groups and the community leads there. I was born in Puerto Rico, I have family there, but I don't live there, right? I don't have that experience. And so having people on the ground who can share their stories and their pressing issues allows me as a scientist to provide them potential resources and tools that could be tailored like CESM. And one example is this cat-dog explanation that was in the earlier session about low and high resolution modeling, and in Puerto Rico in particular, just to give an example of some conversations we've had in that region. There's a pressing need for trying to connect what we see in these more coarse scale resolution models to the local needs and the pressing issues of communities. And one issue is precipitation, flooding, and tropical systems. And one idea that I have presented, which has had some traction, is although there is opportunities for downscaling as a way to resolve some of these local scale issues. Another opportunity as well is taking some of the coarse resolution models that can resolve the large scale features that inform the smaller scale features. So one example is, the easterly trade winds in Puerto Rico and the Caribbean are an important moisture transport across the region, with orographic lifting, for example, sea breezes, et cetera. But how are the winds then informed by what? And that would be the subtropical high, right? These large scale patterns that, technically speaking, a more coarse scale resolution model like a GCM 1 degree could resolve. And so taking that to kind of understand, storm tracks, how are tropical cyclones going to change in the future that might inform the onshore flow of these systems in the northern or southern part of Puerto Rico, given that you have a mountainous region in the center, and that will impact the region. So that's like another, area that, without the input of communities, we wouldn't be able to get to where we are with that. Another unique aspect is the outputs, the deliverables of this project. This project is not just publishing papers. Right, communities are not going to, even being a co-author of a paper, what use will they have in, a written paper that, discusses results and other things? It is of value, but there are other ways that CESM can be provided for communities, data, information, outputs, things that are tailored to local communities that then they themselves can be empowered to then utilize for the pressing needs that they are experiencing in their local communities. And yeah, I think at the end of the day, this really ties into this question, which is, what does it mean by community in CESM? And we have a wonderful community here, and the inclusion of Indigenous knowledge holders or communities of other systems of knowing can only elevate the existing community that we share and have. Yeah, thank you.
Thank you so much, Carlos. And I appreciate so much, I think, oftentimes in related work, it's often how, other knowledges and ways of knowing and understanding are informing the models, right? And what you really did was flip that, as how it's weaving together, maybe to improve that model, but also that, what does that translational piece look like on the ground? It's not just, okay, here's what the results are, but how that's really translated so that it's productive, it's accessible, right? Just because something's open access, how is it also accessible to folks? And that it's usable. And sometimes that's, 10% of the work is the model output, right? 90% of that work really what comes next. And just appreciate, the way that you've been working and to try to, over time and with care and intention, really, stitch these pieces together. And so I'd like to we're going to go, maybe let's reverse order it. So I'll call on folks. I'd love for each of our speakers here, of our teachers here, to share, what is a question that you like to pose to the CSM community to take away with and possibly apply in your own work as part of this community and the work that you're doing. So what's a question, that you'd like to pose back to the community that might be considering how they might apply this in their work? So I will start, Carlos, if it's cool to keep you on the hot seat, we will circle back to you.
Yeah, so like the previous question I had, what does it mean by community, I think is an important one. But another one that I have is, I think this project is transformational in that it provides this notion that communities can be a part of CESM. And so the question that I have for you all, especially since, a lot of us are from different parts around the country, or you come from different stories and backgrounds, not only do you share a story related to your workplace, but also a story with your local communities, whether that's with your local church, whether that's with your local hobby groups, etc. How are you perhaps introducing these types of conversations in your own work to leverage and provide spaces for communities who might be really interested at your institution, university, or organization to work together to address the local needs that are pressing in your neck of the woods?
Thank you, Carlos. We'll come back online to Suzanne.
Oh gosh, I was just going to pass over to Diamond and everybody. I guess the one question that I have to the group is does your research and what's the time frame that you see, that you envision for your research window? Because you have to understand, in working with a lot of these groups, I'm speaking for, and it's for no fault of their own, but they're very resource limited. So what are you doing as researchers in the planning stages and the out years and the operation and maintenance of these models doing to support a what you would say is a long-term relationship? We're not talking 1 to 2 years. We're talking 3 to 5, it's shortest probably. So what are you doing in your planning and your commitment to these communities that you're trying to help?
Thank you, Suzanne. We will stay online. We'll cruise over from Louisiana to Hawaii. Over to Diamond.
Yeah, I just would like to add one piece to Suzanne's question. Also, how are you working to build trust and relationships with these people, right? Because it's not just a timeline for funding cycles, but it's also a timeline of rebuilding trust with Native peoples in the scientific endeavors that you're doing. Because I mean, this could be another 1 hour long panel if we talk about why there is distrust amongst the Native communities, right? So I think trust is a big part of the timeline as well. And then my question, I guess, that I would pose is not so much how would you like to, but how will you start to think outside of the box of, well, I'm speaking to you from a box, I guess, but from outside of this box, right? What kind of data sets could you imagine incorporating into a CESM model that does not look like a spreadsheet? I think that for a lot of the anecdotal, is that what we would call it? Anecdotal, evidence or conversations about climate change don't fit into a spreadsheet. And so how do we think outside the box of a computer screen or a supercomputer to really think about how we're doing our models and what its application is and who it's affecting? I mean, I know these are a lot of different questions, but I guess my thought is beyond an Excel spreadsheet of data or CSV, whatever you use. Yeah.
Thank you, Diamond, and the gauntlet of humanizing all that we do. We're going to come back into the room to Kristen.
Yeah, so I thought a lot about what my question might be, but I guess the part of this project that has been the most enlightening for me is just in terms of learning about Indigenous communities and their knowledges, is how the Indigenous people see their place in nature. And they don't see it like humans as separate. They see them as like part of the ecosystem, a part of the, they see all the parts of nature as kin or, not as resources as like other cultures do. And they seem to have this like intuitive sense of sustainability, like they think about future generations and making sure they don't over-harvest something, and so the ecosystem can continue to be productive for the community. And I just find that really amazing. And so I guess my question is that how can we incorporate this perspective into CSM, rather than just seeing humans as people who emit or CO2 or clear the land or exploit the resources? Like, how can we take this like Indigenous perspective and apply it to our model? And I have no idea what the answer is, but that's something that I think that is important to think about. So.
Thank you, Kristen. Appreciated, and appreciate you being part of this work and your leadership in it. We'll come back over to Haskell now, to Dr. Wildcat. Oh, Dr. Wildcat, you are on mute, although we can never silence you.
Yes. Okay, folks, I think there's a common denominator here. And I think in everything that's been brought up, Suzanne's great point about, rethinking, the time frame. Diamond's point about, thinking beyond the spreadsheet or outside the spreadsheet, all of the points that have been made, excellent. And I think my question to all of you who are using the CESM is to ask yourself, what does engagement with tribal peoples, Indigenous peoples look like? How do you do that? I don't have an answer. I think but to me, that's an important question, because absence engagement with trust, absence engagement with an acknowledgement of responsibilities you will have, none of what we talked about, I think, can really come to fruition. And so I'd like to ask you to think about, what does engagement for a modeler look like?
I think there have been some wonderful challenges posed for the folks gathered here, and whether you're virtual or in person, right? As I know this is kicking off your convening, so I hope that there is time and space to come together and reflect on some of these. These are all very actionable questions posed. These are not 30,000 feet in the atmosphere or beyond, but this is your grounded work. And so we hope that you'll continue to engage with us. I did want to, let folks know that, the Rising Voices Changing Coast Hub is a project. A lot of this came from engagement that we've had together collectively through the Rising Voices Center for Indigenous and Earth Sciences, which definitely encourage, folks in the room and online, if you'd like to engage. We actually just a week ago in the very room that you're in held our annual workshop, which I'm beyond delighted to say had more NCAR scientists attending than I think the prior 10 years combined. And so we're riding this wave. And I think we are in the midst of this real transformational change. It's not easy. It's hard. It's unsettling. It can be unnerving. But it takes a really big village to do so. And so this work is not going away. These problems are not going away tomorrow. We're at this time of intersecting chaos and crises. And this is a space and time to really be putting some good thought, good minds and hearts together here. So we highly encourage, if you'd like to continue to engage that way. I'd also like to invite Carlos to share some work happening through AMS as well, which I imagine many folks here are engaged with.
Yeah, so this is also not going away at the AMS. Why do I mean by that? Well, I developed and chair the Committee on Spirituality, Multi-Faith Outreach and Science, or COSMOS, which seeks to develop relationships with spiritual, faith-based communities and organizations in mutual partnership with the Weather, Water, Climate Enterprise on environmentalism. And following the success of the 103rd annual meeting in Denver, which had its first town hall and presidential session on Indigenous and Earth System Sciences, we will have for the 104th annual meeting in Baltimore an entire symposium on this topic called Convergent Science, Indigenous Weather, Water, and Climate Knowledge Systems Practices in Communities. And we're also really excited in honor of one of our beloved colleagues here at NCAR and Rising Voices that the 105th annual meeting in New Orleans for this symposium will be named the Heather Lazarus Symposium. So yeah, lots of opportunities also at the AMS related to these topics. We'll be here, all week. If you have any questions, as well as, questions for folks online as well related to all of this work. Thank you.
Thanks, Carlos. Yeah, and so hopefully many of you will either be in Baltimore or tuning in to that the end of January. Hope to see you there. And, I did want to one of our core partners in all of this, been with Rising Voices since pretty much the beginning. If I may channel him for a moment, Bill Thomas with the NOAA Office for Coastal Management. And, he often reminds us in this work that we're always setting the table for those coming next. And that's a little of what we've also tried to emulate here of very much the intergenerational approach to this work. And thinking about it really in the context too of, we often talk about inviting people to that table, inviting people to engage, inviting folks into space also, but thinking about very intentionally, well, who built the table you're inviting them into? Where is that table located, right? Where do those conversations happen? That becomes a really important part of a lot of this engagement that we're speaking to. And one of our co-founders, Rising Voices, Bob Goff, would often remind us, climate change is inevitable, but adaptation is optional. So we certainly hope that you will be using the good work you do for the latter side of that equation of helping and supporting ways that adaptation becomes ever more possible and best informed. And as Carlos mentioned, one of our other Rising Voices co-founders, Dr. Heather Lazarus, who's of course at NCAR for many years, a lot of this work was founded really on the ideas of not one single knowledge system holds the answers, and she'd often remind us the importance of that diversity of knowledges, of ways of knowing, of ways of understanding, of how we weave together from what we know from the past, from the present, how that can help inform the future. And it takes all of us as part of that. So deep appreciation for you all tuning in, listening to us, actively listening, and we hope that we kick you off in a good way into the rest of your seminar or symposium. And I would like to hand it back over to, I gotta say, y'all, we were so nervous, at least I was very nervous that we had an hour to do this. Usually we do this kind of thing like all day. So I just want to take a moment of y'all, we did it. I didn't know how that was gonna happen, but well done. And so I'd like to hand this back over to Dr. Wildcat to close us out for this session and move us forward into your next engagements.
Yes, well, thank you, Julie, for that wonderful facilitation, and the hour went quickly. There's a lot that we could unpack and talk about, but I think, when Julie had presented this idea and Marika, I got excited because, again, I'll go back to where we started. Ultimately, it's all about maybe strengthening, deepening our understanding of what it means as a human being to be a part of a life system community on this planet, on this mother, the earth. And I think, I like to always remind everyone in our hub that, we're all related. Isn't that what modern evolutionary theory teaches us? We're all deeply connected in relationships. That's what, modern ecology teaches us. And I'm hopeful that people that are using this CESM tool can really think deeply about how the employment of that technology, that tool, can strengthen our understanding that, life on this planet has suffered tremendous losses, actually, in this age of the Anthropocene, the age of man. And maybe we could turn that around. Let's see if we could use CESM to become better relatives again to the balance of life on this planet and the systems that make our lives, our Earth community, possible. So I'd like to leave you all with that, and thank you so much for the good work that you're doing. Sanlai, Gayasata. Thank you so much.
So thanks to the panel and Julie for moderating the panel. I think, we have a lot of things to think about in terms of how we as a community can engage Indigenous peoples in our work, and how that can actually help us inform our models as well. So not just a one-way interaction at all. And that's definitely what we're trying to do within this RVCC hub. And there's actually quite a few scientists in the room that are involved in this hub. So I see Tim, I see John Fasulo, anyway. So you'll be hearing more about this over the years. This project is just starting. So with that, I'd like to thank our panelists, thank people online who tuned in, and we're now going to a poster session. So.
Thank you again for the panel. Thank you, Mary. So we are going to have a poster session now till 12:30. And the posters are, all of them, I believe, upstairs on the second floor. I'm told that the elevator is not working, but there are stairs on both sides, so you can easily go up. And then the lunch will be served outside starting around 12:30. And then we'll reconvene at 1:30 with 2 parallel running cross-working group sessions. I just want to also, since this is our first time in 4 years, we wanted to take a group picture. So when you essentially go towards posters, if you can just linger a minute outside, somebody is going to be taking a picture from the second floor up and facing that. I mean, we are supposed to face that way, I guess, whichever that direction is. So if you can do that, that'll be great. So we'll have a record of it after 4 years. East, yeah, or whatever that direction is. Okay, thank you.
And we're getting ready to start here.
All right, it's 1:30, so let's get started. Welcome to this cross-working group session. I'm gonna get back from England today, so he asked me to take over the session.
Mic check. Mic.
Can you hear me?
Yes,
Okay.
we can hear you.
Great. So, in case you didn't hear me, I'm not Rich still. He's on his way back from England today. So we're going to talk about understanding climate at the intersection of CSM. Rich sent a couple of slides that I'm going to zoom through really quickly because they are not complete and I don't know exactly what he wanted to say, but the idea of the session is to have a conversation about what we're doing at the intersections of CESM and what are the science issues that are involved with advances in CSM and coupling between different components of the read them as well as I can. I think important, the main emphasis here is going to be on
somebody bring, yeah. Okay. Okay, yeah, I'm going to put a land perspective on this.
And in particular, what Brian didn't mention, I think he'll talk about later, is CAM is having a very thin, much thinner layer at the surface now, nominally 20 to 30 meters above the surface. So what is the impact of CAM approaching the land surface doing to the CLM? And there are a couple of things that you'll see, two parts to this talk. One is what is CLM doing right now? And what might we want CLM to aspire to do? And throughout this presentation, keep this in mind. Where does the atmosphere stop and the land begin? Because really, CESM enforces a very sharp boundary between the atmosphere and land. There are two separate models that communicate through a coupler. But in reality, air is air. It doesn't matter whether it's near the ground or in the atmosphere, higher up. And so that's sort of the theme of this presentation. Okay, so this is a perspective of how CLM represents the surface right now. It's what we call a big leaf canopy without vertical structure. The flux of, in this case, sensible heat to the atmosphere has three components. There's a flux from the foliage to the canopy airspace, from the ground to the canopy airspace, and then there's a turbulent flux from the canopy airspace to the atmosphere. And that's what CAM sees, is that flux. And that flux is modeled using Monod-Nabokov similarity theory, and that has this idea of a surface. Then the surface is this imaginary height where the wind speed extrapolates to zero. And I'll come back to that in a little bit. And then there's a 2 meter temperature that I want to focus in on, and that's 2 meters above this imaginary height. Okay, so the model, and all land surface models are doing this. They're using Monod-Nabokov similarity theory. That's just based on the observation that the wind speeds follow logarithmic profiles in the surface layer near the ground, as modified by atmospheric heating and stability and buoyancy. But the same is true for temperature profiles and wind speed. Specific humidity. Some definitions here that are important are, what's this ZATM, this height of the atmosphere? That's what I'm sort of focusing in on in this talk. That's the height where the wind speed and temperature and humidity of the atmosphere are actually provided to the land model. And so you see those throughout here. And then you see, by definition, the wind speed goes to zero at this Z0 plus D. That's where the roughness length and displacement height, that's this imaginary sink of momentum. And also, that's the height at which the temperature has the surface temperature, and the specific humidity extrapolates to the surface value. So what this looks like sort of schematically is this picture over on the right. The reference height that we use in the CLM is taken to be the height of CAM. The height we get from CAM is taken to be the height above this roughness length and displacement height, this apparent sink. So that's what we're doing. Whatever height we get from CAM, we just elevate it by Z0 plus D. And what you see on the right is sort of some ideas of what this looks like. Is CLM has this concept of subgrid tiling. There are different sort of surface types within a single grid cell. In this case, I just drew a forest tile and a grassland tile. But what you can see, the trees are very tall, of course. They have a very large roughness length and displacement height, something on the order of 15 to 25 meters. The newest versions of CAM are going to have something like the thickness of the first layer is something about, say, 30 meters, centered at 15 meters. So this forcing height and the temperature and humidity and wind speed are 15 meters above this 15 to 20 meters Z0 plus D. But that same grid cell, the grassland tile, is much different. It's shorter vegetation. Again, CAM is going to be 15 meters above that. But in terms of a physical height, it's a much smaller height. And you can sort of see that. That's what I was trying to do in these pictures. Same forcing data, but different sort of physical heights because of this way we're implementing it. And then also the model has a concept of a 2 meter temperature and a 2 meter humidity and a 10 meter wind speed. In this case, 2 meter is defined as 2 meters above this apparent sink for momentum, the Z0 plus D. That's used to diagnose the 2 meter temperature. So what you see over here on the right is the classic sort of profile of temperature from the atmospheric value at that height, ZATM, down to the surface at Z0 plus D. And the 2 meter temperature is just interpolating along that 2 meters up. So again, remember that this Z naught plus D is it's a theoretical height. It doesn't actually necessarily exist. It's not actually measurable, but it's sort of the theoretical height in Mono-Nabokov similarity theory. And then this is, there's also a 10-meter wind too. And that's at 10 meters above this Z naught plus D. Okay, so that's all I want to switch. That's what CLM is doing right now. I want to switch to what we should be doing, and sort of this is the aspirational side of the talk. And it's based on the idea that CLM and most land models use Mono-Nabokov similarity theory, but it fails above and within tall plant canopies. And this is a profile, it's wind speed normalized by friction velocity. It's observed measurements of wind speed above and within a tall eucalyptus forest in Australia. The blue is the observations, and the red is sort of what it would be expected from Mono-Nabokov similarity theory. The height is normalized by the canopy height, so 1 is the top of the canopy. And so what you can see is above the canopy, Mono-Nabokov, the winds deviate from Mono-Nabokov similarity theory. And this has been known for a long time, that the roughness, and this is what's known as the roughness sublayer influence. And then within the canopy, you have an exponential decline in wind speed through the canopy. It doesn't go to 0, as you see in that red line. There actually are still wind speeds in the canopy. So we've been trying to incorporate these ideas into a land surface model. And what I've been working with is with Ned Patton and Sean Burns, also at NCAR, and Ian Harmon and John Finnegan. We've been taking these ideas and developing a multi-layer canopy model. I'm not going to go in, we don't need to go into all the specifics of what this is doing. Just realize that what we're doing is from the volume of air from the ground all the way up to some height above the canopy. We're dividing it into discrete layers and modeling the fluxes, the source and sink fluxes within a layer and the vertical transport between layers. And then we're calculating things like temperature and humidity and wind speeds and so forth. The point I'd really like you to take away from this is the physics and physiology of this model are much simpler and more consistent with theory than is CLM, but that's a long talk in itself. But also it works. And you can see this is a forest at the University of Michigan Biological Station. It's a 20-meter tall canopy, and we're doing a pretty good job of modeling temperatures above and within the canopy there. Some more recent work we've been doing is looking at a walnut orchard in California. This is a 10-meter tall canopy, and that's what the horizontal green line represents, and the little plant off to the side. And again, we have measurements of wind speed and temperature above and within the canopy. And these are some simulations. And I'd say we're doing a pretty good job at calculating both of those profiles. And so what I'd like you to, the thought I'd like you to leave with is this idea of what do we mean by the land surface in an Earth system model? And particularly this idea of where does the atmosphere stop and the land begin? Or another way of phrasing, what is the surface in a land surface model? And so I tried to draw these two different pictures over to the side of the way we're envisioning the land atmosphere coupling. And in a multi-layer canopy, you have multiple layers within and above the canopy. In this case, the trees are at 25 meters tall. But I tried to draw over to the right what I think is going on with CAM, and that's this idea that the first layer is approaching 30 meters in the surface, and the quantities are centered on that layer. And so these quantities we're receiving now from CAM are going to be at sort of 15 meters height or so. But the question is 15 meters above what? And I think that's what we're going to, do we just take that and sort of stack it on top of the multi-layer canopy or CLM, which is sort of what we're doing now? Or do we realize that 15 meters is 15 meters above the ground, but that's getting into the space now where you have leaves and branches and trees, and you have to deal with different processes to model that. So that's the idea. That's what I mean by where does the atmosphere stop and the land begin? Because we're modeling the air now in above and within canopies, and air is air, but we have air in the land model, and we have air in CAM now. So how do we deal with sort of these discrepancies? Now, this is still very aspirational. This doesn't even actually run in CLM yet, so we're talking a long ways down the road. But I think it's time to begin to start thinking about these different ways of envisioning what the surface layer is from a CAM perspective and what it is from a land perspective. And that's it.
question is just that this atmosphere level, the lowest model atmospheric level, which we call ZBOT, or in your schematics was ZATM. So we use the Z is actually the geopotential height, and it's a grid geopotential height. So within the actual grid box, there can be or there can be a distribution of geopotential heights that, as long as the mean gets to ZBOT. So I think that's something to think about in terms of, can you say at this point over this land patch, that grid mean ZBOT is actually a hard sort of limit of where the atmosphere is, or if you can imagine some variability in there.
The bottom height of CAM is actually sort of nebulous quantity to begin with, I think is what you're getting at. There is a talk later on. Meg Fowler has been working on these ideas of sort of subgrid heterogeneity within, and using some of the higher order statistics of club, and that might be sort of what you're getting at. But I will also say, you know, the idea of a forcing height is only really perfectly well understood when you run these models uncoupled, forcing at a tower site. For those simulations I was showing at University of Michigan Biological Station or this wall, we're measuring the profiles from a tower. And the tower is at the Walnut Orchard, it's about 23 meters. At University of Michigan Biological, I think it's more like 28 or 30 meters or so. And that's very clearly define what it is. But when you couple to the atmosphere, you know, CAM, it's less clear exactly what that is.
Okay, well, I'm glad Gordon went first because he went through all the Mono-Nabokov similarity theory, so I don't need to bother with that now. But I think one of the big differences here with the sea ice is that we have to be thinking about a boundary layer above the sea ice and a boundary layer below the sea ice as well. So I'm going to go through a little bit of that. So I'm just going to put up in words the current state of things in the CESM, and note that a lot of this stuff is, you know, 25 to 30 years old and hasn't really changed in a long time. You know, this is based on early work by Bill Large mainly, who came up with a lot of this theory for the stability dependent formulation over the sea ice. And it's similar over the ocean points too. If you look at the code in the coupler over the ocean, it looks a lot like this formulation that's within the SICE model as well. So the main difference here is that we have constant, we do consider drag and transfer as a function of stability, but then we have a constant roughness length over the ice. We don't actually take into account differing surfaces. That's something that I'll talk a little bit about coming up. But U star is definitely a function of the wind, and depending on the option that you choose, it can also be a function of the difference between the wind and the sea ice speed too. Under the sea ice, we use more of a formulation developed originally by Gary Maycutt and Miles McPhee, where they have a constant drag and transfer coefficient underneath in the ice-ocean boundary layer. And then again, U star is still a function of the relative ice-ocean velocity underneath. So graphically, it's sort of a similar thing. Can I point at the screen here? So anyway, you can sort of see that. Oh, okay, cool. So you can see here, I mean, there's a lot of stuff going on in this picture, but I mean, you've got fluxes of shortwave and longwave energy at the surface. You've got the latent and sensible heat fluxes. You have these similar sort of Mono-Nabokov sort of ideas as well, with the logarithmic profile going down towards the surface. And I'll just add a point here on that to Adam, is that it sort of doesn't matter where ZBOT is from the atmosphere, because we just compute those values, the transfer coefficients, up at that level regardless. And then that's how we compute all of our fluxes, is based on the delta T, delta Q, and everything from that level down to the surface level. And then we use the mononomial of similarity to get sort of the reference height velocities and reference height temperatures and so forth. And then, you know, internally, there's actually some of the radiation that penetrates through the ice and comes out through the bottom into the ocean. And you see there's this sort of sensible heat flux underneath from the ocean to the ice. You also have a latent heat flux in the form of ice growth or ice melt too. So again, we've got to be thinking about these two sort of boundary layers going on here. The complexity, like the land model, you know, instead of tiles, we have a subgrid scale ice thickness distribution. So we divide the ice up into categories based on different thickness classes, and we keep track of the fraction of each of these thickness classes. And so we're actually computing all of these fluxes in each of these subgrid scale categories as well, both from the ocean and from the atmosphere side. And then what we actually see at the end of the day is that we've merged this all together based on the fraction of the different surfaces, and that's what we send back to the coupler. And then internally in the coupler, then you're actually merging ocean and sea ice and potentially even land all into one atmospheric box, and that's the fluxes that the atmosphere then sees. And then also just to highlight here too, that within our radiation formulation, we can even in each of these categories have aerosol or dust particles that will influence the albedo, as well as melt puns and other things going on as well there. So, but the future, you know, we want to move to more of a rigorous form drag formulation. And so you can see here the surface of the ice is not smooth, and certainly underneath the ice it's not smooth. And so we want to be able to take into account a variable roughness length going on forward, and so that we would make it a more sort of correct formulation to doing this flux exchange. This is actually in the SICE model currently, but it's not really sort of working as such, I guess is the right word. And one of the main reasons is because of the way we deal with ridges in the model. It's not really quite the correct way. And so again, part of the future work that we want to have is the work of Andrew Roberts, who has worked on this variational ridging approach, which is a more accurate representation of the ridges underneath. The other thing that we do a lot in the polar community is we take advantage of field experiments. And so the Mosaic program, which was basically a ship locked in the ice for a year, you know, they did an extensive measurement campaign of fluxes and albedos and everything, and at different heights, from drones and from aircraft and from satellites and everything. And so they've come up with a very comprehensive data set of these surface fluxes. And one of the things that Lorenzo Zampieri, who recently finished his postdoc here, has been working on is machine learning methods to look at some of these data sets from the Mosaic program and thinking about ways to build parameterizations based on these. So then, I guess I just, with that, I'll sort of summarize that basically we haven't done anything to really update this exchange in many years. You know, so I think you can look back in the CESM manual and you will see that basically the code that is the same as it has been ever since then. And then a unique aspect is, of course, that we have fluxes to worry about at the top and the bottom, but then also the subgrid scale ice thickness distribution where we're merging all these fluxes together. But eventually we want to move to a more rigorous sort of form drag and variational ridging approach that will help us give us more accurately a representation of these fluxes. And then maybe even, I'm not sure this is on the near horizon, but you know, making use of these sort of machine learning methods and other statistical methods to try to derive perhaps some new parameterization, a new approach in dealing with these fluxes to and from the sea ice. So I think with that, I'll take some questions. So. Okay. Oh, sure.
Hi, Dave. I have a quick question about how rain and snow on sea ice is kind of modeled in size, or are there any updates to that in the newer versions? Thanks.
Well, we do accumulate snow, so that's certainly something. Rain has always been a bit trickier. We don't have a way to deal with the hydrology of rain falling on the snow and within the ice. So we actually ignore rain currently, and it just goes straight through to the ocean. We do have a pond formulation, which keeps track of a virtual reservoir of water, and so it will accumulate rain in that, but that's just simply an albedo formulation for the ponds themselves. So in the future, there is definitely, with MOM 6 coming into the picture, we're gonna have to incorporate aspects of enthalpy more correctly. So I think there will be some changes coming in with that, but that's basically the state of it at this point. So. Yeah. All right.
Thanks, Dave. All right, I know I'm next. Thank you. So I'm going to talk about the impact of increasing the vertical resolution in the atmospheric boundary layer, which Gordon has already alluded to, and what we hope it means and what it looks like it so far. So as I mentioned when I introduced the session, we've increased the vertical resolution in the free troposphere to have approximately 500-meter grid spacing above the boundary layer up into the lower stratosphere. There's pretty good dynamical reasons to do this. And basically, it boils down to resolving vertically propagating waves. And there's a good literature about this, and much of it talks about this aspect ratio of the horizontal length scale to the vertical length scale. And it boils down to, at least in some arguments, basically buoyancy versus Coriolis, and you want that ratio to be greater than or equal to about 200 or so, or this M front. This is from this Pecknick and Kaiser paper. That's the slope of a frontal boundary, and that it turns out to be about the same number. So you want it to be about greater than about 200 or so for that ratio, which at 100-kilometer grid spacing is about 500 meters, and so that was our target for this free tropospheric vertical resolution. There are other arguments out there in the literature, shown over on the right. There's at least one argument that says that to do chemical plumes correctly in the free troposphere and get the transport correct, you need a ratio that's more like 1,000. What I wanted to point out is that when you look at these kinds of arguments, they're usually in the extratropics, and if you then extend the argument to the tropics, the ratio becomes exponentially larger, as you can imagine, from F going to 0 at the equator. There's also no argument in any of these papers that I've seen, at least, that says that there's a limit to how small a layer you can go to. I think there are arguments for that in the fluid dynamical sense, but nobody talks about going to too high of a vertical resolution. In the boundary layer, things become a little less clear, but we wanted to increase the number of vertical levels in the boundary layer. We decided, after discussion and negotiation, that we would add 10. So that's what we did, and so this is a picture of a prototype of the vertical levels. And essentially, if you look at the right side, the target here was to go from somewhere around 10 or to 20 meters for the lowest level, and then stretch upward to keep the grid spacing 200 meters or less up to about 800 hectopascal or so. And so that's what we're working with as our prototype CAM7 vertical grid.
there's the reasons to go to a higher vertical resolution in the boundary layer they can't be summarized in a nice ratio like delta Z to delta X, but there are lots of papers out there that suggest that having high vertical resolution in the boundary layer improves things, such as the convergence of water vapor and temperature profiles, obviously cloud top boundary layers. Those clouds tend to be thin or multi-layered, and so we would like to have some representation of that kind of structure. And then if you look at global assessments of climate model boundary layer structure in these like Edwards and Davy and a little bit Holtzog, we see a lot of challenges, a lot of deficiencies in global models when we look at the boundary layer structure and depth. There's also good arguments for going to very, very high vertical resolution in the boundary layer in stable conditions such as in Antarctica. And there's lots of examples in the literature of looking at extremely cold climates and suggesting that you need boundary layer layers that are only a few meters thick, which is not something that we're considering very strongly right now for CESM. Our friends at DOE have gone to a higher vertical resolution already in E3SM using a 72 level model for V0 and V1 and V2, I guess. And Pete Bogenschutz has had several papers looking at going to higher vertical resolution and suggests that for at least cloud top boundary layers in the subtropics, higher vertical resolution in the boundary layer can still help, although they do point out that lowering the model level from their 20-meter lowest level height to even lower causes some problems with the time step. So as we go to this new vertical grid, we have some hopes and some expectations that I'm trying to spell out here in this simple cartoon. One of the main motivations for going to higher vertical resolution is to get those cloud top boundary layers to be resolved better, and including the cloud transitions. As we go downstream in the trade winds, going from stratocumulus decks to broken clouds into the trade wind cumulus regime is something that we'd really like to capture better in the climate model. And it's been a challenge for a long time, and partially because of the coarse vertical resolution that we have. On the other side of the slide, we want to resolve stable boundary layers better, which means having much lower inversions and much higher stability in cold climates and at night. And so as part of this, we're hoping to have also improved diurnal cycle as you go from convective boundary layers in the daytime to stable boundary layers at night. And in all of this, what we expect to happen as we improve the vertical resolution in the boundary layer is to have a representation of processes that have more structure, including not only the clouds, but the precipitation that goes along with the clouds, and including the evaporation of that precipitation, which can influence the surface water flux, the dispersion and distribution of chemical tracers and the chemistry and aerosol that goes along with that chemistry. And then as we go into the stable boundary layer configurations, like Dave was talking about, there's a lot of complexity that happens over sea ice, and so by changing the structure of the low-level wind fields, we expect to have influences on the sea ice distribution. There are some recent examples from other models that have done similar increases in vertical resolution, which includes both going to higher vertical resolution in the boundary layer and or changing the height of the lowest level in the boundary layer. And these are just a couple of examples where in one model they changed from a 64 level model to a 91 level model, and they showed improvements in boundary layer height and surface fluxes. And in the second model, which is the second example, this Harshloss paper, is ECOM, as they moved from 31 levels to 62 levels, which is very similar to what we're doing in CESM. They show in the couple configuration that both vertical resolution and horizontal resolution improve the SST biases that they have. They emphasize that you want to do both, but that the vertical resolution is crucial to getting that improvement in the SST bias. Some early indications from AMIP-like simulations with CESM comparing the L32 to the L58 version of the model show that we are having large regional changes in latent and sensible heat fluxes as we expected. I'm not saying whether these are in the right directions or not, but I'll just say that they are regionally quite large. And then on the lower right here this is the net shortwave flux at the surface, and you can see that we are changing that quite a bit too, including in the warm Western Pacific. We're also seeing some indications of changes in the aerosol fields. This is just the black carbon burden and the dust burden. And you can see that they're localized changes, but they're actually quite large compared to the total burdens. So we're seeing some indications that changing the vertical resolution in the boundary layer is having an impact on things that, on the things that we thought would change, the aerosol fields, the radiation, the surface fluxes. But there are still a number of challenges that we're going to have to address. The boundary layer structure doesn't look great. This is just taking a grid point off of California in the stratocumulus region. The blue color is the standard L32 model. The orange is the L58. You can see that there is more resolution there, but there's not a lot of increased structure there compared to the black line, which is ERA5. And then these gray lines, which are dropsons from the DICOM's field campaign, you can see these very sharp inversions, and then this well-mixed boundary layer below them. So we have only some indication of a subcloud layer that's too thin, and then a really smooth transition instead of the sharp inversion that we expect. This is, on the right side, is the cloud fraction. You can see that we are getting now a subcloud layer underneath the stratocumulus, which is an improvement over the L32 level, but the cloud layer is too low, and the top is still not as well defined as we'd like. Similarly, if you go to the Southern Great Plains and just look at the wind profiles, we have a excessive low-level wind speed bias compared to ERA5, and the boundary layer structure is looking quite different, including differences in the surface pressure. So just to wrap it up, we're moving to this higher vertical resolution. The lowest model is going to be thinner. It's about 15 to 20 meters or so, as Gordon pointed out. We expect that this better resolved boundary layer will improve clouds and subcloud layers, increase diurnal variability, and hopefully represent stable boundary layers in a more realistic way. The potential impacts are in all of the ways that the atmosphere communicates to the surface, radiative effects and heat fluxes and stability. But the current results show that there are large regional impacts, but they're not all positive, and we're still faced with some challenges in capturing that boundary layer structure. And I would suggest to this audience that this is a good time to dive in and do a number of careful analyses of the impacts of this boundary layer structure using a hierarchy of simulations from single column modeling all the way up to fully coupled configurations. So that's it. I'll stop there and take questions.
This is Roy Rasmussen. I'm mainly using the WRF model, and we've done something similar to this, and we're worried about snow, and I was wondering if you had any input on the snow problem.
I don't know what we expect to happen with the snow.
Yeah, what we're seeing is that when you have snow and you resolve the boundary layer better, the wind speed and the radiation will change. And taking that into account, it's a positive feedback, and you have to be careful when you do that.
Yeah.
Yeah, so I was just curious about those last results. We showed really very little impact on the boundary layer properties, and so I guess was that surprising to you, and were you expecting to see a bit some improvement? And if not, then you said there's work to do, but maybe. Do you know what that work is?
I don't know what the work is. I mean, so those are preliminary results, so I'm taking them with a grain of salt for now. I made them quickly, and there could be things that I'm missing in that analysis. So I'd like to take a closer look as a first step, but I'm guessing that we could. There are a number of adjustable parameters in Club, for example, that we could play with to see if that can increase the depth of the boundary layer by increasing some of the vertical transport terms. So that's hand wavy. I don't know the answer, but I was surprised that there wasn't a bigger impact in the stratocumulus in particular, because that was the motivation, and I had seen previous results that suggested improvements with similar changes in the boundary layer resolution. Okay, with that, we'll go on to Justin.
So I'm going to talk about mainly the ocean atmosphere fluxes and acknowledge all these people. I haven't talked to them the last few days, some of them, but over several years, I've learned from these people. And the main points I want to discuss, the Mononobikov similarity theory is used. It was introduced by Gordon, and Dave Bailey mentioned it as well. Using analytical forms of exchange coefficients from Bill Large and Steve Yeager's papers, and from Bill's papers going earlier than that. I wanted to point out it's been extensively used previously for lowest model levels, about 55 meters in CAM, but also in 10 meters in the forced ocean simulations. So both the NTEP NCAR reanalysis and the JRA 55 reanalysis had 10-meter winds, which were kind of modified and then used to force the model. So it's been applied in a range of heights, and as far as I know, there hasn't been complaints about the how it performs at the different heights. And now in CSM3, Gustav has been telling me it's been applied at, say, 20 meters. Next point, the surface waves not explicitly included in the surface flux formulation. They do feed into the ocean model. So there's, I'll mention that later. Next on the high wind speed regime is still an area of uncertainty. This has been an area of uncertainty for a long time. It's very hard to measure, for example, the tropical cyclone winds. So there's been more work done, but still a lot of uncertainty. Next, there are libraries of various different flux schemes. I'll hopefully show later, one by Brodeur called Aerobulk. And finally, a point that's been mentioned by Bill Large several times, the original parameterizations were developed using records of tens of minutes to an hour to estimate the parameters. And now if you go to higher temporal coupling, this could be an issue, and it's particularly an issue for ultra-high resolution models, so something to think about. And just a recap, I'm going to point out a couple of things. This is a recap of the kind of thing that Gordon mentioned. But this is three ways of writing the turbulent fluxes. The top is the direct kind of eddy covariances, turbulent eddies, for the momentum flux sensible heat and latent heat. And these have been measured by very high precision, high frequency measurements of the individual terms. That's called direct covariance or eddy correlations. They're not common, and it's hard to measure things like the vertical velocity, particularly on a ship. The method used by Bill and others, it's called inertial dissipation. It used the horizontal component of the flow more, did not rely so much on the vertical component, which is harder to measure. There's also a friction velocity type of form in the middle row, and then the bulk flux forms on the bottom that you're probably familiar with. I should point out that the wind, which is the capital U here, is a relative wind between atmosphere and ocean. And these have to be derived using the top row of high-quality measurements of the fluxes. And so the bulk fluxes are based on variables each of you measured typically in the bulk of the water column, like the SST and the 10-meter wind. But it needs knowledge of things like the drag coefficient, the CD, and the exchange coefficients for heat and moisture. So that's where a lot of the work's been going on. So don't expect anyone to read through all this. But this is kind of a summary of the Large and Yeager. And I'm not sure if I can point with this. Actually works on there. I'm going to try this. And maybe for the remote, maybe I should do this. Okay. This is where all the measurements from ship were used to get empirical formulations for the drag coefficient CD as a function of wind, UN, here. So these are from measurements at sea, and people in the next slide, I'll talk about other people done measurements of that as well. The other point I want to make, following on from Gordon's talk, the vertical structure, for example, of the wind in the boundary layer over the ocean, has the logarithmic profile in stable conditions. It's modified by these stability functions, which are a function of height, or scaled height. And it's these psi functions which have been carefully measured over fields in Kansas or whatever, and it's been mentioned before. But these are used in the air sea flux schemes over the ocean, whereas the drag coefficients come from measurements really over the ocean. And the point of this scheme is to bring the height and the drag coefficients to consistent layers and to be able to use these empirically derived drag coefficients. I'm not sure. Yes, you can see it on both screens. So that's a summary of how it works at the moment. There are alternative flux schemes in the community, and I'll mention a few. A well-known one is the alternative core algorithm, Chris Farrell et al. And Jim Edson, the ECMWF Bell-Jar scheme, and the Whorf schemes. Instead of having empirically created forms of drag coefficient, they iterate on the roughness length. I should mention the previous slide was an iteration. These iterate on roughness length, and they also include cool skin due to the long wave cooling at the surface, and are in a warm layer. Again, they use these standard stability profiles based on field measurements, but they differ in other aspects. Now, these things are related to the drag coefficient form. For example, on the right here, the roughness length, which is this small, as Gordon mentioned, slightly theoretical concept where the wind goes to zero, is a function actually of the drag coefficient CDN, the neutral drag coefficient. And it's also written as a function of the wind speed or wave state, as so in the Farrell core algorithm. And there's a lot more detail to that, but that's a summary. And let's see if I move on. I mentioned libraries of flux routines. Thank you to Gustavo for pointing this out. The Broder and collaborators, they have some nice papers, and they also have a GitHub repository. And currently, it has the Farrell algorithm and the version by Jim Edson, ECMWF, Ed Andreas, and the NCAR scheme. I just mentioned a couple slides about the role of surface waves. So in CSM, the drag coefficient is a function of wind speed. It doesn't directly have information on the waves, but it's indirectly in there. But this paper by Jim Edson looked in more detail at this and essentially found that in moderate wind speed regime, which might be, I don't know, 5 to 15 meters a second, they're essentially equivalent because the important surface wave parameter, which is a theoretical thing called wave age, he found to be a linear relationship on the wind speed, which are these top two panels, roughly linear. So the wind speed formulations are based on this U10 neutral. Wave age formulations strongly dependent on this parameter, and they're linearly dependent, so you can kind of convert between one and the other. So they both work very well, and you can use one in place of the other. But to say that that's for the moderate wind speed regime where most measurements are taken, and things differ beyond that. So this paper argued that wind speed dependent parameterization is reasonable for moderate winds. I mentioned a bit more about how surface waves are put into CSM. They interact with the ocean model, and they provide fields which are used by things like the Langmuir mixing in the ocean model, parameters like Stokes drift, and so on. But they're not explicitly used in the surface fluxes. And I'll finish just with talking about the extreme wind speed regime, which is, I think, maybe the most important of the unknown regimes. The other regimes include very low wind speeds. They're also uncertain. And I haven't talked much about here beyond my expertise, but with the heat and moisture fluxes, there's uncertainty as well. But for the high wind speeds, is the drag coefficient capped or reduced to high wind speed becomes a question. Surface waves are important here with misalignment of wind and wave, stress and wind vectors. Bill has talked about that, has been using it for the ocean mixing scheme. And there's this issue again of the temporal averaging when things are so heterogeneous and rapidly changing. And I'll show a couple of examples from the literature. So this is reasonably up-to-date literature of a long-standing problem. This is a drag coefficient here as a function of 10-meter wind speed, actually in both of these. These are from 2 papers. On the left, this mainly laboratory experiments, and you can see the drag coefficient increases and suggestion of leveling off, but there's quite a range. And it's converting from field measurements to real in situ data is an art. And then on the right is from people have estimated from dropsonde data in hurricanes. They've looked at the wind profile from dropsondes and they assume a logarithmic profile and they extrapolate down to the surface and they make an estimate of drag coefficient. And that was the original paper that by Powell et al. Pointed out that the drag coefficient didn't continually increase. But now, about 20 years almost since that paper, and have a look at the green area is an estimate of the uncertainty of these estimates from dropsondes. It's actually done by subdividing the data and getting estimates from each subdivision. And there's a huge uncertainty. The black line is the mean, but note the uncertainty and things changed with later period in the record length and so on. There's a whole lot of dependencies of this form for the drag coefficient, so still very uncertain. In the Large and Jaeger work, they proposed one potential drag speed reduction, but I'd say it's still unknown. And there's certainly a sensitivity to it. I haven't mentioned it here, but experiments done in a regional CSM showed quite a strong sensitivity for tropical cyclones to how you represent the drag coefficient. So I think I'll wrap up with that. Thank you.
Hey everybody, my name is Kate. Today I'm going to be talking to you about ice sheet feedbacks. And I actually don't have to talk about Mona and Overcroft theory today, so you don't have to worry about that for my talk. Quick outline, and I'll try to go through this talk pretty fast here. So I'm going to give you an overview of how land ice is implemented in CESM and talk a little bit more closely about the atmosphere ice sheet coupling issues that we have. And then mention ocean ice sheet coupling issues we have as well, and give you an overview of our current and future work in the land ice group. And my goal here is to have everybody here learn something new about how land ice works in the fully coupled CESM system. But I see that like Adam and Bill Sachs are here, so everybody else can learn something new, but not them. So, first off, why are we even modeling land ice in CESM? It's not one of the big three. It's not atmosphere, ocean, or land. But sea level is rising, and the melting of glaciers and ice sheets is a huge component of that. And as we saw this morning, there's large numbers of vulnerable populations on this planet that are sensitive to that sea level change. And right now, because of the warming that we have in our system, there's already some amount of sea level change locked in due to disequilibrium in the ice sheets. And we have no idea how much that is or when we'll see it realized. So modeling these ice sheets in the fully coupled climate system out into the long-term future is very important for all of those questions. Excuse me. We also learn a lot about our climate system through paleo simulations of growth and retreat of ice sheets. It gives us a lot of information about climate feedbacks and sensitivities. So this is a hugely important piece of the climate system. And currently we model it with a model called CESM, or the Community Ice Sheet Model version 2. And this is a relatively new component in CESM compared to some of the other ones, and a relatively smaller scientific community working on it, but we're pretty excited and diligent. The things that I want to give you here as a quick overview is that CESM has two basic modes in CESM. We have a fully dynamic and interactively coupled ice sheet mode, which we call CESM Evolve. And then we also have a fixed size one-way coupled mode called the No Evolve. And that's actually the default version right now. So like if you pull up CESM and you run a B case or an F case, then you're going to be getting your No Evolve, one-way coupled, non-dynamic ice sheet. And I'll give some reasons for that later in my talk. But most of this talk focuses on the fully coupled evolving ice sheet, so you can see the coupling issues that we have right now with the CESM system. And I just want to put it out there that right now CESM is one of the highest resolution components in CESM2 at 4 kilometers horizontal resolution. So until the atmosphere gets to that ultra high res 3 kilometers, we're winning in that. This is a plot. I want to see how this works. Does that work? So this is a plot of velocities in the ice sheet, and you can see that we're dealing with a very high resolution model. So how is land ice coupled in CESM? This is a basic little cartoon about it. But the important thing is that we actually don't interact directly with the atmosphere. We interact with the land model. So the land model takes in high temporal resolution properties like surface fluxes, precipitation, temperature, radiative properties, and converts it all into a surface mass balance and a temperature that the top of the ice sheet sees. So surface mass balance is basically just you're getting more ice or you're losing ice. And that's the information that the ice sheet cares about at the top. The ice sheet does respond to the land with a change in the horizontal growth or the vertical growth. And the land model can adjust its virtual elevation classes, which I'm not going to get into here, but it will adjust its knowledge of the ice sheet based on what the ice sheet grows and retreats. We do have ice sheet ocean coupling. When the ice sheet's in full evolved mode, it will calve ice into the ocean, and it will have basal melting that is fluxed as a freshwater melt flux into the ocean. And then we do have sort of a back-end atmosphere feedback system with the ice sheet, in that as it grows taller or shrinks and melts, the roughness on the edges and the height of the ice sheet, because we're talking about several kilometers of ice on top of a whole continent here, will feed back and change the atmospheric circulation around it. So we, excuse me, we have an offline method for changing the topography of the atmosphere, because CAM does not actually typically run with a changing topography in any other case. So I'll talk about that a little bit more here. So just to mention surface mass balance and how that works, because we're the only component who deals with this. So CESM doesn't actually exchange any sort of fluxes with the atmosphere. All of those atmospheric fluxes go to CLM. And CLM accumulates precipitation and temperature over time. And then once a year on our coupling time step, it hands that information to the ice sheet as either a melt or a growth flux, which we call surface mass balance. And you can see in this picture, and I'm going to pull heavily from this paper, Mutendorf et al. And Günther tried to teach me how to pronounce it, I just failed. In the PI control, you can see that most of the ice sheet is growing over time, actually, and then the melt occurs along the edges. If you get into a high CO2 forcing regime, we have a whole lot of melt along the edges, but still some growth in the middle of Greenland here. So let's talk a little bit more closely about this atmosphere ice sheet coupling that I just mentioned with the topography updates. So on decadal or longer time scales, and we do run this ice sheet fully coupled in CESM for 100 to 300 years at a go, the topography changes of the ice sheet will feed back on the atmosphere over time. So what we typically do, we have sort of a complicated workflow that we've automated through some of the tools in SEAM, which is pretty nice, but it was tricky for our last fully coupled simulations. Every 10 years, we stop the model, and we run a topography updating script that takes about 20 minutes and updates the topography file, the phys field, and the subgrid 30 fields for CAM so that it can see those roughness changes of the ice sheet over time. So you can see over here the elevation difference between the early part of the simulation and say I believe this was about 250 years later. It's lost quite a lot of elevation change due to the high CO2 forcing, and that CAM sees at a much lower resolution here in the topography file. And then this is a calculated standard deviation of that topography change around the edges, so this is a roughness length in the ice sheet. And then this is what the surface roughness, the SGS, looks like and change over the course of that 200-year simulation. So there are other atmosphere ice sheet grid interactions, but they're a little bit even more removed because the precipitation does go through CLM and become a part of that surface mass balance. But that precipitation bias, Gökhan actually mentioned it this morning in his talks, has been a problem for our ice sheet. And this is the main reason that we haven't been running CESM fully evolving as a default option in CESM. It's because the atmospheric grid is still so coarse that it produces precipitation well inside of, oh, well, that was close. Here, do this. Well inside of the ice sheet here. And I apologize to Adam for not using his most recent paper, but you can see that as the variable resolution grid is increased, we actually do a better job of reducing that internal bias and keeping the precipitation more around the edges. So the variable resolution SE grid does provide a path forward for us, but that SE grid actually is not fantastic because we lose that tightening of the grid that the finite volume has up in the polar regions, and we actually experience a slightly lower resolution in Greenland with the fully uniform SE grid. So we'll see where this goes. There's definitely a lot of promise with the variable resolution grids that we've seen so far, and I know that Adam is going to talk about this more probably in the next session. So you should go see that talk. So quick mention of ocean ice sheet coupling. With Greenland and evolved, ice sheet coupling is generally one way because the ice sits on top of land. So we don't have a huge amount of interaction with the ocean in Greenland. But it becomes a bigger issue when you get into Antarctica because at that point, there's quite a lot of floating ice shelves, unlike in Greenland. So here's a picture really quick of Antarctica. And you can see that there's these very large ice shelves right here. And right now, CESM does actually, thanks to Bill, have the infrastructure to run fully coupled with active Greenland or Antarctica or both, which is really exciting. But there's still some scientific questions and some issues around the ocean coupling in Antarctica, because these are places where we actually are going to have to couple 4 different components of CESM in one vertical, oops, sorry, go back, 2-way. This way. Okay, and yeah, in one vertical column. So in one vertical column of CESM, you'll have the atmosphere, you'll have CLM taking in the precipitation surface fluxes and handing a surface mass balance down to CESM. And then CESM is going to calculate what the ice sheet shelf is doing and the ice sheet on that shelf is doing. And then it'll interact with MOM below it to try to handle the ocean salinity and temperature fluxes that will be melting the bottom of the ice shelf. So you can see that this is a very complicated scientific and software engineering part of CESM that we've been working on quite hard. So I'm just going to put up a quick list of our current and future work. There are quite a lot of variable resolution simulations that are being done right now that are very promising and exciting. Summer is working on some really cool mountain glacier stuff right now, which is even more interesting in the coupling areas. We're going to try to improve that topography updating workflow that I mentioned previously so that our next round of fully coupled simulations are a little less error prone with the offline. And we even talked a little bit about trying to find a way to bring in the topography updating workflow so that's actually online. You don't have to stop the model and do it every 10 years. I've been working right now on a project that actually handles negative ice fluxes when CESM's not fully evolving. We've got ISMIP 7 coming up. And if any of this sounds exciting to you guys, then you should come to the Land Ice Working Group meeting on Wednesday morning. So, thank you. Oh, Jen jumped up.
Antarctica, how do you handle the sea ice model and the interaction between the sea ice and CESM?
So right now there is no interaction between CESM and sea ice. However, we actually did have somebody come in and talk to us about icebergs. So you could potentially model giant floating chunks of the ice sheet in the ocean, and that would have to interact with the sea ice very directly. But at this point, once the ice leaves the ice sheet, it becomes part of the ocean, and we stop caring. Oh, I know. I feel it.
Thanks for the great talk. I have a very general question. So, from my limited experience, the topography will have like impact on land ice melting. So I was wondering, what's the current photograph influence in the CISM model?
I'm sorry, what?
Influence of topography.
The influence of topography?
Yeah, on land model, land ice melting.
Okay, so I don't have a specific result for differences between doing the topography updating or not, but basically what it comes down to is that there is large vertical, very, very tall cliffs along the outside of Greenland, and the atmosphere in the real world, it moves precipitation up against those cliffs, and the orography produces a lot of rain that rains out along the coastline. If that's not modeled correctly, then you end up with a whole lot of precipitation over the center of the ice sheet, which is very cold, and that causes the ice sheet to grow too large. It's unrealistic at that point. So that's why we're trying to get the topography correct so that we can get that atmospheric forcing on the ice sheet correct. Yeah.
All right, I think we'll move on to Meg Fowler now.
Okay. So today what I want to talk about is a way that we're looking at kind of advancing land-atmosphere interactions and their coupling in the community air system model. And the goal is really to move towards explicitly capturing the impacts of land surface heterogeneity on convective updrafts in the CSM. And of course, this is work I've done with a number of collaborators. I think I've listed most of you here, but if I left you off, I apologize. I really do appreciate everyone's input to this. So in the current versions of CESM, the way that the land and the atmosphere connect is really only through grid mean values. So we have surface heterogeneity in the land model, but we're passing just grid mean fluxes of temperature and moisture up to the atmosphere. But that isn't really ideal, right? We know from observations and large data simulations that even fine-scale differences in surface cover can drive really important impacts on the atmosphere. So it can impact where boundary layer cumulus clouds form, where rainfall occurs. And one of the main ways it does that is by setting up these mesoscale secondary circulations. So when you have these gradients of temperature and moisture at the surface, the atmosphere wants to kind of work to equilibrate those, and so it sets up an overturning circulation to try and do so. And even though those circulations can exist on just, say, tens of kilometers, they actually impact even grid mean things like liquid water path and interior link kinetic energy. So what we're proposing is a new strategy. So the idea here is to link existing representations of subgrid heterogeneity between the land and atmosphere model components. So in the atmosphere model, what we're really looking at is something called Club MF. So Club MF is a combined eddy diffusivity mass flux scheme. The idea is that Club can handle kind of small scale random turbulence, and then the mass flux part captures those larger variations in temperature, moisture, and vertical velocity that we'd ideally like to capture. And so this is somewhat of a simplistic representation here, but the idea is if we have a multi-plume framework, so we have 12 updrafts occurring within a grid cell, all those 12 plumes would initiate when the grid mean buoyancy flux turns positive. So it starts to heat up when the sun comes up during the day, buoyancy flux turns positive, you have 12 updrafts initiate from the surface. But they're initiating from a homogeneous surface, essentially, because it's a grid mean buoyancy flux. Those plumes are then going to grow into the vertical. They'll undergo stochastic entrainment until eventually the buoyancy flux hits zero and they stop growing. So this is kind of a nice scheme in that we do get kind of vertical heterogeneity from having a stochastic entrainment rate. So some plumes will grow deeper, some will terminate early, so on. But we can probably do a little bit better. We know that this is not a homogeneous grid cell. The land model gives us information on which different surface types might be present within a given grid cell. So here, for example, we have a grid cell that is made up evenly of grass, lake, irrigated cropland, and urban area. And each of those different surface types has a unique surface sensible latent heat flux, different friction velocity, et cetera. So when we're averaging those together, that's what we're using for the homogeneous case I showed you before. But we could, in theory, just pass that tile level information from the different surface types up to the atmosphere and then initialize those plumes over surfaces that are actually indicative of a grass patch or an urban patch. And so that's what we're proposing to do. And kind of the first order question is, does the atmosphere actually respond to this additional information on surface heterogeneity? So does it matter that what led to that mean value of buoyancy flux was this difference in surface types, or will the atmosphere not really care and just do the same thing as it always has. So to try and explore this a little bit today, I'm just going to show you a single day. This is a case study, and I'll show you single column results from SCAM. These are run at the ARM Southern Great Plains site for 2 days. We'll discard the first day for spin up and just look at what happens the second day. And I will put a caveat here. I've redefined the surface of the Southern Great Plains site. So the Great Plains of the US are pretty homogeneous, so the grid cell by default is just grass and cropland. What I've done here is redefine the surface that it's the grid that I showed you previously. So it's an even split between urban area, lake, grass, and irrigated cropland. From the atmospheric side of things, CLUB-MF is set to use 25 updraft plumes, and those are evenly divided across the 4 patches, at least for the most part. So we can initiate 6 plumes per patch. That gives us 24 updrafts. For the extra 25th updraft, that'll get allocated to whichever patch is warmest at that time. So in reality, we expect updrafts to be concentrated over kind of the warmer surfaces more often than not, so that's what we're mimicking here. And I will note I'm using a constant entrainment length. If you have questions about that, we can absolutely talk more. It is sensitive to that, but just to note that kind of a simple case study here. So when you look at how the atmosphere responds, one of the first things we can look at is just how many plumes exist at each level in each case. And so here on the left-hand side, oops, sorry, not the right button. Here on the left-hand side, we have the homogeneous case and then the heterogeneous case with our kind of orange shading. So as I mentioned before, in the homogeneous case, the 25 updraft plumes will initialize when grid mean buoyancy flux turns positive. And you can see that really clearly on this plot here. So somewhere around maybe 9 a.m., grid mean buoyancy flux is positive, all 25 plumes initiate. This is different than what happens in the heterogeneous case, where we kind of get a bit more of a gradual curve starting around 9 a.m., but then not until about 10 a.m. do we see all 25 plumes kind of really initiate. And it's a little hard to tell with this color scheme, but another important thing is what happens overnight. So in the grid mean sense, your buoyancy flux turns negative nocturnally, so no plumes are being initiated. But when we have a heterogeneous case and we're initiating plumes based on surface type themselves, what we see is that, in particular, the lake patch maintains a positive buoyancy flux overnight, and that's giving us kind of some level of convection happening nocturnally. So we're not as reliant on the diurnal cycle. It's a little bit more realistic. And it doesn't just impact kind of how many plumes you have, but even the characteristics of these updrafts in the atmosphere can change depending on how they're initialized at the surface. So here we're looking at, again, the homogeneous case and the heterogeneous case for this one day. And what you'll notice is that we sort of have a deeper maximum in terms of the near surface updraft speed, so closer to about 4 meters per second from 12 to 4 p.m. local time. And we can kind of dig into this a little bit more and look at each plume individually. So here I've averaged over that 12 to 4 p.m. local time window, and for each of the 25 updraft plumes, I'll just plot their profile of vertical velocity. So here in the homogeneous case, there's certainly some spread across plumes, but for the most part, all the plumes are terminating somewhere between 600 and 500 hectopascals. If we add in heterogeneity, though, we can start to kind of broaden that spread. And so if we take a look, for example, at the plumes that are initialized over that lake patch in particular, the lake tends to be a lot cooler than the surrounding patches during the afternoon. And so as a result, these are generally weaker plumes. They have a weaker surface vertical velocity, and they terminate much lower in the atmosphere, so closer to about 850 hectopascals or so. A few can grow deeper, and that's because we have that stochasticity and entrainment rate. And so you can still kind of see that stochasticity present, but for the most part, there's a sensitivity to surface type. And if we compare that with what happens with plumes that are initialized over grassland, grasses tend to be your warmest surface in the afternoon, we get quite a different response. So these particular plumes tend to be a lot stronger than what we saw in the homogeneous case, so touching about 6 meters per second in the around the boundary layer height. And they can extend deeper into the atmosphere as well. And so ultimately the atmosphere is pretty sensitive to how these plumes are being initialized at the surface, and that's playing a role in how the plumes develop over time. And just to fill it in, we have the irrigated cropland and urban initiated patches. And so what we're seeing is just really an increase in the heterogeneity vertically and of these plumes, not just in terms of their overall speed, but also in terms of where they're terminating in the vertical. And in case you're thinking, well, that's great, but I don't really care about the individual updraft plumes, those plumes do have an impact on important atmospheric variables as well. So here we're looking at the turbulent moisture flux and the turbulent temperature flux here on the right. And in the homogeneous case on top versus the heterogeneous case on the bottom, we see a pretty different behavior. So if we look at the turbulent moisture flux in particular, once those 25 plumes initiate, what we tend to see is a really sudden and strong increase in the turbulent moisture flux. So we get that peak around 9 a.m. or so. Whereas in the heterogeneous case, because we kind of have those plumes gradually growing in time, they're not just initializing as soon as your grid mean buoyancy flux turns positive, the atmosphere kind of builds up to its peak in turbulent moisture flux. It is a little bit weaker as well, in part because not all 25 plumes are growing to quite the same level. We do see more variability in that. So just a couple takeaway messages. One of the exciting things for us is that when we've paired ClubMF with the surface information from different surface types, we're actually seeing a pretty strong impact on the atmosphere. So the atmosphere is sensitive to surface heterogeneity in this case. It impacts the depth and the speed of the updraft plumes. According to surface type, we see that variation. But also those changes in plumes drive important shifts in larger scale atmospheric variables that are really exciting to explore further. And looking ahead, I think this ultimately opens up a lot of new possibilities and opportunities as well. So when we are able to explicitly simulate updrafts and downdrafts, you could imagine giving some horizontal advection between plumes and actually capturing explicitly these overturning circulations that are forming as a result of surface heterogeneity. And there's also the potential to communicate subgrid information from the atmosphere back to the land. So now that these plumes are maybe tied to a particular surface type, if they're more likely to form clouds or precipitation, we can pass that information back down to that particular surface tile and impact things like incoming rainfall, solar radiation, et cetera. And with that, I'm happy to take any questions, and thanks for your time.
Thank you. It's a very impressive talk. So my question is that since now you're in the atmosphere, you can also heterogeneity, and I'm wondering if you want to do regional or global simulations, how do you how do you plan to consider the interaction between different grid cells or columns?
Yeah, that's a really good point. I think it's something that's still very open to exploration. Right now, we don't really have a lot of communication in the horizontal. But if we are moving to things like 3 kilometers, ideally you'd have 2 grid cells and you get that communication in the vertical. So I don't have a fantastic answer for you now. I think it's an open area of development and research, but we are trying to think about it. Yeah.
Thank you. Good job.
Thanks.
All right. Awesome. We're going to go to Cheng Zhang now.
So, hello everybody. I'm Cheng Zheng. I'm a postdoc in Columbia University, and going to talk about something different. So, what happens if we perturb one component in CESM, which is the sea ice, and how the atmosphere react to it. So the title is Diverse Eurasian Temperature Response to Arctic Sea Ice Loss in Models Due to Varying Balance Between Dynamical Cooling and Thermodynamical Warming. So starting with the background, we're looking at the warm Arctic cold Eurasia pattern, which is shown in the middle. Middle here. So in the observations, we have the largest sea ice loss over the Barents-Kara Sea region during winter. This region also has the largest sea ice variability. And in the late 90s to early 2010s, we see a large decreasing trend of the sea ice, and at the same time, there's a cooling trend over the Eurasian continent. So that's the warm Arctic cold Eurasia pattern. So the question is the sea ice loss actually driving the cooling trend over the Eurasian continent? Well, this is still being debated in the literature because there are also studies suggesting that the internal variability or tropical forcing are also playing a role. They can drive both the sea ice loss and the cooling trend over the Eurasia. But if we look at in climate models, we can decrease the sea ice in the models to see whether we can simulate a cooling signal. So at least in some climate models, the cool Eurasia pattern can be simulated if we reduce the sea ice. So what we are looking at is a 2018 paper using 50-year CESM1 vacuum force simulation. So we can reduce sea ice by using 2 sets of AMIP simulations with prescribed sea ice and SST, and the sea ice in the 2 sets of simulations are different, so the differences between the 2 simulations is due to the sea ice loss. And we're using WACCM because there are studies suggesting that the stratosphere circulation could contribute to the cooling trend in the Eurasia continent. And what we see here is with this 50-year simulations, when we reduce the sea ice over the Barents-Kara Sea region, there is a cooling signal over the Eurasian continent. And the mechanism is the sea ice, or the sea ice loss, induce an anticyclonic circulation over here, which drives cold advection into the Eurasian continent, resulting in cooler temperature. And we can look at some longer simulations. On the left, we're using WACCM-4, 225-year simulation with sea ice reduction over the Barents-Kara Sea region. There is a cooling signal over the Eurasian continent. However, if we switch to WACCM-6 using the same sea ice and SST forcing, the cooling signal is gone. And we have tried to test whether this is sensitive to the sea ice and SST forcing. So we use different background SST or different sea ice forcing over the Barents-Kara Sea region in WACCM-6 in 7 different setups. And in any of them, we cannot find a cooling signal. So there must be some differences between WACCM-4 and WACCM-6. So to understand this, we use a linear regression measure to diagnose the temperature response due to sea ice loss. So what we do is we first find the linear relationship between the 2-meter temperature here over Eurasia continent and the circulation over the Barents-Kara Sea region. As we've discussed, the anticyclonic circulation over here can drive cold advection, which leads to cooler temperatures here. And with this linear relationship, we can then determine the cooling signal due to the circulation that is forced by the sea ice loss. So by utilizing this linear relationship, we find that stratosphere and troposphere circulation is driving a cooling signal over the Eurasian continent with this regression method. But with this regression method, there's also an intercept term, which is shown here. We interpret as the eddy diffusive transport of warming, or we call it the thermodynamic, tropical thermodynamic warming, because when we reduce the sea ice over here, the warming will be transported equatorward and partially into the Eurasian region. And if we sum these three terms up together, over here it matches the actual 2-meter temperature response very well, so the method works well. And if we apply the same method to WACCM-6, what we can see here is the circulation is still driving cooling signals over the Eurasian continent. However, the intercept term is way stronger. It's not only stronger in the amplitude, and it extends into the Eurasian continent. So it overwhelms the cooling signal, results in almost no cooling or even a warming signal over the Eurasian continent. So to briefly summarize the differences in the tropical thermodynamics term, or the eddy diffusive transport of warming, likely drive the differences in the 2-meter temperature response between WACCM-4 and WACCM-6, even if we use the same very similar forcing. And we currently don't know what's the model physics that's drive the differences, particularly for this thermodynamics term. We hypothesize that the land model changes in CESM2 could play a role because in CESM1, highlighted the continent is colder, which may reduce the diffusive transport of warming, but we haven't done any experiment to test this. Of course, there are other possibilities like the changes in the atmospheric component or the interactions between the atmosphere and the sea ice component. So I would like to briefly talk about similar analysis in CMIP6 models. So we are looking at the PAMIP models, which is a subproject of CMIP6. So different modeling centers use identical sea ice and SST to do their experiments. So the differences is only in the model. So 3 panels represents different sea ice forcing. And what we can look at is the first row, which is the temperature response. You can see that across different models with sea ice reduction, they don't agree in sign in temperature over the Eurasia region. Some models give us cooling signals, some models give us warming. What is consistent across the models is from the stratosphere circulation and troposphere circulation, almost all the models give us a cooling signal, although the amplitude is different. And for the thermodynamics term, or the anti-diffusive transport of warming, almost all the models give us a warming signal. However, for different models, the amplitude of the dynamical cooling and thermodynamic warming are different, and the spread across the models don't cancel when we add the terms together. So when we add all the terms up together, different models show different results over the Eurasian continent. Some models show cooling and some models show warming. So I can stop here and take questions.
I missed it, but I mean, we have pretty different sea ice climatology. Were all your runs with the CSM1 and CSM2, they had the same base state sea ice, and then you removed the same?
Yes. So for WACM 4, we only have one set of experiments. So the sea ice forcing is constructed from CMIP 5 simulations in WACM 4. And for WACM 6, we have different sets of sea ice setups, and one of them is the same as CMIP 5 forcing, or the same as our WACM 4 simulation. Okay. So basically, we have the same forcing in WACM 4 and WACM 6, and we see different signals.
Interesting, thanks.
Yes?
The first part of the talk.
Yes.
Aren't the direct model outputting these contributions?
I don't think so. Yeah.
Thank you.
Thank you.
Yeah. Hello.
Xiaolu, are you?
Can you hear me now?
We can't hear you yet.
Okay. Can you hear me?
Give us a second to troubleshoot. Hey, can you hear us in the room?
Oh.
Okay, we cannot hear you.
Oh, can you?
Next presenter, and then I can troubleshoot with her in the meantime.
Okay, let's do that. That's Hui.
Yeah. Hi, everybody. My name is Hui Wan. I'm from the Pacific Northwest National Lab. First of all, thanks to the session chairs for the opportunity to present. I would like to go back to the model development topic and present some of the work my colleagues and I have been doing in the DOE model E3SM. As we have seen, challenges at the interface is a huge topic, and in this presentation, I would like to focus primarily on the numerical aspects of process coupling near the Earth's surface in the atmosphere model. And at the end, I will mention the linkage to questions about the physical assumptions. So when preparing this presentation, Rich Neal gave us the guidance to talk about the plural assumptions of the coupling between model components, how sensitive these are to aspects like resolutions, etc., and how things can be done better in the future. So here is the homework we would like to turn in. The key messages I would like to deliver are the following. First of all, solving interface-related process equations in isolation and coupling those processes over long time steps can be problematic. The splitting-induced numerical errors can be very, very sensitive to process ordering, vertical resolution, and time step size. And thinking about the future, it will be useful to couple interacting processes more tightly, and part of this will require clarifying the physical assumptions at the interface. So now let me try to explain this in a little bit more detail. So the first figure I would like to show here is the seasonally averaged ocean mean, average over the oceans. So the atmosphere long-wave radiative heating profiles in the lowest 3 kilometers of the atmosphere simulated by ETHRSM version 1 using 72 model layers. A couple of years ago, when we started looking at certain time-stepping issues in the model, we noticed that these heating profiles often have big jumps of the values near the Earth's surface, which is a feature that was not seen in ETHRSM version 0, which used 30 model layers. At first, we worried that maybe the model had a bug or something, but after a series of simulations and analysis, we started to realize that these jumps actually can be considered good news because they are an indication that the model is starting to resolve the so-called surface layer, which according to textbooks is about the lowest 10% of the boundary layer. So after these plots, we started to notice more and more fields in which we see big jumps. For example, on this slide, I'm showing you something related to the dust aerosol life cycle. So these are box plots of showing statistical distributions of instantaneous values in dust source regions simulated by ETHRSM V1. And on the left, we have the dust mixing ratios that are passed as input to the aerosol dry removal parameterization. And then on the right, we have the mixing ratio tendencies caused by turbulent mixing. And in both cases, you can see that the bottom layer looks quite different from the layers above. And after looking into many of profiles like this, we realize that some of those big jumps are physical because they do represent the distinct features of the surface layer that are different from the layers above. And some of them I would refer to as justifiable numerical artifacts because the numerical schemes we use in the model by design can produce step function-like features, and some of them are actually okay. But then there are some jumps, or sometimes some part of the magnitudes of the jumps are caused by large and undesirable numerical errors caused by taking into account the different physical processes in isolation using sequential splitting, meaning that you think about one process, solve the equations, update the model state, and then move on to the next process, think about it in isolation, and then update the model state. And when we use long time steps and suboptimal process ordering, the situations can get a lot worse. So what are the impacts of those numerical errors? We have seen that those errors can make the model results strongly sensitive to the process ordering, to the vertical resolution, and time step size. Here is the first example. Because the radiative heating cooling rate profiles have those jumps at the bottom, we have noticed that depending on whether we apply those radiative heating cooling rates before or after deep convection, we can get a significantly weaker or stronger deep convective activity. And as a result, even if you look at annual mean low cloud fraction in the subtropical regions, the results can differ anywhere between 5% and 50%. And so thinking about the aerosol life cycle, we have seen that because the surface emissions of aerosols are considered as a separate process and in our model, and then this separate process does produce big jumps in the bottom layer, then depending on whether we apply the emissions before or after aerosol dry removal, we can have the dry removal rates in the dust source regions or the vicinity regions that are more than 50% different. And then if we look at the global mean burden and lifetime of the larger aerosol species, for example, dust and sea salt, the burden and the lifetime can differ more than 30% for dust and more than 50% for sea salt. So these were examples of jumps in the vertical, but then there are also big jumps in time series. Here I'm showing a figure from Sean Santos, who is in the room today, who noticed that in the E3SM simulated near-surface wind speed, there can be very strong unphysical oscillations, and then the magnitude of these oscillations can be very sensitive to model time step size, process ordering, and then the way how surface momentum fluxes are calculated and applied to the atmosphere. So what all those examples have made us think is that in older model versions, when the bottom layer in the atmosphere model was maybe 100 meters thick, we used to consider the so-called surface as the lower boundary of the atmosphere and a source of external forcing. But now, since we have bottom layers that are only about 20 meters thick, we need to start considering the so-called surface layer, which is a potentially resolvable feature in the atmosphere that has strong sources, sinks, and very short time scales. Because the sources sinks are strong and the time scales are short, we need to revise the numerical coupling of the related processes to avoid large numerical errors. So our work in E3SM, the lessons we have learned include we should really try to avoid sequentially split source and sink over very long time steps if one is significantly dependent on the other. And we have noticed that in some of those cases, just simply switching to a parallel splitting of source and sink can be an easy and a very effective remedy, but we think we can actually do better than that. In terms of our current work, what we are doing right now is to not only reorder, but also reorganize the parameterizations at the so-called TFIS BC, TFIS AC level, mainly the driver of the atmospheric physics parameterizations in the model. For example, recently we just made some code changes so that we can provide the surface emissions of aerosols as a boundary condition to to the turbulent mixing of aerosols, so that we can numerically solve those two processes together. And another thing we are currently in the process of doing is to separate different dry removal processes of the atmosphere and to combine the turbulent dry deposition with the turbulent mixing so that we can also couple these two processes together more tightly. And in terms of the numerical schemes, we plan to go beyond the simple sequential versus parallel splitting and explore more sophisticated coupling schemes. So when working on numerical methods for process coupling, our guiding principle is to respect and try to faithfully represent the physics described by the undiscretized equations. Therefore, before we make any changes to any coupling schemes, the first thing we want to ask ourselves is what the physics is, what is the physics that we are supposed to represent, and whether the equations will change in the near future. So this is one example that we encountered when thinking about aerosol dry removal, specifically the turbulent dry deposition. So we have been asking ourselves, should this process occur in multiple layers in the future instead of only in the bottom layer of the atmosphere? This is a valid question because the interception of aerosol particles by forest canopy is an important contributor to turbulent dry deposition. So if the atmosphere model's lower boundary is defined at the ground, then if you look at the canopy height plot produced by Michael Brunke, you'll realize that then some of the higher trees are now intruding in the second lowest layer of the model. But then some senior scientists told us that in the CESM community, it has been discussed many years ago that a different interpretation of the word surface could be the canopy top instead of the ground. So basically, in this case, we were asking exactly the same question as what was asked in the first talk of this session, which is where does the atmosphere end and where does the land start? So, and therefore, today's discussion and presentations were very helpful for us. But then we do expect that further down the road, we will probably run into more questions, conceptual and definition questions like this. Therefore, we expect that we will often go to our experts on interface physics and then try to ask them to help us clarify the physics so that we can design the numerical schemes appropriately. So that brings me to the end of the presentation. Thank you.
A couple quick questions for you. All right, don't go far. I think you'll be needed for the discussion. We're going to try Xiao Lu again.
You hear me?
Yes, can you hear me?
All right.
Wonderful. Okay, yeah, you can start sharing your presentation.
Okay. Can you see the presentation all right?
Yes.
Wonderful. Okay. Hi, everyone. Thank you so much for this opportunity. And my name is Grace. I'm currently a postdoc at Penn State. And I want to continue our discussion on the interfaces between the land and the atmosphere and focus on a relatively small but still important question about how phenology would influence land-atmosphere feedback. So you may wonder, why is phenology important? Well, phenology influences both the carbon cycle and land-atmosphere coupling, and particularly for land-atmosphere coupling, it directly influences the energy and water exchanges and indirectly changes cloud cover and albedo, and then it also modulates the energy versus moisture control of land-atmosphere coupling. However, phenology varies. So the interannual variability of one plant phenophase change can be as large as 2 weeks. And there's also been a spring advancement, which means that spring arrives earlier, on average by 1.5 days per decade. And in addition, there are large disagreements between the simulated and satellite-derived leaf phenology in climate models. So the figure here, in the figure here, the black line is showing the satellite-estimated leaf area index, and the colored lines are those simulated by CRM. And although we are only showing CRM or the CESM here, across the CMIP6 models, there has been delayed spring onset and longer growing season. And However, so this, I'm not sure if this is a good thing or not, but although we see large discrepancies in RAI simulations, the differences in GPP that resulted from these RAI differences are still large, but relatively small, a lot smaller than what we see in RAI. And therefore, we are because RAI also influences land-atmosphere coupling, so we are wondering to what extent would phenology biases influence coupling and what the influences are. And to do that, we first run the BGC mode with the data atmosphere forcing and get the simulated phenology. We then replace the prescribed satellite phenology in the model with those simulated by the BGC mode. So for the results I'm going to show, you are still seeing you are still seeing land-atmosphere interaction forced by a prescribed phenology, which means that we don't really allow phenology to change with the changes in the atmosphere. So we use a coupled land-atmosphere configuration with the climatological ocean conditions, and we modify the RAI, SAI, and vegetation height for each plant functional type in each phenology type. So the three lower figures here shows the three phenology type and then what plant functional types are included in each one. And the difference between the modified phenology simulation and the control run. And we run 100 years for each simulation. So for the results, here each panel shows the seasonal mean differences in surface temperature between each modified phenology run and the control simulation. And the crosses show the significant differences. So we found two distinct signals. First of all, not surprisingly, we see a significant decrease in surface temperature during the growing season, especially in areas with abundant soil moisture. And so what happens there is that the increased plant activity increases in evapotranspiration, and that lowers surface temperature through both directly modifies the Bowen ratio and then also increases low cloud fraction and it decreases surface temperature through cloud feedback. However, we also found a significant and strong increase in surface temperature in the late winter to pre-spring season, or to early spring season, or which we call the more like pre-growing season signal. And what happens there is that the increased plant activity would increase the absorbed solar radiation by vegetation, and then also decrease surface albedo, and both increases surface temperature directly and also changes snow melt and changes low cloud fraction due to that. And then so together, the increased absorbed solar radiation, the cloud feedback, and the snow albedo feedback all increases surface temperature. And so you see a strong temperature signal. And this is actually still the strongest and most significant signal, even if you average at the interannual timescales. And particularly maybe of interest to this group is that not only is this influence significant at the land surface and in the boundary layer, we also see that it propagates into the upper atmosphere. So here the panels are showing the differences in each variable between the seasonal deciduous and control run in June. So June is the month where we found the most significant influences. And so, as you can see, the changes, the influences on temperature propagates up to 500 hectopascal in temperature, and then up to 700 hectopascal in humidity. And so, I wouldn't go through all the conclusions here, but just want to echo the point raised in several talks, both in the afternoon and also in the morning, that land surface processes like how phenology emerges are important, and they need to be evaluated in a coupled context, and not only to the land model itself, but then also in a coupled context. So with that, thank you for your attention and sorry for the technical difficulties. I would also like to thank my collaborators for their contribution and the NSF for funding this research. And I'm happy to take any questions.
Any questions for Grace? Isla has one.
On the mean, I'm just wondering if you've looked at changes in variability.
Changes in vulnerability in which aspect?
I guess surface temperature on the timescales over which the phenology changes.
By vulnerability, do you mean like how the interannual vulnerability changes, or?
Yeah, or any relevant timescales, I guess. Yeah,
That's a great question. We actually haven't. I would imagine temperature vulnerability to increase, but no, we haven't looked at that specifically.
All right, thanks, Grace.
Thank you.
For having a discussion. And I don't know exactly, again, what Rich wanted to get out of this discussion, but I'm just going to open it up first and ask if there are any overarching comments or questions, or any questions that are burning for any of the speakers that we had that you didn't get a chance to ask. Dave?
Yeah, so I guess I'm Obukov most, and it came up several presentations, 3 or 4. And I guess I've been going to whatever presentations across the last few years, various workshops and part of the glass panel, and people are very upset with most, or some people are very upset. Not working well, and Gordon showed, that maybe we should move to something like the roughness sublayer if we have the capability to go to multi-layer canopy. So I'm just curious whether just the land community that's complaining about most, or are the oceanographers and sea ice modelers also hearing complaints about most? And if there's other thoughts out there for something, since it's been around for how many decades, it's been around. Stuff that I've been seeing is people sort of relying on machine learning, possibly move beyond it. But I'm just curious if anyone has any more experience on that. Very general question.
Yeah, I had a similar question. Now, Gordon.
Along the lines of what Dave is talking about, what struck me is looking at the sea ice presentation and also the ocean, is how old a lot of these parameterizations are. I didn't mention it in the CLM in my talk, but on the first slide I showed, some of our stuff goes back to things that Jim Deerdorf was doing when he was here at NCAR in the 1970s. And definitely Bob Dickinson with the biosphere atmosphere transfer scheme in the 80s. We're using 30-year-old ideas, in these models. And I got the sense that was also true for some of the ocean was citing really old papers, and definitely the sea ice. And so Dave, that's sort of getting to your point. We're using sort of old ideas in these models.
Does anybody Justin, that's who I was looking at you, and I didn't want to put you on the spot. Is the ocean as unhappy as everyone else?
I just mentioned at a recent meeting, people mentioned machine learning in relationship to this strong wind speed. I'm not sure whether it's directly it was at the most theory that was aimed, but just these estimates of the drag coefficient seem to be all over the place, and maybe I think the statement made was it could be revisited with the ensemble of sets of data, although obviously as they're extremes, it's not really but there might be some machine learning there.
another question I had, I shouldn't have let you sit down, Justin. Another question I had was whether it matters. So we know it matters for the land where the bottom of the atmosphere is versus where the top of the land is. We don't have a good answer for it maybe. But does the ocean, from the ocean perspective, does it matter where the bottom of the atmosphere is?
And I know it's relevant with respect to the waves and large waves. Then in the tropical cyclone conditions, it's very hard to define the interface and the spray, kind of foam layer. I think it does matter. I think people that know a lot more observations of these things could probably comment. I think in the more standard conditions, it's big.
Anyone else have a thought? I can say that when we were designing that new vertical grid, a prominent oceanographer was one who was driving us to put that lowest model level at 10 meters, suggesting that that was the right place to put it. No, I'm not going to mention it. You all know. All right, other.
I don't know much about machine learning, but it seems like the solution to a lot of these problems is adding more vertical resolution. How does that compare to using machine learning approaches to derive at more accurate solutions?
I'm not going to try to answer that question. Anybody? Oh, good. Gokhan's going to answer.
Problems, obviously, but aside from that, I mean, just coming back to what Dave was asking, should we actually do CSM form a task team or something? Because this topic keeps coming up, not just in this meeting, but in many other meetings that I attended, especially over the last few years. Everybody thinks that there are issues, problems, but I don't see a clear path forward as to how to address these. And I'm not sure, I mean, I'm hoping that we have the expertise within this community to tackle these challenges. So I don't know whether Dave has any ideas or whatever going forward, but everybody keeps bringing these issues up, and I don't see it being sort of addressed in a sort of systematic way.
Yeah, I think the suggestion that we form some kind of task team or similar group of people who are interested in these processes at the intersections of the components would be probably worthwhile at this point. I think my interpretation, listening to the talks, is that every component's dealing with the issue in their own way and hoping that the other components are going to take care of the problems on their end. And I think we're now at the point where we can't assume that the other components are going to take care of the problem because we're all mashing things together. I mean, literally overlapping where our physical parameterizations are happening without talking to each other. So I think something needs to happen. All right, any last comments, questions? Adam?
I just have a question, and I think it's an interesting one that a lot of us are thinking of. what does it mean when the roughness length scale hinges into ZBOT? What does that mean? What happens to our most algorithms in that situation? Because it is happening.
Yeah. I think that'll be at the root of this task team that Gokhan is forming. All right. With that, let's thank all the speakers again, and thanks everyone for participating.
Well, no. Well, I mean,
I don't want to do it, but this is the advance.
Oh,
This is
okay.
back. This is the pointer.
Perfect.
All right, we'll still have a minute. Yeah, that will come in once we start talking. And it's okay, we're just starting to, and Jim will be ready to jump in. Well, 5 minutes to get everybody.
We really don't have much to say. We probably have a minute or two of things to say.
Yeah. Okay, we're starting soon, in a second. People may come in. Maybe I start just slowly. Okay, welcome everybody to the next session. This cross-working group session is on ultra-high resolution and regional refined modeling as well as limited area modeling. And so today what we want to do is we want to first have 8 speakers that will present work that is happening on these different resolutions in the CSM model framework. And after that, we will discuss some results of a survey that we sent to you about a week ago. And we are really excited to have some results that we can present, and we want to have a longer discussion afterwards. So we want to ask our speakers to stay on time, and I give it over to Sophia.
Did you already say how long the speakers?
Yeah.
Well, let's see. What time are we at now?
Okay, so the first speaker, I guess we can bring up, and you.
Sure. Yeah. Our first speaker is Jim Hurrell.
Thank you very much. All right, thank you very much. I'd certainly like to begin by thanking Simone and Sophia for the invitation to present in this session. And I'm going to begin with developing scales, and then just say a few words about some possible pathways forward for the CSM project, specifically touching on some of the themes that we heard in Gokhan's presentation this morning. One of the things I want to mention is this talk is summarizing a workshop that we had on this topic recently up at Colorado State that was sponsored by NSF. So I'm sharing more than just my personal perspectives on this. Hey, I know how to work this, good. So, you know, in terms of motivation, I don't have much time to spend on motivation. Certainly, one motivation is that as changes in high impact weather events or extreme events become more widespread, demands for continuously updated and improved information about the potential for even more catastrophic changes in terms of extreme events is a societal driver for the need for high resolution models. And one example of that at the workshop we held is shown here. If you focus on the movie loop, this is a movie loop from the SCREAM model, DOE's SCREAM model that Ruby Leong presented, simulating an atmospheric river event impacting the West Coast. And Ruby really made the point about the societal relevance of understanding these phenomena, being able to simulate these phenomena well. But the other thing that Ruby emphasized, and that I want to make clear in today's presentation, is the opportunity to advance our understanding of this coupled system, the importance of high resolution for advancing both weather and climate science and weather and climate prediction. And this point was also emphasized by another speaker of the workshop, Falco Jute, who talked about some of the challenges in terms of tropical weather and climate and the importance of explicitly resolving convection for getting, for example, more realistic tropical waves, such as African easterly waves. And this is an example of a simulation from a high-resolution impasse simulation that shows you can get the amplitude and the phase speed of these waves well simulated in these higher resolution models. And this is one other point along those lines. Since I have to honor GOCON and the oceanographers, I thought that I'd show some slides that were presented by Christiane as well as Justin Small, showing some results from the IHESP simulations, where you see on the left-hand side the very high resolution, the mesoscale ocean eddies that aren't captured in the workhorse version resolution of CESM. And of course, simulating these mesoscale eddies is very important for a range of scientific questions. And then finally, in terms of an overall motivation, in terms of one of the presentations that Dave Randall gave at the workshop, and then followed up in a working group session that Kristen Rasmussen chaired, was that we do have a problem in our field, and that problem also presents an opportunity. And that is the schism or the divide between the weather and the climate communities. And I know this is a generalized kind of statement, but this is really pervasive. It's across universities often, it's across national research laboratories, it's across our entire profession. If you think of the lack of sessions at, for instance, a typical AMS meeting, really focusing on things at the weather-climate interface. And high-resolution global models can help us overcome that divide. And I think there's a lot of prospects and exciting opportunities by bringing the weather and the climate communities more closely together. So this was a motivation that we held recently for a workshop that we held recently up at Colorado State University. We had about 50 people in attendance, so it was a very nice sized workshop. About a third of those attendees were from NCAR. Another third were from the host institution, CSU, and the other third were from other universities and research centers across the nation. And the whole objective was to talk about future storm resolving configurations of CESM, the pathways forward, really to bring these different groups together, just to share who is doing what and seek opportunities for collaboration. And we're going to be submitting a summary of this workshop and the main findings for publication soon. And I just want to go through some of this in the rest of the talk. So one of the projects that GOCON mentioned today that you may be familiar with, but maybe not, is called EarthWorks. EarthWorks is a 5-year CSU-led project in close collaboration with researchers here at NCAR to develop a global convection permitting coupled model that is heavily based on CESM. What EarthWorks consists of is the impasse atmosphere non-hydrostatic dicore, the impasse ocean model, and the impasse sea ice model, along with other CSM components and capabilities. And the vision of EarthWorks is, at the end of 5 years, to be performing 3.75 kilometer fully coupled simulations that we can use to study both weather and climate on timescales from days to decades. EarthWorks will help us understand deficiencies of lower resolution models. One of the exciting things is developing improved parameterizations that work well at both ultra high as well as lower resolution parameterizations and physics that work well across scales. In the workshop, Dave Randall gave the presentation on EarthWorks. He's the PI of the EarthWorks project. He's in the back of the room. Gave a lot of examples of some of the early simulation results coming out of EarthWorks. I don't have time to really talk about that in detail, but I will say the early results are quite encouraging. We're encountering a number of issues really almost on a daily basis. And we are making improvements and we are overcoming those issues, and we're working with NCAR and the CSM community to overcome that, so it's going to be beneficial to the broader community. We're porting the physics to GPUs. We're almost done with that task, and I want to advertise that we have had our first functional release using CSM terminology of Earthworks, and you can see on that website there. In terms of some of the work on physics, I was chuckling this morning in Peter Loritzen and Julio Bachmaster's talk, talking about simulations of squall lines, but here is a simulation of a squall line. This is work that Bill Skammerock presented. He's a key member of the Earthworks team, looking at a one-day forecast of a squall line. You see the observed squall line, as well as the simulation with impacts with wharf physics. When we run the out-of-the-box CAM physics, we see that we get a relatively diffuse, unrealistic simulation of this particular squall line. But with some of the works that we've been doing, especially adjusting the microphysics in the model, running it with CAM6 physics as adjusted by the Earthworks team, we're now getting a much more realistic simulation of this squall line case. There was another presentation, and Gokhan mentioned this in his overview talk today, that Christiane presented on behalf of the team of PIs and co-PIs that you see on this slide about another vision for how CSM can get to ultra-high resolution modeling. In Christiane's talk, she emphasized that high-resolution modeling with CSM has hit somewhat of a barrier, and that CSM is missing an emerging opportunity to move to these scales if it doesn't move in this direction. So she gave a presentation about the ideas there, and the goal is to turn CSM into a viable tool for kilometer scale investigations by integrating DOE's spectral element non-hydrostatic core into CSM and working in collaborations with Earthworks to support high resolution ready CSM infrastructure and GPU ready CSM physics. So this is exactly the point. A lot of opportunities for multiple efforts in this direction to be working together to overcome some of these challenges. We also heard from Adam Harrington at this workshop, who talked a lot about the current work of CSM in terms of a variable resolution grid. Gokhan again highlighted some of the results from looking at the grid over Greenland and some of the applications for ice sheets and the simulation of the Greenland ice sheet. Here is another slide from his talk that really focused on the advantages of resolving the mesoscale eddies in the Gulf Stream region, fundamental changes to ocean atmosphere coupling in the North Atlantic, and you can see the much improved simulated precipitation fields as you move to higher resolutions in the variable resolution mesh. And finally, I just want to conclude in this limited amount of time with a couple of thoughts in terms of data challenges. Brian Medeiros gave a really excellent talk at this workshop talking about the challenges around data, both in terms of data value, data volume, as well as analysis on unstructured grids is a major challenge. And then validation, the relative lack of data sets at some of these high resolutions that you can do model validation with. As part of Brian's talk, as well as some of the working group discussions, a number of options were identified for dealing with some of these challenges, and you can see some of those options listed at the end of the screen. And then finally, I just want to conclude, Rich Loft gave a invited presentation and also led a working group discussion on some of the computational and the data challenges, really emphasizing by every measure, global storm resolving Earth system models. Costs are extreme. Current model throughput is too low. Simulations on climate timescales are too expensive, and data sets are very big. Tools are not really where we need them to be to do the analysis. I'm sure many of you are thinking about a lot of these challenges. And in the working group discussion, Rich had the working group come up with the following options for enhancing throughput. And he ranked them in terms of the participants of this workshop. A lot of discussion about the potential for machine learning methods for improving workflows at these high resolutions, porting, optimizing for emerging architectures, developing new numerical algorithms and the like. So I'm going to stop with that, hopefully staying within time, like I promised. But the key thing is there was a lot of rich discussions, and we're going to be writing a summary of this workshop up. And I'd be happy to talk to you in more detail after this session. So thank you.
Are there any questions for Jim?
Okay.
Thank you very much. Our next speaker is an online speaker, Lucas Harris.
Hello, can you hear me?
Yes.
Hello? Oh, thank you so much. Okay, can you see my screen also?
You're not in oh, there we go. Perfect.
Okay, great. Okay, so thank you so much for giving me this opportunity to talk. I want to thank the FE3 team for putting together a lot of these results, and also our collaborators at the Modeling Systems Division at the Allen Institute for Artificial Intelligence. And to briefly explain the title, I remember hearing back when I was a graduate student way back in the day that global storm resolving climate models is something that's going to be done in the far future. And actually, we've come to this point now where the community has been able to do this in a couple of different excellent efforts. So I'm very honored to be able to join this cooperative effort to get to this monumental achievement. So the model we're using is the X-SHIELD Global Storm Resolving Model. This leverages the developments of the SHIELD Weather to Subseasonal Unified Modeling System, as well as our collaborators in the UFS, the GFDL Climate Modeling Suite, and the rest of the worldwide FE3 community. X-SHIELD, the experimental system for high-resolution prediction on Earth to local domains, couples non-hydrostatic FE3 dynamical core to a SHIELD GFS-like physics. So it's simple. It's a global 3.5 kilometer resolution. No deep convection. We are using a scale-aware shallow cumulus scheme. This is a very efficient model, even including our coarse-grained I/O for machine learning purposes for our partners at the Allen Institute. This is 68 minutes per day on 18,000 stellar epic cores. And also, it's accurate. We're very pleased to have this excellent minus 5/3 spectrum and this beautiful 4 delta X cutoff. And I think the quote by Suki Manabe, our Nobel laureate here at GFDL, is most apropos in developing these very high resolution models. If you keep increasing resolution but don't make the model more complicated, I think you'll have a great time. And I really hope that, yeah, we can have a great time by doing all this. Originally, it's put together as part of the Diamond collaboration, and indeed, X-SHIELD is the latest in a 15-year-long series of FE3-based GSRMs at NASA and NOAA. That's a 40-day simulation forced by analyzed SSTs. But we had the opportunity, we had a computer at Princeton that allowed us to run this model continuously. So we've done these unprecedented 2+ year-long simulations, both in the present day climate and for a variety of perturbed climates as well. We're making this data publicly available through NODD, NOAA's Open Data Dissemination, and we're already putting it to use for both our machine learning purposes, basic science, and for this PIRE-CIRRUS project, an NSF-funded multi-center collaboration. A little bit about the mean climate. So yeah, we have 2 full years of simulation and 3 winters, it turns out. And so while some of these numbers are a bit preliminary, and indeed you have to keep the interannual variability in mind, that even with these 2 years of simulations, we are getting errors on par with the best of the CMIP class models. Here I show you radiative balance and precipitation, but also we have good statistics also for the tropospheric circulations and temperatures as well. And the most impressive thing here, in my opinion, is that this is all done again without a deep convector parameterization. The deep convection is all explicitly represented in this model. We can take a look at tropical waves and also the MJO. You don't need 3 kilometers to get a good MJO, but you can get a better MJO with higher resolution. We find that in the present day climate, we are able to get a good climatology of tropical waves, the Kelvin waves, the Eastern inertia gravity waves, the MRGs, and so on. Time scale is a little bit different compared to the reanalysis. We do get the time scale of the speed at which these waves propagate is right. And we find this interesting thing is that in our plus 4K simulation, where we warmed up the oceans by 4 degrees Kelvin uniformly, is that we see this distinct acceleration of the gravity waves, which is an interesting result in and of itself. And now we have this. We have these global storm resolving models, and there's been a lot of talk about what to do with them. And one of the things I really want to do is think about what new things can you do with the global storm resolving model that you can't do with an existing GCM, or you can't do with the regional convective scale model? And one of the things you can do is look at convection as a global phenomenon, explicit convection as a global phenomenon. We published a couple of papers on this, and one of the interesting things is how does convection change in a warm climate? And we see that continental convection, interestingly, is shifting towards higher latitudes in these simulations. Again, we only have, this is only showing 1 year simulation. The second year looks similar. This is explicable by the large-scale circulation shifts, but not by changes in the CAPE, in the amount of convectively available potential energy. We do see a bit of a reduction over land in the simulation. That's partially an artifact due to the fact that the simulation is increasing the SSTs, but not adding the radiative perturbation from the carbon dioxide enhancement. But this shift does have some interesting implications. The first thing that comes to mind is severe weather, but to me, the implication is here, what happens when precipitation shifts to the higher, to the more northern plains in the central United States, which is an agriculturally active region. We also have these 3 winters, and we're taking a look at the Western Snowpack as a consequence of this Western United States hydroclimate project that we've been funded to work on. We can take a look at our the 3 winters that are available here. One of the things we find is that the precipitation shift, when you get to increasingly high resolution, compare this to a 50-kilometer AM4, which is already a pretty good model. But you see that the precipitation shifts so it's properly over the mountains, over the Sierra Nevada, instead of over the Central Valley. I like to characterize this as resolution is paramount when you want to improve your orographic precipitation. One interesting thing that we found in our plus 4K simulations is that even though in the lower mountains, so over the Central Nevada area, that a lot of the snow does melt out in the middle of winter, it looks like that possibly California might be able to hold on to its snowpack in a warm climate, and that also has implications for water resources too. So, I mean, there's a big uncertainty bar on this. It's only a few years of simulation, but it is an interesting prospect. And then I want to sum up with just a few conclusions and also some challenges as people move into these higher resolution simulations. So kilometer scale climate modeling has arrived, and yeah, I could also talk about some of our efforts with variable resolution global models. I didn't have time to do that. And we've been able to achieve a lot with the model we've got, efficient, accurate, and relatively simple, as well as the fact that we had a nice computational resource to do this with. And again, our simulations are only limited, but this does indicate a lot of possibilities. And these GSRMs are powerful tools for studying convection precipitation worldwide. We also think about what new things you can do that you couldn't previously do with the existing models. And one of the ideas is we can start to talk more about how convective scales interact with large scales and synoptic scales. That's just important for GSRMs, but also for some of these large domain convective scale models, like the upcoming RRFS and some of the interesting things that our partners in Germany and the UK are doing. And finally, the way I like to characterize GSRMs is they're not necessarily a solution. They're not going to solve climate sensitivity because that's governed by very, very large eddy time scales for anvil clouds and stratocumulus. But there are a lot of new possibilities for what you can do with these pretty amazing models. So anyway, I want to thank our partners at the Modeling Systems Division, Princeton SEAMS, and the Allen Institute. And for more information, you can go to the websites shown here or on the title slide. Thank you very much.
For Lucas?
Okay, thanks everybody.
The question is that I have is, does high resolution do anything for the land surface modeling?
One of the big things we actually want to look at, and we had this nice workshop here a few weeks with the class project, is to take a look at the land surface heterogeneity, which we get a lot, we can represent a lot at these 3 kilometer scales we're running the global model at. And that has interesting implications for what sort of land surface heterogeneity is forcing for convective motions, as well as a number of other phenomena as well. So this is a potentially very valuable data set for the people using coarser resolution models in that sense. Plus, it also gives you more broadly a chance to study what's the effects of these heterogeneities on the climate, as well as also for urban scale simulation as well.
Thank you.
Thank you. Thank you so much.
We have time for another question, if anyone.
This is Jesse. I'm with NCAR. I'm just curious, like you showed those plots of like the climatological averages of temperature and mean and other plots, but I imagine loading 3 years of 3-kilometer data is not a trivial endeavor to generate plots. I'm just curious, like how much are there barriers to actually doing the diagnostics and analysis of this model output from just a
Yeah, it can potentially be slow, but we do have one advantage that a lot of our data has been output core screened natively. So our excellent collaborators at the Allen Institute actually put in this nice core screening mechanism into SHIELD. And as originally for the machine learning purposes, they're core screening the data to train a coarse resolution model on. But it did make a lot of analysis for us a lot easier. So basically we're loading in a 1/4 degree model instead of a native 3-kilometer model to be able to do this analysis. And it turns out to be fairly quick to do it in that case. But it is a bit of a challenge when we start to analyze the native resolution output. And tools like Xarray that can read in a chunk at a time and make it relatively user-friendly do help an awful lot. And I believe also ZAR is a popular tool for that as well. But there are quite a bit of challenges. Another big challenge is getting the data to our collaborators outside of NOAA who'd like to be able to analyze it.
Awesome,
But
thanks.
thank you. That's an excellent question.
Thank you.
Thank you.
Appreciate it.
Thank you.
Okay, please stick around, Lucas, so you can participate in the discussion at the end, if you can't
Absolutely.
stay online. Okay, great.
Thank you so much.
Thank you. Our next speaker is Han-Li Liu.
Thank you. So this is raise the model a notch, and this is a space weather study, and for a very short time run for WACA-MAX. Oh, okay, sorry. And so this is a WACA-MAX using the new die-core. It's a modified spectral element die-core with species dependence for the thermosphere. And it's on the cube sphere, and we're still kind of stuck with a 1/4 degree, not ultra high yet. But considering the complexity and also the extra levels, it's still a pretty expensive model to run. And the model for this particular case of Tonga Tonga, we're looking at initialization of a pressure perturbation following the work by Emoris et al. And which is a shallow water, global shallow water model. And this is a free run, so there's no meteorological constraint. And we really want to examine how good or bad or poorly we're doing with a high res in simulating, especially the response in the ionosphere, thermosphere. So this is a comparison with observations, satellite and model a few times or hours after the explosion started. And first of all, if you look at the shape, the general shape of the wavefront, I would say that they're pretty well resolved, and including the non-uniformity as a result of the refraction of the wave in a variable temperature environment. And maybe I didn't mention this is surface pressure perturbations, and this is parameter readings at different places, and it registered about between 100 and 200 Pascal perturbation, which is pretty well resolved in the model. And if we look at the vertical evolution of the wave, this is to look at the vertical growth of the wave amplitude of the vertical wind, zonal wind, and temperature. And in general, from the surface to the thermosphere, this is middle thermosphere. It's a growth of about 3 order of magnitude, and which is in very good agreement with the theoretical modeling that some 50 years ago by Lindsay and Blake, and this is in the case of with dissipation and ion drag and surface friction. So the result agree pretty well with the theoretical modeling results. And then this is not so clear on the screen, but these are 3 components, 3 wind components, zonal, meridional, and vertical wind. in the mesosphere, lower thermosphere, and upper thermosphere. So the main thing here is, apart from the wave front, the lambda nominal, lambda wave front with a speed of about 320 meters per second, we also see a slower wave here with about a phase speed of 250 meters per second. And that's from the earlier analysis or theoretical modeling by Francis, we know that's the so-called L1 mode. And so both modes are nearly dispersive and nearly non-dispersive. So they propagate, they can propagate globally. And it seems it's pretty well resolved by the model. And this is to look at the vertical structure, the phase structure of the wave. These are normalized wind perturbations, zonal wind and meridional wind, and vertical and zonal and meridional. So you can see that up to the lower thermosphere, the phase line are perpendicular to the surface, the wave fronts. And then in the thermosphere, because of the rapid increasing of the phase speed, of the acoustic speed, it started to be more like an internal wave, tilt into the propagation direction. And these structures are, again, very well, very consistent with theoretical modeling results. And this is to look at the observation, compare our model results with observations. This is ICON, which is a satellite measuring the wind in the thermosphere. And this is similar times after, for about 9.5 hours after the eruption. And we have wind perturbation in the thermosphere of about over 200 meters per second. I forgot to mention this is longitude and altitude. And you have the very large wind perturbation and with a westward phase tilt. And this general features are very consistent between the two. And this is a few hours later. And then you see the propagation distance from here to here are again quite consistent between the observations and the model results. In the interest of time, I'll skip this one and jump to the ionosphere results. This is the vertical E cross B drift as a function of time and latitude. So you can see that this is taken right at the longitude of the epicenter. And you can see the very clear wave propagation, the lambda wave mode. And also interestingly, because of the electromagnetic mapping along the field line, there's an almost instant response in the northern hemisphere. And there's a clear northward branch of the lambda wave. And this is to look at the total electron content perturbation. And you see clearly this global mode, L0 mode and L1 mode, and propagating globally. And also within the first few hours of the perturbation, you see very large perturbations in the electron content with much larger phase speed, 900 meters per second, approaching the phase speed of the acoustic wave in the thermosphere. But they do not show a global propagation. They decay pretty fast. Okay, and also you see a little bit of a hint of the conjugate effects in the electron density. So I'll just skip this. Comparison with observations in general is pretty good. And let's see if this one plays. It doesn't play, it seems. Let's see. I have. Is there a way to make it play? No, that's fine. I intended to have, sorry. It's a movie. I don't know if they can play it. No, it doesn't.
This is a
fine.
PDF file. We won't play.
Yeah, okay. It's supposedly a movie showing the animation, showing the surface perturbation along with the TEC perturbation, aligned very well, and a lot of nice and fine features in the simulation. Anyway, so this is a quick summary. Seems by comparing the modeling results with theoretical predictions and also with various observations, we can get I think with a 25 kilometer resolution, we can get the kind of salient feature of the response in the upper, in the middle upper atmosphere. So I'll stop here. Thank you.
time for a question.
Quarter degree to resolve this? Is this really the absolute minimum that you need, or could you go to like half degree or a degree would not
I
work?
think you can go further because there are some recent analysis results using very fine satellite measurement, saying that at least some of the transient response can have a horizontal scale, much finer than we are seeing here. So you can go higher, but I think the big picture, we can kind of get the big picture using this resolution.
All right, if we don't have any further questions, thank you. Our next speaker is Louisa Emmons.
Air quality, I listed a few of the people in ACOM, and but we were also very grateful to a lot of people in CGD like Adam and Patrick who have helped us greatly with getting things running. So in the past, air quality modeling has really required and has used different models for different scales of simulations, process models, or regional models for finer resolution, and global models for studying atmospheric chemistry and air quality. And so the goal of our Musica project, the multi-scale infrastructure for chemistry and aerosols, is really to combine those various processes into a single model. So one aspect of Musica is to develop variable resolution simulations, and another aspect is to treat the chemistry and aerosol processes in a more modular manner to facilitate doing different chemistry and aerosols in single models. So I'm going to talk about the first aspect in this talk. So we have a version of Musica we're calling version 0, which is CAM-CHEM, essentially, with the spectral element dicore, allowing for a variable resolution grid, such as this CONUS grid. And Musica version 1, we're currently developing using the MPAS dynamical core within CAM and adding chemistry to that. So CAM with MPAS has been functioning for some time, and we're currently adding chemistry to that and testing it out with this grid that has down to 3 kilometers over the Asian monsoon region. So as Musica version 0 was released as a comp set and resolution in CESM 2.2, and so it's available to users readily to download and run themselves. The CONUS grid is shown here as one of the standard resolutions that are available. And for people who don't want to run the model themselves, we run so far a couple of years of the CONUS grid simulations and made those available through the GDEX archive for people to download to look at and analyze for their own studies. So one of our science studies we've done, Wenfu Tang wrote a paper looking at fire plumes. So this illustrates how how do I do this? Oh, thank you. So this shows that a fire plume can be resolved in this CONUS grid with 14-kilometer resolution, which is comparable to the scale that the aircraft flight tracks sampled during an aircraft campaign in 2019. But it's valuable to have a, sorry, I'll get this. Have this in a global model because the fire plumes get transported far away from the original source region, and as shown in this visualization. We also would like to emphasize that we feel that Musica version 0 can be replaced, can replace WRF-Chem and other regional model simulations, allowing for fine-scale resolution over a region, but also then naturally incorporating the boundary conditions that are needed, for example, for simulating a fire plume. So this is an example from 2020 on the left that shows the fires in California that got transported, emissions plumes got transported into Canada and then carried back into eastern US. And for the red box shows the WRF-Chem domain. And so WRF-Chem would rely on a global model to provide boundary conditions to get the plume transported back in. And on the right is our forecast from WRF-Chem, and we use boundary conditions from WACM. So this is run from just a few days ago, from the Canadian fires getting transported into the eastern US, but they rely on the WACM boundary conditions to get that correctly. Another area that we've been studying is looking at air quality in Africa, and Wenfu Tang has made this grid that covers an entire cube face of the spectral element with a 25-kilometer resolution, and is starting to look at air quality. Their plots on the bottom show PM 2.5 at 2 sites in Eastern Africa. And there also is a WRF-Chem simulation, comparable resolution and similar emissions, and that we're comparing to, and see that there are, at one of the sites, there are significant differences between WRF-Chem and Musica, but at another site, they're very similar. And so in one case, maybe the meteorology in Musica is somewhat different, and the meteorological processes differ from WRF-Chem, but in the other case may be more due to differences in emissions that affect both simulations. And we're also comparing to satellite observations to evaluate the model. So there are a number of refined grids that are already available for use and are available at standard resolutions in CESM, such as the CONUS grid and the Arctic grid. We've also, a group has also been looking at South America, and so that grid's available for users. And we've put on our wiki page various other resolutions that groups have made and are willing to share. And I've created this grid on the bottom here that has 1/8 degree resolution over each of the 3 continents, and I hope to be running that as part of my first simulations on derecho. So we'll hopefully that will work. So there are more results being shown using Musica on Wednesday. Dusong Jo has created a grid over South Korea and has results from simulations with it looking at air quality. And Nora Beth Mariscal, a graduate student at Wayne State University, has made a grid over Michigan, and she has results also to show on Wednesday. So I just want to conclude with saying that we have a lot of tools put together. We ran some tutorials last year to help people get started with creating their own grid, or using Musica, or plotting the unstructured output. So we have the tutorials, videos are online, there's a GitHub page. We also have a wiki page that goes through all the various steps to get started with Musica. And we have a newsletter, email list, so we welcome you to sign up for that if you're interested. And that's all.
Time for questions? Okay, if there's no questions, thank you very much. Our next speaker is Adam Harrington.
How's this laser thing work? Well, I have it backwards? Oh, I do have it back.
So this is the top one is the pointer.
Okay.
This is the advance, the middle is the advance, and the bottoms go back. So you can go back first. Yes, and now the top is the pointer. Try that. And maybe you have to hold it and see if it doesn't work. There it is.
Okay. Thanks for bearing with me. I'm Adam Harrington. I'm going to climate applications of VRCSM. From glaciers to convection. Everything's using the spectral element hydrostatic dynamical core, so I'll only be going down to 7 kilometers. And these are all the colleagues that contributed to this work that I'm going to show. So you may be tired of hearing about my Greenland work, so let's get on with it. You know, the Greenland ice is obviously a very important component of the Earth system. 7 meters of global sea level rise locked in there, and it's very challenging to resolve at 1 degree. And so in 2019, Leo van Kampenhout led a study with a 1/4 degree refinement over Greenland and showed you can substantially improve the surface mass balance with that grid. It inspired me to develop 2 grids that CSM will now support, and we can all run out of the box. And Louise mentioned the Arctic 1/4 degree grid, and then this is the Arctic 1/8 degree grid. I have to get used to that. And then with that, we've also been working on now actually coupling the Arctic grid to the ocean, which Gokhan had shown a little bit of this morning. This just illustrates the integrated precipitation over Greenland and the integrated melt over Greenland in the bottom. The Arctic and the Arctic GRIS grids are the purple and magenta, and they improve both precipitation and melting. And I'm just going to talk about the melting thing. The precipitation, Kate had touched on why that gets improved. So it has a lot to do, in my hypothesis, it has a lot to do with the boundary conditions. And so this is the land surface data set that's used in 1 degree to 2 degree models that I simulated, and then the 2 Arctic grids over here. And you can see the coasts of, or the margins of the ice sheet are represented by these sort of mixed vegetation ice grid cells. And so the actual ice margin is subgrid. I had thought that that might be a problem because in the 1/4 and 1/8 degree, it's much more of a sort of a binary, all glacier, all vegetation grid cells that sort of make up that margin. And that's sort of illustrated over here, this schematic. And so what I did is I took the climatological melt bias in all of these grids, all these runs, and I mapped them to the 2 coarsest degree grids. And I used that ice mask to conditionally sample the melt bias by the grid cell ice fraction of those coarse grids. And you can see the 1/4 degree and the 1/8 degree in the purple and the magenta, the bias is the same regardless of the ice fraction, whereas in these coarse grids at smaller ice fractions, you have larger melt biases. And so I believe that the subgrid representation of the ice margin overestimates melting on the ice margin due to the vegetation portion overly influencing the mean state of that grid cell. Now, so we decided to try to simulate glaciers with VRCSM, so we built this HMA grid over high mountain Asia, sometimes referred to as the 3rd pole. Lots of water locked up in those mountain glaciers. And we ran 2 simulations. One was tuned and the other one is untuned. And what happened is that the glaciers were melting too much, even at 7 kilometers. And these are just time series of the SMB integrated over different regions of high mountain Asia. And the green is the first attempt and the blue is the tuned attempt, and the observations are up here at the top, which is more of a neutral mass balance. So we're melting too much on our mountain glaciers, even in the 7 kilometer model. And we think something similar to how the 1 degree views the Greenland ice sheet margin is kind of how the 7 kilometer model is viewing these mountain glaciers, which are only 1 kilometer wide. So they're subgrid features. And so you see this similar type of behavior where you sample the SMB depending on the grid cell ice fraction. You bin it by grid cell ice fraction, and you see for these grid cells that are representing glaciers as small fractions of the grid cell have more negative SMBs. And so we think something similar is happening there where we need a higher resolution boundary condition to resolve those mountain glaciers. So now I'm going to move on to more atmospheric circulation examples. And so this is the North Atlantic grid, quarter degree and eighth degree versions. And we ran sort of a perpetual year 2000-like simulation. And then we also ran some anomaly experiments where we put SST anomalies. Here is a gradient anomaly, and here's a warm anomaly. And we wanted to see how the behavior of the atmosphere changes depending on which grid you use to these anomalies. So 1 degree on the bottom, quarter degree in the middle, eighth degree on the top. These are latitude height transects over that North Atlantic anomaly. And what really sticks out is if you look at the eighth degree solutions, you have this deep heating in response to the anomaly, penetrates pretty far into the middle of the upper troposphere, and it's also poleward heating. And you see that in the gradient anomaly simulation as well. You don't see those in the quarter degree at all, and you see a faint hint of it in the 1 degree. And so what's interesting is that at quarter degree in these runs, the cold fronts start to become represented by these permitted updrafts, these resolved updrafts at the grid scale. But the warm fronts are still, most of their ascent is from the sort of large scale non-resolved updrafts. Well, when you go to eighth degree, the warm fronts start manifesting as resolved updrafts. And because they're a warm front, when you mix vertically in a warm front, it also moves heat poleward. And so you see actually a really interesting sea level pressure response that looks like the NAO in the eighth degree runs up here that you don't see at 1 degree, or you see a very diminished version. And then at quarter degree, it's just kind of something in between sort of, but also putting these lows in a different location than they should be at eighth degree, than they are at eighth degree. So lastly, I'm going to talk about the South America grid, which Luis had showed a picture of. This is Patrick Callahan primarily did this work. He did various levels of refinement from half a degree all the way down to 6 kilometer refinement. And this slide sort of shows a bias that's actually persistent regardless of resolution, and that is, if you look at the precipitation rates, this is just a half a degree. You have these sort of anomalous precipitation over the mountains, and you have this dry zone right here. And we think that this is spurious precipitation caused by the terrain following coordinates, and then the hyperviscosity operators are mixing along that coordinate. And so they kind of mix moisture over the mountain and can create spurious precipitation. Well, Patrick came up and did some magic and came up with a different boundary condition for the hyperviscosity, and he was able to basically remove, to a great extent, some of that spurious precipitation, and that dry, impinging tongue of dryness that was there is now gone. So that's a pretty interesting result. And then we also, I want to show just some results from the South America grid, or what resolution does to you. This is a diurnal propagating mode. It's in northeast Brazil, in this green box. You have precipitation sort of starting on the coast in the late afternoons, and it propagates westward overnight. And so this is a diurnal propagating mode. And so, yeah, it's shown much better in this Havmaler here. And you can see with various levels of refinement that you're slowly starting to resolve that propagating mode. And at 6 kilometers, you've primarily got your magnitude and phase correct. And so you have sort of permitted to resolve this feature, permitted this feature to be simulated in the 7 kilometer run. So I just want to end here. I don't actually usually ever get to my conclusion slide, but this is great. And, you know, just make clear that a lot of the improvements that you can get from variable resolution don't necessarily have to do with permitting convection. It has a lot to do with your boundary conditions. More realistic topography can facilitate more realistic orographic precipitation. Obviously, the land surface type resolving ice sheet margins, but at 28 kilometers or 7 kilometers, you're not doing it for mountain glaciers, but nonetheless important for the ice sheet margins, and you can get that at about 28 kilometers. Louisa kind of made reference to improvements in the emissions data sets for air chemistry type studies, and so that's also another improvement that you get at variable resolution. And then some other sort of milestones that I've sort of showed is that 28 kilometer, you're sort of updraft permitting, you can get these resolved updrafts, and you can start to simulate sort of elements of tropical cyclones, they look like them. You can start putting together cold fronts that are a manifestation of updraft elements, and you can start getting more realistic precipitation extremes. But it's not till 14 kilometers till you start resolving a significant chunk of the mesoscale. So this is the KE spectrum, and the 14 kilometers, the black run. So this is just some convergence experiment I did, and you can see a big chunk of that black line sits in the negative 5/3 slope, and so we call that mesoscale permitting. And then, as I said, you can get these sort of ascent and warm fronts. And then at 7 kilometers, you know, we're starting to permit these propagating MCS type features and getting more realistic diurnal cycle over land. So you don't need ultra high to do good science. And so this is what I wanted to sort of convey to you all. That's it.
One quick question.
Adam, thanks. So CAMSC is a hydrostatic model. I'm wondering if you have any, I mean, I agree that at 7 kilometers, CAMSC is sort of convection permitting. Do you have any ideas of how we might be able to assess whether the hydrostatic assumption is producing damage?
Once Christian gets the non-hydrostatic dicore in, then we can presumably do a pretty close to apples comparison of hydrostatic versus non-hydrostatic. But that's really hard to do because you now have an additional prognostic variable, vertical velocity, and so you have now explicit dissipation operators on that additional prognostic variable. So you can't just click a switch and say you're exactly the exact same as hydrostatic but non-hydrostatic. There's multiple changes in the model that make it difficult to compare, but we can try, and I think that would be, yeah, the easiest way is once we get non-hydrostatic SE.
Thank you. Our next speaker is Betty Otto-Bleesner.
Okay, so I want to thank the organizers. I want to talk about how we're starting to leverage high and variable resolution simulations with paleoclimate data to study weather and climate. So this is an exciting new future climate. So if we look at low resolution of versions of models, and the I here means we've added the water isotopes. This is the choice of many of the paleoclimate simulations done at NCAR. It's very useful for long simulations with components for long time scales like the ocean, land ice, biogeochemistry for transient simulations. But it's, if you look at the topography here, it's at 1 degree, it isn't resolving, for example, things like Sierra Nevada mountains. We now also have a high resolution version thanks to the IHES project, the NE120 that is a 1/4 degree atmosphere and a 10th degree ocean. So you can see in the top figure here that we do start to resolve things like the Sierra Nevada, not all the features, but at least do somewhat better. And the cost difference, though, is substantial. So at the NE30, the 1 degree atmosphere ocean, we can get maybe 40 to 50 simulated years in a wall clock day. At the higher resolution, we can maybe at least on Cheyenne, get about 1 simulated year per day. So you have to pick what you want to do depending on what you need to do. And in particular, as I mentioned, we have these IHES high-resolution simulations that have been done already, just shown here. On the right-hand side is they've done a multi-century pre-industrial, they've done several historical simulations, and they've done an RCP 8.5 to 2100. So we were very thrilled that we got one of these Accelerated Scientific Discovery, or ASD projects, on the new supercomputer in Wyoming, Duratio. We call it our Paleo Weather Project. It's kind of a past to future perspective. And what we proposed, and have just started, the simulations have just started, is to kind of look at this out-of-sample development and testing. So kind of understand the fundamental understanding of how extreme or elevated CO2 levels would affect extreme weather. So we have here, it's about 50 million years ago, what's called the early Eocene climate optimum. It has a CO2 level about 1680 ppm, and global temperatures are estimated to be about 14, 15 degrees Celsius warmer than today. We've also are going to run a Pliocene simulation for about 3 million years ago, which has atmospheric CO2 about what we were maybe 5, 10 years ago, 400 ppm, so kind of a medium warmth. And then the third paleo simulation / glacial maximum, very cold time period, big ice sheets over the northern hemisphere continents, CO2 levels of 190 ppm. The key for all of these time periods is we have low resolution simulations already. So we have an ocean that at least is spun up at low resolution that we can start all of these. So we can run 50-year simulations. We don't have to run 2,000-year simulations. For the geologists, this is great because it's a new paradigm of how they interpret their data. Instead of talking about means, some of their data may be representing atmospheric rivers or tropical cyclones. And as I said, we've just started, thanks to the great help of Jim Edwards and Jean Zhu. We're now running on Duratio. As of 2 days ago, I think we have 3 years of the Eocene and 2 years of the last glacial maximum. And they have increased by about 50% what we thought we could get as throughput. So it's 1.6 simulated years per day. So it's really quite reasonable to do these 50-year simulations. So as I said, we're just starting on this, but I'll show you some of the hydroclimate extremes that we would like to look at across timescales. This is a figure from the IHES model where they compare observations of atmospheric river, the high resolution, the 1/4 degree by 10th degree, and then the 1 degree. And you can see that the 1 degree model severely underestimates atmospheric rivers, while the high res does much better. On the right is just a figure that Gokhan showed you this morning. This is for a time period about 16 to 14,000 years ago when there was a lot of meltwater coming off the northern hemisphere ice sheets, these icebergs into the North Atlantic, much reduced AMOC. And there's a number of records here, in particular in the Great Basin here, high lake levels there, and also in California. So to be able to simulate atmospheric rivers and how they affect the hydroclimate during this time period will be interesting. Another really important thing about this resolution of the model is it's a 10th degree ocean. Models at low resolution just cannot simulate the coastal upwelling in the subtropical regions. But if you look at these figures here from Jean Zhu, if you look at the high resolution, the biases here in the coastal areas, particularly off, for example, California, the Baja region, also South America, are much reduced as compared to the low resolution version here. So we're starting to get coastal upwelling reproduce. And this is important for kind of understanding what happened in past climates and could be relevant to future climates. So this is a time period, the Pliocene, that we will simulate. And on this left figure here is all these proxies that suggest the southwest US was much wetter, higher lake levels in the southwest. Also in the middle here, proxies suggest much warmer SSTs off of California. Neither the models or the global reconstructions can reproduce this much wetter climate or these much warmer SSTs. So on the right side is just a sensitivity study done by Min Fu with CAM5, where he just artificially increased the SSTs here off of the California coast, and then he gets much warmer or much wetter conditions over the southwest US. And then he did an opposite sensitivity study, I'm not showing here, where he made it wetlands over the southwest, and then he can get much reduced kind of coastal upwelling winds. So there's this feedback loop between the upwelling and the wetter conditions. And just one last slide here. The other thing we're just getting starting into is to start using the variable resolution versions of ICSM. So you can see here on the graph on the left here that it's more expensive than the 1 degree, but not as expensive as the very high resolution. So some simulations that, in fact, Sophia has just is starting to look at using the CONUS grid to do paleoclimate. Can I say this one quick? Okay, just want to, and I know at either of these resolutions, the 12-kilometer of the variable is not quite for mesoscale convective systems, but we still can start looking at them. This was actually a study done with a low-resolution model, and it's looking at this cave here in Texas, Hall's Cave, which is a cave that when you go deep into the cave, they're able to determine that the sediments deposited there had to do with mesoscale convective systems. And they can tie that to differences in the land surface warming and the low-level jet based on both their sediments and the present day. So I will stop there.
Your questions for the discussion portion of the session. Thank you, Betty. Our next speaker is an online speaker, Yifeng Cheng.
Can people see my screen okay?
Yes, you're good.
Okay. Hello, everyone. This is Ethan, and today I will talk about hydrometeorology as well as biology in Alaska and the Yukon. So, this is part of NSF Navigating the New Arctic project, and this is also about institution collaborations where we collaborate with Indigenous Alaskans to estimate the climate impacts in Alaskan and Yukon rivers, fish, and communities. And under climate change, the Arctic is rapidly changing, such as increasing air temperature and precipitation, decreases in sea ice, and changes in seasonal snowpack. And so the climate change greatly influenced the inland freshwater system, so the Indigenous Alaskans heavily rely on them for subsistence fishing and transportation. And since the objective of this project is tangible to the daily lives of Indigenous people, it is critical to get them involved in the research process. And the left diagram actually shows the collaborative mechanisms in our study. And I want to highlight two things. The first is the knowledge co-production involves Indigenous community, the social scientists, as well as climate and earth scientists. In our project, we specifically recruited an Indigenous Advisory Council, as you can see on the top right corner, to help the project investigators make decisions about research design, analysis, and deliverables. In addition, The social scientists in our team actually lead the design of a climate information survey, as well as organize the Arctic River Summit with the Indigenous Advisory Council. And the Arctic River Summit is an in-person workshop to discuss the current and potential future states of Alaska and Yukon and how we can adapt. And the information collected from the survey and the summit has been used to guide some of the modeling decisions in the science team. And I would like to point you to Keith Musselman's presentation, which already happened this afternoon in the actionable science session. So for the modeling part at NCAR, we aim to produce a high resolution, which is 4 kilometers in this study, and high fidelity climate information for Alaska and Yukon. We use a regional Earth system model specifically designed for the Arctic, which is called the Regional Arctic System Model, short for RASM. And this model is a fully coupled land atmosphere, ocean, sea ice, and river routing model. And in this study, we specifically focus on land atmosphere interactions, and we use prescribed sea surface temperature and sea ice fraction data. We replaced the land model using the Community Terrestrial Systems Model, CTSM, for more comprehensive land process representation, and use Mesoroute as an offline routing model. So to increase the fidelity of the terrestrial hydrology simulation, we developed an optimization workflow for CTSM. And we conducted an offline optimization for CTSM using ERA5 meteorology, and mostly focused the optimization is focused on river flow and snow. And the optimization generally improves the hydrological simulations in Alaska, and the workflow has been recently published in WRR. We have finished the historical WRF CTSM simulations for water year 1990 to 2021, and it took roughly 4 months using the NCAR Cheyenne system and cost roughly 9 million CPU hours. And in this study, to examine whether the optimized parameters would deteriorate the coupled land atmosphere modeling, we examined the hydrometeorology and terrestrial hydrology simultaneously. We evaluated following variables, including the total precipitation, snow to precipitation fraction, 2 meter air temperature, evaporation precipitation ratio, terrestrial snow, as well as stream flow. And for the sake of time, we choose precipitation and stream flow as representative variables today. Before we dive into the comparisons with observational data sets, I want to show 2 simulated climatology plots for Alaska, which showing the historical mean annual temperature and precipitation. And the plots in this slide actually shows our simulation capture the complex Rift Valley pattern and onographic impacts on the precipitation and air temperature distribution. So first of all, we evaluated the simulated precipitation against 3 sets of data sets, including a probabilistic estimate ensemble, which is observationally based spatial estimate of meteorology in Alaska and Yukon, which is developed by Andy Newman. And the second is called PCIC, which is a gradient interpolation from observation. And the third is GPCP, which is a satellite-derived precipitation data set. And the map above actually shows the seasonal bias, and the lower map shows the distributions of the bias across the entire domain. But this map has too much information, so we mostly focus on so we use the bias for the winter and summer seasons when compared with the probabilistic estimate ensemble as an example. So the plot above shows the bias compared to the ensemble mean. And generally, you can see for most of the gray cells, the bias is smaller than 50 millimeters per season. And the lower plot shows the bias distributions for the 75th, the 50th, and 25th percentile and the mean value. And you can see the bolded number, which is the regional mean for different percentiles. And you can see this number is actually distributed around 0, which shows our simulation generally captures the precipitation amount well for each season, or for the winter and summer season. So for the terrestrial hydrology, we actually evaluated our simulation against 15 major river basins in Alaska. And in addition, we compared our simulation, which is from the coupled land atmosphere modeling, with the flow simulation from the standalone CTSM optimization. And our coupled simulations sometimes show better flow performances, as you can see here, such as Saftina and Tanana River Basin. But sometimes the river basin shows deteriorated flow simulations in the coupled front. For example, like Kuparuk and Colville River Basin, which is in the northern slopes. In general, out of the 15 major river basins, 9 of them show better flow performance in the coupled simulations than the CTSM-only optimization, and which is highlighted in the orange boxes in this slide. So, to quantify the potential climate impacts of hydroclimate in Alaska, we propose to use a method called pseudo-global warming. And this method imposes large-scale changes in climate system from GCMs on the historically regional climate simulation. This method is flexible in future scenario design and easy to interpret and avoid biases from GCM. In our study, we select 2 future scenarios, including medium and high scenarios, which are ensemble means across different GCMs from SSB 245. However, one big constraint about PGW method is its limitations in predicting projected changes in weather, storms, and extreme weather events. Therefore, we would like to conduct direct dynamic downscaling from GCM output. And we were also fortunate to get derecho as the allocation, which is about 71 million core hours, which allow us to select 4 ensemble members and conduct 30-year historical and 30-year future simulations for each ensemble members. And we select 4 ensemble members from CESM 2 large ensembles. And we are currently preparing for this run and will kick off the run very soon. So the main takeaways is we actively engage Indigenous participation in this project and make sure that Indigenous knowledge is included, valued, and protected. And we developed an optimization workflow for CTSM, which is available in GitHub. And we are trying to make our climate data more accessible back to the Indigenous communities as well as our science community. So the next step is trying to wrap up the PGW runs and kick off the direct dynamic downscaling very soon. Thank you.
In the interest of time, please save your questions for the discussion. We'll have our last speaker now, our last invited speaker, Jim Edwards.
Hi, thanks for having me provide a software engineering perspective on high-resolution modeling. I hope I can do it justice. Ultra-high resolution or kilometer scale modeling has some, positive aspects, and we've heard a lot of them here this afternoon. Obviously, improved spatial resolution enables researchers to investigate localized phenomena. Fewer parameterizations are required because you can resolve more processes. It may lead to improved understanding of climate feedback, but there's some costs here. It's extremely computationally expensive. It's really limited to a few scientists and institutions with HPC facilities. And there's a significant investment required to port codes to emerging and potentially short-lived technologies. If we just look at this current state of GPUs, we have OpenACC, OpenMP, CUDA, the Fortran now has a capability, but these languages are not compatible with all the GPUs. Some work on some GPUs, others work on other GPUs. Which ones do you invest in? Yeah. Oh, I know what I wanted to say. This morning, Everett spoke about community and talked about the importance of community to CSM. And then Julio and Peter talked about the importance of maintaining operations at lower resolution. And we saw in the panel discussion a very good example of communities that we want to continue to support. I don't think that ultra-high resolution kilometer scale modeling necessarily supports our communities. Oh, what's it doing? It's going backwards. Yeah, I got it. So in around 2015, the DOE, Department of Energy, forked the CESM model and created E3SM. They've invested an incredible amount of money over the several years in E3SM, and they have about 15 FTEs of software engineers working on that model to do high-resolution modeling. They also have a lot of hardware. These are numbers from recent HPC Top 500 list. Aurora hasn't yet made the list. Frontier is the first exaflop machine. They have Summit and Perlmutter. And Polaris and Frontier TDS are test systems for the larger Aurora and Frontier systems. But those test systems are both also still bigger than Duratio, which is what we have at NCAR. We should focus on the strengths of CESM in our future development. We have a large and diverse user community. We should support that community. We're portable across a wide variety of platforms of all different sizes, from laptops to the biggest supercomputers. We have an ability to create a wide variety of experiments useful to many different disciplines. We've been a leader of the CMIP experiment since '96 when it was CSM. And we've spawned a large number of climate modeling efforts around the world. Norway, Italy, I saw Taiwan this morning was using CSM. There are a lot of communities using this model or variations of the model. And we're bottom-up, science-driven development, which I think works really well. Oops. CSM should complement and extend the capabilities of E3SM, not try to compete with them. And in order to do that, we really need to strengthen the CSM infrastructure. Improved and easier user infrastructure will lead to a larger user base. Gokhan talked this morning about the GUI that's been introduced to CSM. Unfortunately, that GUI has, had been developed by one software engineer putting in maybe 20% of his time, and that time has been taken for other projects now, so the work on the GUI is effectively stopped at this point. We have an I/O subsystem. It has capability to do asynchronous writes and data compression, but that capability really needs to be developed further before it can be implemented in the production model. Our post-processing and data analysis subsystem, I'm sorry if I hurt anyone's feelings here, but it's a mess. It's a total disaster. We really need to refocus on post-processing tools and data analysis tools. We're using some workflow tools in seasonal and subseasonal forecasting. Those tools deserve a lot more work. They really make the job of running multiple ensemble members a lot easier and should be supported. And we need more ensemble tools. Right now, our idea of running an ensemble is to run 50 copies of the model and then figure out how to put it all together and make the ensemble plots and stuff. We should have tools that are specific to that project. We need improved interfaces to data assimilation components. Fault tolerance we've been talking about for 20 years. I don't know if we've done anything about it. We should introduce on-demand tutorials and improved user support forums, not just for new users, but for advanced users as well. I think that would be really helpful. And we should improve portability and use of containers in the model. And I also want to mention that the Earth System Modeling Framework, it's kind of fundamental to CESM 2.3. It's the backbone of the model. And currently, our Earth System Modeling Framework team is housed at NCAR, but funded mostly by NOAA and other projects. We need to redouble our efforts to support them. And nearly all of these improvements will also help with the high resolution and kilometer resolution modeling as well. I'm running out of time, so we'll go on. Let's see. By emphasizing the growth of the user community and improving accessibility of CSM, the model can have a broader and more significant impact. Enabling kilometer scale modeling may be valuable, but it should be pursued in a manner that aligns with the goal of expanding the user base and fostering collaboration and making CSM a widely accessible tool for climate research and applications. Thank you. Oh, I forgot. Go Nuggets.
Quick question. Discussion. Okay, now before we get into a community discussion to end the session, Simone and I just want to, summarize the survey results that we got as a part of this session.
Yeah. So thank you, all the speakers. I think that was amazing. And what we tried to do in this session was really get an overview about all the things that are going on. Not only, we do have our low resolution model for many years, but now what is actually in the last few years going on with high resolution in the global scale, ultra high resolution, regional refined, and also area limiting. And we heard about this all. We tried to get together talks that encompass all what is going on, but we realized we couldn't. Because there was so much going on, we realized that we should do a survey that actually serves you, and we send it to you to say what is actually happening and who is interested in high resolution modeling. And that's what we want to go over here quickly and then have a discussion. And so I give a quick overview of the survey on the different 3 parts that we asked you. That was the ultra and high resolution modeling, variable resolution modeling, area limited modeling. Then we designed a Venn diagram that Sophia will go over with benefits and shortcomings that we kind of identified in the survey, and talk about community resources and go to the discussion. So this is a general overview. And we, up to last Friday, we got 62 responses, which we thought was really good. And we were also happy to see that all the working groups had responded to our survey. Some more, some less. Obviously, the atmosphere is quite a bit of a contributor here, but all the working groups, also the software engineering working groups. The other thing that we saw is that you can see here that we can actually, we did cover all the areas. So global, ultra, and high resolution encompasses everything that is lower quarter degree, but we also identified that about half of the answers that we were getting were actually at or below 3 kilometer scale. So there is quite an interest in the ultra high resolution modeling. We have interest in all the other regions, with the top is the regional refined here. The other nice thing is that we have a lot of interest, especially also from early career. More than 50% is early career, so grad students or early career scientists here. And then for the ultra high and high resolution modeling, what we can point out is here on the bottom right. The pointer doesn't. Oh, I see. That's the problem. You have to. Yeah, so actually, obviously, what is interesting is to see the top interest is in the surface climate and the convection here, but also land surfaces and ocean surfaces exchange. We do see that a lot of people that have responded, at least over 60% have already experienced with this model framework. Going to the next, the area limiting model version, we do also have a lot of experience in the group that answered. And again, it is mostly that people like to look at the land surface hydrology and exchange land atmosphere. And finally, global grid with regional refinement. We do actually have the most interested people that haven't yet started on this. So there's a lot. And one thing that is interesting is that, again, a lot of land surface hydrology, and here top is chemistry and aerosols. And what we can see is that there's a lot of common science questions that are investigated. And Sophia, you want to do the next part? Thank you.
Yeah, this slide is all just to say that there was a ton of scientific overlap in the processes and features that people are looking at with these 3 high-resolution approaches. And so it was difficult to come up with like a Venn diagram of the scientific applications. However, we tried, regardless of scientific application, to come up with sort of a Venn diagram of the main benefits that each of these 3 high-resolution approaches provide. So I think we've heard a lot of this already today. But the reason people use high-resolution modeling is because it improves many processes compared to traditional low-resolution simulations. And so this allows you to resolve a lot of processes you wouldn't be able to otherwise. You get closer to the scale of the observations, and this allows you to make more meaningful insights about community impacts on a local and regional scale, which has all sorts of implications when you think about business and policy and planning and agriculture. But then there are some unique benefits to each of the 3 approaches. So first, with global ultra high resolution, you're explicitly resolving traditionally parameterized processes on a global scale. You also get a fully coupled Earth system at high resolution. Shared benefit with regional refinement is that you get that 2-way interaction between large-scale climate and fine-scale mesoscale processes. But unique to global with regional refinement is that you're capturing that regional information at high resolution with this physically consistent exchange with a low resolution global model, so you're saving resources there. A shared benefit between regional refinement and area limited is that, these are both cheap compared to a global high resolution simulation, and you can focus your resources on your region of interest. But then some benefits that are unique to area limited is typically these models can be more rapidly developed and tested. They can achieve sometimes higher resolution in your region of interest compared to a global simulation, and they also can be cheaper than a global simulation. Here's a similar Venn diagram for the main shortcomings of all these high resolution approaches. So an issue that came up from people across the board was that these simulations are expensive, they may not be able to run them as long as they would like to, and they may not be able to run as many simulations as they would like to. So your ensemble is sacrificed. You can't quantify uncertainty the way you'd like to. Also, generating resolution-specific input files is a challenge of all these 3 approaches. With global ultra high resolution, this is the most, take that issue that's shared and amplify it, because these are the most expensive. You have to run the shortest simulations, and you have to run the, fewer simulations. It produces the largest amount of data, and it's the least accessible approach at the moment. A shared sort of issue with regional refinement is that typically global models have longer development and testing cycles. A big issue that came up on the survey is a question of scale dependence of many parameterizations. This needs testing, and it's also highly uncertain. Some unique shortcomings of regional refinement are that you may lose some information between that outer low resolution domain going into this region of refinement. And also sometimes if your grid is not properly refined, you can get artifacts due to that region of refinement in your simulation. And then some shortcomings unique to area limited are the lack of that two-way interaction with the global system. You have to account for global model biases superimposed on regional model biases, and also, you need to generate those inputs at the domain of your model, or at the boundaries of your model. So after that brief overview of the whole survey, we asked people for resources that people found useful, and also what do you need in terms of community resources going forward. So some really common ones that came up were CESM Forum, the CISL Python lectures, very useful to people. Musica was a really useful resource for people. But also most people mentioned that specific members of the atmosphere model, chemistry, climate, ocean model, and ACOM were critical to their process. Then some common needs that came up, which is kind of highlighted by these resources, is that people want more comprehensive online technical documentation and outreach so that the community is empowered to do this work on their own without needing that connection to the specific expert. Many people brought up wanting kind of standardized scripts for post-processing data, more distributed resources, particularly for ultra-high resolution modeling, and then more software engineering support. So also some ideas that were brought up is an extension of CESM tutorial dedicated to high resolution, and potentially a VR CESM 2 workshop. So with that, now we want to get to the bulk of what we're excited about with this session. So we want to invite our invited speakers to the front. If you will come up to the front, that would be great for our community discussion.
No surprise.
And also the first part of this discussion, as you see, these are kind of some, we don't want to necessarily force any discussion to go on in this session. We want it to be as free as possible. But first off, if anyone has any remaining questions about any of the invited talks, feel free to ask those questions now. And also, what did you think about the Venn diagrams? Did you feel that captured your experience in high resolution modeling?
I can go back if you want for now.
Yeah.
Monica.
Are we opening it up to?
Yes.
Oh, yeah.
And I can go back to the questions.
All right. So I guess I have kind of a comment with a question wrapped into it, just because I'd like to, open this up to discussion. I think that, going off of Jim's talk, one thing that is maybe absent or not explicitly captured in the Venn diagram with respect to shortcomings of a lot of the high resolution capabilities is accessibility, right? And community-oriented modeling. Because as Jim pointed out, there's a lot of communities that in efforts related to actionability and climate justice, we'd like to partner with. We'd like to not only provide them with data, but also provide them with tools that has usefulness and usability for the questions that they want to be asking. And a lot of these communities are incredibly resource constrained. And so I guess one consideration is that as CESM moves of things like actionable science and also climate justice, how are we going to appropriately balance those considerations with continued CESM development and things like high resolution, where there might be inconsistencies between making model development decisions that are for increasing justice, but decreasing kind of the new technological capabilities that might be opening up to resource-rich institutions.
And we invite the panelists, anybody who can open the microphone and respond.
I wasn't putting you on the spot.
Oh, and if your speaker isn't on, there's an on button for the...
But anybody in the room can also respond if you have an answer to Monica.
I don't know that I can respond perfectly to that question, but I mean, I think one of the things that I try to keep in mind is, this isn't a discussion about putting everything in the direction of ultra high. It's what is the niche that the CSM community on that way, and there's many challenges. We've heard about that today. We've started to discuss that. Jim's talk was raising a number of the challenges, and I agree with some of those challenges. But, the CSM community, the strength of the CSM community is how diverse and broad it is. And I think that presents a lot of opportunity to really leverage a lot of expertise out there in the community and do things, some of the comparisons to E3SM, cost and all of that, I'm not sure, to be honest, is a fair comparison, right? Because you mentioned that the strength of CSM is the broad community, and that community can be leveraged to develop some of these kind of capabilities. And I think there are gaps. There are a niche to fill with ultra-high resolution modeling. It's not everything. There has to be a balance. But I think it is an important, capability. And this does not address the question about the resource limitations of all the user bases, especially, your comment about having people actually use those models. I agree there's challenges, but things can be done, through bringing the community together, identifying some high priority kind of simulations to be done, and making those data sets available broader community to look at, or the kind of things that can be done, at least as there's real challenges. It needs to be an ongoing discussion. But I just want to see all of the challenges, damp the enthusiasm that a significant part of the community has in moving toward ultra-high resolution. So, just a comment to try to get the discussion going a little.
Yeah, great. Is this better?
Just to add to what Jim said, the CSM community develops models, but the CSM community also uses models, creates simulations, shares simulations. You think of the lens, or we have a number of other ensembles. We are always putting out, all of us, and not just those at NCAR, but the whole community is sharing simulations that can be used. So it's both, it's development and sharing these simulations.
Yeah. Oh, it's not on, I think.
Thanks for the presentation. Stand closer so you can hear me. Kind enough to give me a microphone. So I'm the program manager for LEAP, the Science and Technology Center devoted to artificial intelligence and climate modeling. There's also a couple of other big projects going on in that domain. And, one thing that's kind of interesting to think about is, they routinely use high-res simulations of one sort or another as a training set. So there's one sort of obvious synergy between the ultra-high resolution thing and the machine learning thing, which, as far as I can tell, those are the two big things going on right now. And I don't know which of them is bigger. Certainly, if you look at the effort that's going on at NVIDIA, you could imagine that there's a lot of competition from that side in terms of who's bigger. They're also better able to utilize the new architectures, because these GPU machines, I think, use technologies that are primarily designed for these kinds of AI applications. you know, it would seem to me that NCAR could be a really nice crossroads here, you know, where you're doing the conventional model, you have access to people who are doing machine learning with the intent of improving parameterizations at that sort of 1 degree scale, so you can do the long integrations. Large ensembles aren't a problem at that scale. You can characterize the structural uncertainty because groups all over the world are doing that. You know, at the same time, if you go into the high-res kind of domain, either through CESM or through the large 80 simulation models that you have at NCAR and other resources like that, that you know, you could combine information from those kinds of simulations with the machine learning to inform models that are still first principles models and can be run, you know, out of sample, you know, taking advantage of the fact that you can do quite a few of them and do quite a few different things. So, you know, has there been any discussion within NCAR, you know, that you're aware of as to how these things can sort of, you know, interact with each other constructively?
Maybe the mic works. We can try.
It sounds like it works.
Yeah, you keep it close and then.
Okay, keep it close, like that? Okay. All right, Simone. I'm not going to answer that question, but I'll refer back to Betty and Jim Hurl's question, comments. We are working, I'm working with the other niche model at NCAR, the WRF model or the empath model, and we are creating a data set for South America that was referenced by Adam Harrington. Julio Bachmeister and Patrick Callahan are working on comparing the variable resolution to the WRF model output, and we're making that data available to everybody. So I think this is, I agree with your comments. Not everybody can do this. This is resource limited, so we've done a limited domain over South America and North America, but making the output available to everyone who can't use it. And we've got over 100 people in our affinity group, so it works. Thank you.
Yeah, I think we just go with Coca next, and whoever wants to speak here can raise his hand next.
Answer Eric's question, I guess, but I mean, if you look at the
Can you go closer to the
CSM Science and Strategic Plan, indeed, we are taking advantage of our machine learning sort of, well, projects that are led to CESM. That's the M2 lines, LEAP project, HPE, as well as NVIDIA. So I mean, that's part of the CSM strategic plan to essentially take advantage of all of those in collaboration with industry and university partners. And in fact, the next session right there in the South Bay is talking about parameter estimation, taking advantage of machine learning approaches. And I also agree with what Jim said, and that was one of the outcomes of the CSU workshop on high and ultra-high resolution modeling. I think there is recognition in the community that ultra-high resolution cannot, I mean, we can't really get climate scale simulations, but there's so much science that we can learn by looking at even short, I mean, I don't know, order a year or two simulations in terms of air-sea flux exchanges, improving parameterizations at process level with ultra-high resolution models. And as I this morning, I like to use harmonization of low-res, high-res, and ultra-high-res simulations so that we can learn from each other and bring all of those together. And it doesn't get many university colleagues or others people are already working on those, and we can essentially, in a collaborative way, take advantage of what's being done rather than essentially saying that, well, we can't do that or we can't do this. But we can essentially try to come together. And that would be sort of my approach, and that's already articulated in CSM Science and Strategic Plan as well.
I did, actually. I think I agree with you that we can do all these things, but we need to do it in a smarter way. For example, The IHESP, the ICESM project is currently stuck at CESM version 1.3, which is a completely different model than CSM 2.3. And so software engineering ends up supporting two different model infrastructures. And to me, that's a real waste of resources. We chose not to bring that high resolution component into CSM 2.3 because it was going to be too expensive to do it. But now we are stuck with this expense of supporting two different models, and I'm not sure that expense is less than it would have cost to bring the isotope models into CSM 2.3.
Yeah, I was just going to make a very quick additional comment, and I'm not an ML expert, but one of the things Gökhan mentioned, the workshop that we had with people interested in ultra high resolution modeling across the CSM community. Not that 50 people is representative of the entire community, but one of the really exciting things is machine learning also not just for emulators of physical processes, but for as a really valuable tool in terms of dealing with some of these data challenges well and post-processing challenges as well. So I just want to put that flag out there that I think there's a lot of potential applications of machine learning to the ultra high resolution modeling challenges.
I'll just, I think this, and I'll see if I can articulate this correctly, but I think this sort of piggybacks off of some of what Jim said, but there's also a bit of a disconnect when we talk about kind of like accessibility, especially at the user, I'll say this coming from a university perspective. So obviously running a 3-kilometer global MPAS simulation is not really feasible for me on a university cluster, but we routinely run 3-kilometer refined MPAS simulations to be honest, quite easily. The biggest hurdle there is not actually the resources, but as Jim pointed out, it's actually getting the infrastructure to behave well on our systems. So I think if we're talking about accessibility for users, I think we also do need to kind of separate that out into, what are fundamentally resource limited. There's also data analysis limited issues. So a lot of these data sets are available, such as we have these giant data sets, Project Diamond, things like that. But at the end of the day, it's not, it can be challenging to get access to that data if you want to analyze it locally. And there's some strategies, putting the data in the cloud, creating user accounts on external systems, things like that. But I suppose it's mostly a comment about kind of the more, nuanced aspects of this. There are also some benefits maybe in drawing from things like the weather community. There have been a lot of benefits of running simulations such as WRF, MPAS, things like that in some of these more leaner, meaner configurations. And I think maybe better drawing on some of that expertise can also help break down some of the barriers. So hopefully that sort of made sense, but it was kind of a synthesis of a couple of comments that had been made, I know of, at the table. So.
All right. One thing I'd love to hear from people, whenever we talk high res and ultra high res, it's pitched as the community is moving here. What percentage of the community do you expect to be running an ultra high resolution versus a high resolution run? And this matters because when we talk about the effort to enable this, especially on GPUs, which are really good for the ultra high resolution, but maybe not the high resolution, which would run faster on CPUs, it's a question of how much effort do we invest in something that's for, say, 1% of the community. Like if you tell me we need to put 50% of our FTEs towards something used by 1%, that's a challenge. If we're putting 10% towards something that's used by 10%, that's understandable. So I just want to get a sense of where we think this is going for the community. Because I agree with Gökhan, we should support all of these, but it's a question of how we support it and how much resources we put in. So I'd love to hear from each of you with your guess. I won't hold you to it, but it'd be great.
Maybe I can give a quick answer on our survey, and that was our question. Is it 1%? But it was actually not. It was actually a fair amount of people half of the, I don't know, maybe 20 people out of 60 that said they are interested. That doesn't mean they actually use it, but at least half of those said they already used the model. So we have to go more into detail, but maybe that is really something we have to look into more. Yeah, just from the survey, that would be your answer, not that it may be representative. But yeah, maybe somebody here.
Okay, I think I don't have maybe a picture of overall percentage as comprehensive as you presented in that pie chart, but I think what we can say is, for example, we put the high-res WACMX simulation online as part of the SEMA project. It's for space weather studies, and by far, I know at least 3 or 4 groups proposing for satellite missions. They use that as a virtual lab to for their forward modeling effort. And I think it's maybe not everyone in the community will run the model themselves, but they would like to use what comes out of it, and also for parameterization studies, like some kind of ground truth for parameterization studies.
I also want to give the chance to the 2 speakers online if they want to say something. Please raise your hand. I'm not putting you on the spot now, just saying. Okay, there we go. Go ahead.
Thank you so much for giving me this chance to speak. Yeah, I really agree. I mean, not everybody needs to be running these gigantic models to make great use of them. In fact, we already have a number of different downstream clients who use our high resolution models, even if they aren't running them. The data itself can be a valuable data set. The big challenge is getting it to the people we want to work with. So thank you.
Yeah, please go ahead.
Can I chime in just a little bit? So for the project we are working on, because we are also running some high resolution regional climate modeling, and we're also working Unity. I think one big challenge is, as also Monica mentioned, is how we actually convey processing the data in a meaningful and easy to accessible ways to the communities also remains to be a big challenge. And also, as Lucas just said, it's not only a challenge for the community members, but also for our downstream stakeholders. And I also want to echo back to the people mentioned a lot about the Leap Center as well as the machine learning. I think it's a great way that that we can probably using something like surrogate modeling or other machine learning kind of substitute to learning from those super high resolution modeling and use some meaningful ways to transfer those data to our stakeholders or community members in a relatively cheaper way. Yeah, training the model is not cheap, but they probably can use the already being trained model. Yeah.
Yeah, thanks for the response. I don't know how many people there are. Maybe are you in line too? Then we stop it after Peter, maybe. Can I just say one
Yeah,
please go ahead.
Sorry, just a very quick comment. Brian, you're not going to trick me into stating a percentage because you'll hold me to that. But I do just want to make a general point. When I went up to CSU, one of the first things I did was I had a workshop. All these people at the university who are interested in climate and climate change and climate impacts, but are not part of the traditional CSM community in terms of a Earth system science community, right? There was a lot of interest I want to do, looking at changes in terrestrial ecology or whatnot. We have to have much higher resolution simulations than the climate community typically. So I would just also say another aspect of what you're asking is how much could the community that really utilizes an ultra-high resolution version of CSM grow. I think there's a lot of people who could be entrained into this process and bring all different levels of Earth system science expertise into a project like this with that kind of capability. So I just want to make that point.
Okay, there we want to go.
Hi, I'm from the community.
What is your name? We want to go.
Hi, I'm from the community.
What is your name?
I have a question for Jim on a slightly, not the core topic of this discussion, but I was intrigued, I was intrigued by your fault tolerance idea that we have to work on this. So when I look at my own work as a postdoc and now PG students in my group, I say this is what we lose most time with, like having these errors trying to set up the model and not having answers, not finding the answers to them. So I was wondering if you have some ideas and some concrete plans to work on in this direction. So it's the fault tolerance, right?
Fault tolerance. I don't. But as we move to these exascale systems, it's going to have to happen because the mean time to failure when you're running on 80,000 processors is much shorter than if you're running on 800 processors.
Thanks a lot. One of the questions, it's a pretty simple question, which is like, we have this shared model that we're trying to put more and more complexity into, like carbon cycle, stratospheric processes, whatever else it is. But do we need to have all those processes like running when we're doing ultra high resolution runs? The question is, it's really expensive to have a very complex model. Should we have a simpler model that we use specifically for this ultra high sort of like simulations? That would be a lot cheaper to run at ultra high than the full complex, full carbon cycle, full everything else.
I think in some respects that's what Earthworks is. Yeah. It has a lot fewer. Correct me if I'm wrong. It has a lot fewer physical processes than the full CESM.
No. I mean, Earthworks is starting from the fully coupled CSM, all of the components, and learning to run at those really high resolution. We don't have everything turned on, but I mean the capabilities are there, right?
You're not running with chemistry, just throwing that in, but of course that wouldn't be even possible.
Does chemistry matter?
I think, okay, we have the last, I think let's go to the last one, that's you, and then if there's any responses from the panel, and then we conclude for today, because I think we all want to go out and have the reception, I assume.
I'll try not to stay too much in the way between you and the reception, but I'm a carbon cycle guy that is used to spinning up models for 2,000 years, so I come from a perspective of, I'm not an absolute advocate of ultra-high resolution, but I think that the point of view, I think what Brian's question, I think, is oversimplified, because if 10 years ago, before when we were trying to do the large ensemble, if we had said, how many people really think we want to have 50 ensemble members, and how many people want to do experiments with 50 plus ensemble members, not many people would have raised their hands, but the community has benefited tremendously from that activity. So I want to echo the comments here about synergies between these communities and benefiting from each other. Coming from someone at one end of the spectrum, that I think that all aspects of these communities can benefit from each other's efforts, and we should try to do that.
Yeah, that's a good comment. Does anybody want to respond? Else, I think this was a good ending comment, and I think everybody, the speakers and all the participation was a great discussion, and I hope we can continue it. Thank you.
So
thank you to our online speakers too.
Poster session as well, but we have the reception, there's all the drinks and all that stuff. You can grab as many beers I think you want, and you can check out the posters as well. Thank you.